Do you ever wonder what makes a life-changing history? Right, a solid mission of the visionaries. It was Dr. Anka and his colleagues' mission to accelerate technology development. Through the establishment of Institut Teknologi Sepuluh Nopember, their goodwill has encouraged ITS students to take important roles in both local and global communities, ministers, CEOs, professors, entrepreneurs, and yes, another history maker. These successful alumni were trained in a healthy learning environment that was equipped with various supporting facilities. From vocation to marine technology, all faculties and departments of ITS were formed to be the best place to learn science, technology, and design. 7 faculties and 1 interdisciplinary school. Scientists, Faculty of Science and Data Analytics. MARTech, Faculty of Marine Technology. INSYS, Faculty of Industrial Technology and Systems Engineering. Electics, Faculty of Intelligent Electrical and Informatics Technology. CivPlan, Faculty of Civil, Planning, and Geoengineering. CreaBiz, Faculty of Creative Design and Digital Business. Vocation, Faculty of Vocational. And Interdisciplinary School of Management and Technology. Recognized as one of the top best-ranked institutes doesn't mean the finish line for ITS. To gain greater international recognition, ITS launched International Undergraduate Program. Students can get wider international exposure through 20 study programs they can apply. The chances are also open for professors from all over the world to teach and conduct research at ITS. These opportunities have made international joint research and other international activities successfully performed. Like IUP, students and lecturers from other programs have also contributed to the ITS achievements. Appreciations earned exemplify Institute's excellent performance. But technology and academic excellence is not the only goal of the Institute. Students are guided to apply their knowledge for the welfare of society. Because to note a new life-changing history, technology must advance humanity. ITS, Institut Teknologi Sepuluh Nopember.
我们谢谢国科会的这个支持啊，那我们可以有机会跟台科大毕业回国工作这个 杰出的校友一起来合作，看看呢能不能把台湾很成熟的一些环境的法规、循环经济的制度跟做法呢引介到印尼，彼此呢可以有一个交流。举个例子来说呢，我们在绿色工厂的标章制度，非灰、炉渣、炉石呢转换变成这个低碳的营建材料呢，台湾的相关的法规做法非常的成熟。透过我们的校友，可以跟印尼的官方、产业或者是学界呢，可以有一个很好的一个网络关系 （networking） 以及建立这个伙伴的循环关系。透过这样的一个平台，可以让台湾跟印尼产官学就一个绿色的技术循环经济呢，非常简便的、很有效的一个沟通。我觉得做这个事情是非常的有意义的。
本中心跟2个单位合作，那都是一直持续在进行。第一个是新加坡的半官方新加坡智慧局国际处，那第2个我们交流的合作机关是新加坡国立的新药社科大学。新创的环境里面，智慧财产是一个蛮重要的环节，毕竟在这个技术的保护上是绝对重要的哈。这是让我们技术研发有一个很实质的回馈。我们在了解到新加坡它在官方，因为它是一个商业组成的环境所以我们知道它在官方无形资产的议题上面是特别重视。
我们看到了东南亚巨大的商机，因此我们想要把台湾所累积的一些技术，然后包含专利这边，还有我们的一些 domain know-how， 能够用软实力来去让这个世界来看到。所以我们在新加坡这个市场呢，我们也会非常关注当地的会展产业，就会涉及到非常多的一些包含的 IP、专利、商标著作权相关的一些部署。那如果有单位能够提供我们帮助跟扶持的话，那这点对我们来讲，进入陌生的市场，其实会提高比较多的一些成功率，可以减少我们的一些犯错的一些这种踩坑的一些机会。
台印度人工智慧海外科研中心在过去3年，跟印度理工学院罗巴尔分校合作的非常愉快跟密切IIT Ropar 跟我们中正大学之间有签署一个双联博士学位学程。
About this center, this is a very promising center. Like already there is a collaboration between India and Taiwan.
This center helps students a lot, how they can collaborate, how they can join, choose their program, and how they can go further.
我们在当地跟当地的政府像 Himachal Pradesh 等等还有巴地的这个工业区的执行长我们合作的范围主要包含智慧环保跟智慧交通在这一方面，我们在当地进行多项资料的收集以及分析完之后做 AI 的应用落地，来提升他们的环境的监控跟交通的效率。
在菲律宾这边吕宋岛的北部的山区义富高，这里是一个世界遗产指定登陆的地点。那它里面有很多关于人文生态，还有当代的地景保存，还有原住民族权利的相关的议题。那我们就发现说，这里面有很多值得双方去进一步交流、发展合作的地方。那我们也在菲律宾这边，透过这个台菲科研中心的这个办公室，作为一个教学的基地，让菲律宾这边的原住民知识的拥有者，像是部落的耆老跟他们的中小学的老师，在这边去发展课程、发展教材，然后让这些老师回到他们自己的教育场域里面，把这些在地知识、原住民知识传递给他们的学生们。
Overall, it was a very fun experience for me because I got to meet leaders, elders in the indigenous peoples communities who imparted some of the wisdom.
我们在这个研究中心里面，我们跟斯里兰卡合作，我们的一些重点要研究斯里兰卡在临近机场有个叫尼干博拉顿， 他们的优氧化跟他们的缺氧状况。2019年的年底，也在另外一个大学叫鲁夫纳大学成立了一个叫做海洋研究站。那我们要去看看当地的这个水质优氧化的状况，还有这个珊瑚白化，还有鱼类有时候会突然暴毙，那其实就是因为缺氧的问题。
最主要这一台跟其他市面上也会看到一些科技养殖的设备有一些最大的不同，就是这个灰色盒子里面有二氧化碳的感应器。那我们这里下面还有一个水汽平衡器。以产业的角度来说，今天如果有跨国的水产养殖业的业者，那我们这台仪器就可以提供你背后的一些基础知识，可以协助你的量测水体里面的碳通量。那就有助于可以了解这个水产养殖业可以留下多少碳足迹。
那我们叫乌角病实际上是确实出现在湄公河畔，因为它是跟挖地下水是有关系的，那也跟挖地下水技术有关系。所以目前我们比较具体的是，像泰国那边的国家他们的金属及材料中心做感测材料的开发，然后我们这边像董瑞安院长他们是做电极材料开发。然后我们这边还找了我们的国家研究院的这个仪科中心，把它做整合做设备。这个中心目前的情形大概就希望链接国际合作，然后希望用我们的长处、对方的长处，解决对方现场的问题。
那湄公河大家都知道，其实对东南亚国家来讲，它是非常重要的生命之河。我们的团队带了手掌大小的仪器，然后我们到了清莱河畔之后，我们就在河畔旁比较刻苦的地方架设起我们的仪器。我们在捞起那个河水的当时，其实在透明的瓶子里面就已经可以看到蛮多悬浮物的。我们希望连同湄公河附近的国家一起来做一个比较跨国的，但是又区域性的水质的整治。我们在泰国那边主要的研究单位有国家金属与材料研究中心、朱拉隆功大学、马其顿大学跟泰国农业大学。那我们跟这几个大学，其实在今年也会有后续的合作和三边或者是双边的国际研讨会。
Globally, one of the challenges for developing countries is to provide excellence and world-class infrastructure. It is a part of the global goals known as Sustainable Development Goals or SDGs. Several of the goals are related to sustainable infrastructure, such as number 6 about clean water and sanitation, number 9 about the industry, innovation and infrastructures, number 11 about sustainable city and community, number 12 about responsible production and consumptions, and number 13, 14, 15 about climate change, life below water, and life on the land. Since 2015, Indonesia has started focusing on massive infrastructure building to support economic growth and welfare. As a developing country, building a green, environmentally friendly, and sustainable infrastructure is necessary. The Research Center for Infrastructure and Sustainable Environment aims to answer the challenges to create sustainable and environmentally friendly infrastructure.
The Research Center of Infrastructure and Sustainable Environment, under the Directorate Research and Community Services of Institut Teknologi Sepuluh Nopember, has a goal to create a sustainable infrastructure that has 4 pillars, including environmental sustainability, social sustainability, financial sustainability, and institutional sustainability.
The roadmap of research has focuses on 5 main topics, including mitigation and adaptation of climate change, pollution prevention, built environment, protection of natural resources, and efficiency use of resources and circular economy. More than 80 professional researchers from different expertise are involved in this research center, such as civil engineering, environmental engineering, architecture, urban planning, chemical engineering, biology, chemistry, and others. We have more than 10 partners at the international levels. At the national level, we provide services for preparing many different environmental analyses, based on our expertise. We also conduct the training course include on-the-job training.
Research Center for Infrastructure and Sustainable Environment, dedicated to create world-class infrastructure with sustainability and environmental friendly concept. Collaborate with us, be better, together, be greener.
Do you ever wonder what makes a life-changing history? Right, a solid mission of the visionaries. It was Dr. Anka and his colleagues' mission to accelerate technology development. Through the establishment of Institut Teknologi Sepuluh Nopember, their goodwill has encouraged ITS students to take important roles in both local and global communities, ministers, CEOs, professors, entrepreneurs, and yes, another history maker. These successful alumni were trained in a healthy learning environment that was equipped with various supporting facilities. From vocation to marine technology, all faculties and departments of ITS were formed to be the best place to learn science, technology, and design. 7 faculties and 1 interdisciplinary school. Scientix, Faculty of Science and Data Analytics. MarTech, Faculty of Marine Technology. INSYS, Faculty of Industrial Technology and Systems Engineering. Electex, Faculty of Intelligent Electrical and Informatics Technology. CivPlan, Faculty of Civil, Planning, and Geoengineering. CreaBiz, Faculty of Creative Design and Digital Business. Vocation, Faculty of Vocational. And Interdisciplinary School of Management and Technology. Recognized as one of the top best-ranked institutes doesn't mean the finish line for ITS. To gain greater international recognition, ITS launched International Undergraduate Program. Students can get wider international exposure through 20 study programs they can apply. The chances are also open for professors from all over the world to teach and conduct research at ITS. These opportunities have made international joint research and other international activities successfully performed. Like IUP, students and lecturers from other programs have also contributed to the ITS achievements. Numerous appreciations earned exemplify Institute's excellent performance. But technology and academic excellence is not the only goal of the Institute. Students are guided to apply their knowledge for the welfare of society. Because to note a new life-changing history, technology must advance humanity. ITS, Institut Teknologi Sepuluh Nopember.
我们谢谢国科会的这个支持了哈，那我们可以有机会跟台科大毕业回国工作这个杰出的校友一起来合作，看看呢能不能把台湾很成熟的一些环境的法规、循环经济的制度跟做法呢引介到印尼，彼此呢可以有一个交流。举个例子来说呢，我们在绿色工厂的标章制度，非灰、炉渣、炉石呢转换变成这个低碳的营建材料呢，台湾的相关的法规做法非常的成熟。透过我们的校友，可以跟印尼的官方、产业或者是学界呢，可以有一个很好的一个网络关系 （networking） 以及建立这个伙伴的循环关系。透过这样的一个平台，可以让台湾跟印尼产官学就一个绿色的技术循环经济非常简便的、很有效的一个沟通。我觉得做这个事情是非常的有意义的。
中心跟2个单位合作，那都是一直持续在进行。第一个是新加坡的半官方新加坡智慧局国际处，那第2个我们交流的合作机关是新加坡国立的新药社科大学。新创的环境里面，智慧财产是一个蛮重要的环节，毕竟在这个技术的保护上是绝对重要的哈。这是让我们技术研发有一个很实质的回馈。我们在了解到新加坡它在官方，因为它是一个商业组成的环境所以我们知道它在官方无形资产的议题上面是特别重视。
我们看到了东南亚巨大的商机，因此我们想要把台湾所累积的一些技术，然后包含专利这边，还有我们的一些 domain know-how， 能够用软实力来去让这个世界来看到。所以我们在新加坡这个市场呢，我们也会非常关注当地的会展产业，就会涉及到非常多的一些包含的 IP、专利、商标著作权相关的一些部署。那如果有单位能够提供我们帮助跟扶持的话，那这点对我们来讲，进入陌生的市场其实会提高比较多的一些成功率，可以减少我们的一些犯错的一些这种踩坑的一些机会。
台印度人工智慧海外科研中心在过去3年，跟印度理工学院罗巴尔分校合作的非常愉快跟密切IIT Ropar 跟我们中正大学之间有签署一个双联博士学位学程。
About this center, this is a very promising center. Like already there is a collaboration between India and Taiwan.
This center helps students a lot, how they can collaborate, how they can choose their program, and how they can go further.
我们在当地跟当地的政府像 Himachal Pradesh 等等还有巴地的这个工业区的执行长我们合作的范围主要包含 智慧环保跟智慧交通在这一方面，我们在当地进行多项资料的收集以及分析完之后，做 AI 的应用落地，来提升他们的环境的监控跟交通的效率。
在菲律宾这边，吕宋岛的北部的山区一夫高这里是一个世界遗产指定登陆的地点。那它里面有很多关于人文、生态，还有当代的地景保存，还有原住民族权利的相关的议题。那我们就发现说，这里面有很多值得双方去进一步交流、发展合作的地方。那我们也在菲律宾这边，透过这个台菲科研中心的这个办公室，作为一个教学的基地，让菲律宾这边的原住民知识的拥有者，像是部落的耆老跟他们的中小学的老师，在这边去发展课程、发展教材，然后让这些老师回到他们自己的教育场域里面，把这些在地知识、原住民知识，传递给他们的学生们。
Overall, it was a very fun experience for me because I got to meet leaders, elders in the indigenous people's communities who imparted some of the wisdom.
我们在这个研究中心里面，我们跟斯里兰卡合作，我们的一些重点要研究斯里兰卡在临近机场有个叫尼干博拉棍，他们的优氧化跟他们的缺氧状况。2019年的年底，也在另外一个大学叫鲁夫纳大学成立了一个叫做海洋研究站。那我们要去看看当地的这个水质优氧化的状况，还有这个珊瑚白化，还有鱼类有时候会突然暴毙，那其实就是因为缺氧的问题。
最主要这一台跟其他市面上也会看到一些科技养殖的设备有一些最大的不同，就是这个灰色盒子里面有二氧化碳的感应器。好，那我们这里下面还有一个水汽平衡器。以产业的角度来说，今天如果有跨国的水产养殖业的业者，那我们这台仪器就可以提供你背后的一些基础知识，可以协助你的量测水体里面的碳通量。哦，那就有助于可以了解这个水产养殖业可以留下多少碳足迹。
那我们知道乌角病实际上是确实出现在湄公河畔，因为它是跟挖地下水是有关系的，那也跟挖地下水技术有关系。所以目前我们比较具体的是，像泰国那边的国家他们的金属及材料中心做感测材料的开发，然后我们这边像董瑞安院长他们是做电极材料开发。然后我们这边还找了我们国家研究院的这个仪科中心，把它做整合做设备。这个中心目前的情形大概就希望链接国际合作，然后希望用我们的长处、对方的长处，解决对方现场的问题。
那湄公河大家都知道，其实对东南亚国家来讲，它是非常重要的生命之河。我们的团队带了手掌大小的仪器，然后我们到了清莱河畔之后，我们就在河畔旁比较刻苦的地方架设起我们的仪器。我们在捞起那个河水的当时，其实在透明的瓶子里面就已经可以看到蛮多悬浮物的。我们希望连同湄公河附近的国家一起来做一个比较跨国的，但是又区域性的水质的整治。我们在泰国那边主要的研究单位有国家金属与材料研究中心、朱拉隆功大学、马西敦大学跟泰国农业大学。那我们跟这几个大学，其实在今年也会有后续的合作和三边或者是双边的国际研讨会。
Globally, one of the challenges for developing countries is to provide excellence and world-class infrastructure. It is a part of the global goals known as Sustainable Development Goals or SDGs. Several of the goals are related to sustainable infrastructure, such as number 6 about clean water and sanitation, number 9 about the industry, innovation and infrastructures, number 11 about sustainable city and community, Number 12 about responsible production and consumptions, and number 13, 14, 15 about climate change, life below water, and life on the land. Since 2015, Indonesia has started focusing on massive infrastructure building to support economic growth and welfare. As a developing country, building a green, environmentally friendly, and sustainable infrastructure is necessary. The Research Center for Infrastructure and Sustainable Environment aims to answer the challenges to create sustainable and environmentally friendly infrastructure.
The Research Center of Infrastructure and Sustainable Environment, under the Directorate, Research and Community Services of Institut Teknologi Sepuluh Nopember, has a goal to create a sustainable infrastructure that has 4 pillars, including environmental sustainability, social sustainability, financial sustainability, and institutional sustainability.
The roadmap of research has focuses on 5 main topics, including mitigation and adaptation of climate change, pollution prevention, built environment, protection of natural resources, and efficiency use of resources and circular economy. More than 80 professional researchers from different expertise are involved in this research center, such as civil engineering, environmental engineering, architecture, urban planning, chemical engineering, biology, chemistry, and others. We have more than 10 partners at the international levels. At the national level, we provide services for preparing many different environmental analyses, based on our expertise. We also conduct the training course, include on-the-job training.
Research Center for Infrastructure and Sustainable Environment, dedicated to create world-class infrastructure with sustainability and environmental friendly concept. Collaborate with us, be better, together, be greener.
Do you ever wonder what makes a life-changing history? Right, a solid mission of the visionaries. It was Dr. Anka and his colleagues' mission to accelerate technology development. Through the establishment of Institut Teknologi Sepuluh Nopember, their goodwill has encouraged ITS students to take important roles in both local and global communities, ministers, CEOs, professors, entrepreneurs, and yes, another history maker. These successful alumni were trained in a healthy learning environment that was equipped with various supporting facilities. From vocation to marine technology, all faculties and departments of ITS were formed to be the best place to learn science, technology, and design. 7 faculties and 1 interdisciplinary school. Scientists, Faculty of Science and Data Analytics. MarTech, Faculty of Marine Technologies. INSYS, Faculty of Industrial Technology and Systems Engineering. Electics, Faculty of Intelligent Electrical and Informatics Technology. CivPlan, Faculty of Civil, Planning, and Geoengineering. CreaBiz, Faculty of Creative Design and Digital Business. Vocation, Faculty of Vocational. And Interdisciplinary School of Management and Technology. Recognized as one of the top best-ranked institutes doesn't mean the finish line for ITS. To gain greater international recognition, ITS launched International Undergraduate Program. Students can get wider international exposure through 20 study programs they can apply. The chances are also open for professors from all over the world to teach and conduct research at ITS. These opportunities have made international joint research and other international activities successfully performed. Like IUP, students and lecturers from other programs have also contributed to the ITS achievements. Appreciations earned exemplify Institute's excellent performance. But technology and academic excellence is not the only goal of the Institute. Students are guided to apply their knowledge for the welfare of society. Because to note a new life-changing history, technology must advance humanity. ITS, Institut Teknologi Sepuluh Nopember.
Distinguished guests, ladies and gentlemen, thank you for attending this conference. The conference is about to commence shortly. Please kindly find your comfort seat. Before that, let's take a look at the following health, safety, environment video.
Selamat datang di Institut Teknologi 10 November. Di sini, kami berkomitmen untuk menciptakan lingkungan belajar dan bekerja yang aman untuk semua orang. Pada video ini, saya akan memandu Anda mengenai berbagai aspek penting dari induksi keselamatan, termasuk prosedur evakuasi darurat, peraturan kebakaran, dan tindakan pengamanan yang harus diikuti. Saat ini, Anda berada di gedung Research Center ITS. Gedung ini telah dilengkapi dengan sarana keselamatan seperti alat pemadam api ringan dan tangga darurat yang ada di sekitar ruangan ini. Untuk informasi selengkapnya, berikut panduan induksi keselamatan di gedung Research Center ITS.
Bila terjadi kondisi darurat seperti gempa, tetap tenang dan segera berlindung di bawah meja atau kursi atau peralatan apapun yang cukup kuat di sekitar Anda. Lindungi kepala Anda dan tunggu hingga gempa mereda. Hindari kaca dan benda yang berpotensi untuk jatuh.
Anda dapat menghubungi nomor emergensi yang ada jika membutuhkan pertolongan.
Bila melihat kebakaran, tetap tenang dan jangan panik. Bila mendengar suara sirine darurat, jangan panik dan segera hentikan aktivitas Anda. Laksanakan prosedur evakuasi dengan tenang, lalu keluar dari gedung dan mengikuti jalur evakuasi menuju tempat kumpul terdekat. Hindari menggunakan lift saat kondisi darurat. Lakukan pertolongan pertama bila terdapat korban atau hubungi rumah sakit terdekat atau emergency call center untuk penanganan lebih lanjut. Pastikan Anda berjalan keluar gedung secara teratur menuju tempat mobil darurat. Saat sudah bertemu dengan petugas penjaga setempat, segera laporkan kejadian. Jika ada asap, berunduklah sambil menggunakan masker atau menutup hidung dengan segala kain yang ada.
Demikianlah prosedur keselamatan di Institut Teknologi Sepuluh Nopember. Ayo kita utamakan keselamatan dan wujudkan ITS yang aman dan nyaman.
Distinguished guests, ladies and gentlemen, now please enjoy the traditional dance Jejer Gandrung from Banyuwangi, performed by UKTK ITS. Please give a big applause.
Sampur penghormatan dimulai.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, Shalom, Om Swastiastu, Namo Buddhaya. May God always bestow prosperity to all of us. Distinguished guests, ladies and gentlemen, welcome to the International Conference on Sustainable Semiconductor Manufacturing at Auditorium Research Center ITS Campus, Sukolilo, Surabaya. It is such an honor for me, Azefa Pradiar, as a Master of Ceremony, to finally see you in person. Thank you very much for your kind participation and presence. First and foremost, we would also like to extend warm welcome to our VIPs and guests, the Honorable Rector of ITS, Mr. Bambang Pramujati, Representative of Taipei Economic and Trade Office Taiwan, Mr. John C. Chen, Representative from Deputy of International Economic Collaboration Affairs, Ministry of Economic Affairs Indonesia, Professor Hamam Riza, Consul General of the U.S. Consulate General Surabaya, Mr. Chris Green, Representative Directorate of Research and Innovation Funding of BRIN, Dr. Ajeng Arumsari, President of Taiwan Tech Global Alumni Association and also CEO of Toolcorp Taiwan, Mr. Ted Chen, Director General Taipei Economic and Trade Office Surabaya, Taiwan, Mr. Isaac CCU, and all distinguished speakers, VIP guests, and participants. And now, the International Conference Sustainable Semiconductor Manufacturing begins. Distinguished guests, ladies and gentlemen, to start this conference, please stand up for the national anthem of the Republic of Indonesia and followed by hymn of ITS.
Jadi pandu
Thank you. Please be seated. We will begin our agenda with welcoming remarks from Rector of ITS. We kindly invite the Honorable Rector of ITS, Mr. Bambang Pramujati, to come up to the stage and deliver his welcoming remarks. So please welcome Mr. Bambang Pramujati. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera, salam sehat buat kita semua. Good morning everyone, honorable guests. Today's international conference, the Consul General Mr. Chris Green from US Consulate General Surabaya and all the delegation of the US Consulate, Mr. John C. Sen as the representative of Taipei Economic and Trade Office Taiwan, Mr. Eric Su, Foreign Commerce Service Consular US Embassy, and then we have Mr. Philip Green as the Deputy Director of Economic Growth and Education USAID, Dr. Holin, the Executive Director of Science and Technology Division Taipei Economic and Culture Office in Australia, Mr. Isaac Chiu, Director General Teto Surabaya and Rector of Vidya Mandala Catholic University, Prof. Kunchoro, Prof. Liu, Vice President of Taiwan Tech and Director of TIC, and then we have also Ibu Ajeng, Director of Research and Innovation Funding from BRIN, and also all delegate, all speaker guests from US, Taiwan, and Indonesia, and also we have colleagues from other universities such as Sumatera Utara University, Institut Teknologi Bandung, UPN, etc. Thank you very much, ladies and gentlemen. Good morning, everyone. It is my distinct honors and pleasure to welcome you all to the International Conference on Sustainable Semiconductor Manufacturing, held here in the second largest city, the dynamic, beautiful and vibrant city of Surabaya. Today, we gather here in the auditorium of Research Center of ITS. This is 11th floor of the Research Center of ITS, to discuss and explore the critical intersection of semiconductor manufacturing and sustainability, a topic of paramount importance in our rapidly evolving technological landscape. This international conference is conducted under the collaboration of ITS, USAID, the US Embassy, Teto Jakarta and Surabaya, with a sponsor from the National Science and Technological Center NSCT Taiwan, and organized by Taiwan Indonesian Science and Technological Innovation Center STIC. STIC itself was a consortium under the collaboration of ITS, Taiwan Tech and Vidya Mandala Catholic University and BRIN that started in 2021 with STIC, CIGER, and develop a new partnership under STIC. Thank you for the contribution. And as we stand on the brink of a new era of technology, the need for sustainable practices in semiconductor manufacturing has never been more important. Indonesia is making significant strides in developing its semiconductor industry as part of its Indonesia Mas Vision 2045. This vision aims to transfer Indonesia into a sovereign, advanced, just, and prosperous nation by its 100th anniversary in 2045. And we may ask why Indonesia put semiconductor as one part of this vision. Indonesia has abundant natural resources such as silica, shale, and nickel, which are essential for semiconductor production. By leveraging these resources, Indonesia can create a sustainable and self-sufficient semiconductor industry. Other than that, the semiconductor industry is a high-value sector that can significantly boost Indonesian economy. By developing this industry, Indonesia aims to create high-skilled jobs, increase GDP, and reduce dependency on import. However, Indonesia still faces some challenges such as shortage of professionals with the necessary expertise, in semiconductor technology. Indonesia R&D capabilities in semiconductor field are still developing. We realize that Indonesia need to collaborate with various international partners to develop the semiconductor industry, such as with the US and Taiwan that already well established in the field. And again, today the seminar is going to discuss a lot of things about the semiconductor industry. And again, thank you very much for the time and support from all partners. ITS is one of the leading university in science and technology, also appointed by the government with 40 other universities in Indonesia under consortium to develop chip design in Indonesia. We have already established collaboration with industry partners to develop products related to this field. We developed tablet Merah Putih and also specializing in production automation of LED bulb in-house. There are several examples of R&D of ITS in semiconductor. We are privileged here today to have distinguished assembly of expert industrial leaders and academics from around the globe. From the US, we have Prof. Taufik, we have Prof. Yu, and several speakers from industries such as Intel, Micron, Nokia, and AMD. And also from Taiwan, we have speakers and experts from NTUSA, from CYCU, and industry in Taiwan. Your presence here underscore the significance of international cooperation and the sharing of knowledge in advancing sustainable practices within the semiconductor industry. Over the next few days, we will delve into the latest research, discuss the challenges we face, and identify opportunity to drive sustainable innovation. Today's conference also attended by various industry partners who work in semiconductor, academia, and research from different universities in Indonesia. And again, thank you very much for your coming and your participation in this conference. We also have young talented students from many different campuses and backgrounds. We really hope that this international conference will bring a lot of issues and transfer knowledge on how Indonesia can leverage to build the sustainable semiconductor industry. I encourage each of you to actively engage in the discussion, share the valuable insight, and build lasting connection. Let us use this platform to exchange ideas, forge partnership, and pave the way for a more sustainable future in semiconductor manufacturing. In closing, I would like to extend my deepest gratitude to our speakers, our sponsor, that is NSCT Taiwan and USAID, organizer, and all participants for making this conference possible. Your support and dedication are truly appreciated. Thank you, and I wish you all have a productive and inspiring conference. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Rector of ITS, for your remarks. Now, please be seated. The next one, we kindly invite the Honorable President of Taiwan Tech Global Alumni Association and also CEO of Toolcorp Taiwan, Mr. Ted Chen, to come up to the stage and deliver his remarks. So please welcome Mr. Ted Chen. The time is yours.
Good morning, ladies and gentlemen. On behalf of NTUST Alumni Association, it is my great privilege to welcome you to the International Conference on Sustainable Semiconductor Manufacturing here in Surabaya, Indonesia. It is an honor to stand before such a distinguished assembly of professors, researchers, and leaders who are dedicated to shaping a sustainable future for our industry. The semiconductor industry is the heart of technology, innovation driving advances that touch every aspect of modern life, from smartphone and medical device to renew the energy system on these sustainable semiconductors.
Pool our resources and inspire each other to push the boundaries of audience. I trust that through our collective expertise and shared commitment, we can create an ecosystem that not only meets the demand of our current. I would like to wish everyone of you a successful meeting and fruitful results of today's get together. Thank you so much. 谢谢。
Thank you, Representative of Taipei Economic and Trade Office, Taiwan. The next one, we kindly invite the Consul General of the U.S. Consulate General, Surabaya, Mr. Chris Green, to come up on the stage and deliver his remarks. So please welcome Mr. Chris Green. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Salam Swastiastu, Namo Buddhaya, Salam Kebajikan. Selamat pagi, Genjang. Good morning. Thank you for the opportunity to participate today and for the opportunity to speak with you. We're very excited to be part of this event and for the United States government to be a sponsor of what we believe is a very exciting opportunity for the future of Indonesia. Before I get started, I want to recognize first of all our host, Director Pak Bambang. Thank you very much for agreeing to host this event. To our distinguished visitors, I don't want to stop and name you all one by one, but thank you all for coming. I do want to recognize the organizers in particular, the Taiwan Indonesia Science and Technology Innovation Center, and our friends at the Taipei Economic and Trade Office from Jakarta and Surabaya. Thank you very much. I also understand we have Dr. Hugh from Arizona State University here today. From one Sun Devil to another, welcome to Surabaya. my own alma mater, a proud graduate of ASU. So I think as some of you may know, because we talk about it a lot, 2024 marks 75 years of diplomatic relations between the United States and Indonesia. And since the beginning of that partnership, one of our priorities within the bilateral relationship has been helping Indonesia achieve its economic potential. And as we think about that, it means many things, but one of the things it means is in the 21st century, finding a way for Indonesia to become part of high-tech global supply chains. And semiconductors, being the focus of what we're talking about here today, are a huge part of everything that we think of as high-tech. Our support for Indonesia ranges far and wide, and including United States support for Indonesia's goals to join the OECD. But we're here today to talk about semiconductors. And we all know this, but I think it's worth just repeating to focus. We think of semiconductors a lot of times as very small things, the phones in our pockets or our kids' PlayStations. But the truth is semiconductors power the modern world. They power our hospitals, our airplanes, our satellites. Absolutely everything relies on semiconductors. And advancements in this sector is going to be critical for Indonesia to position itself at the forefront of technological innovation and be part of these important global supply chains. And the United States is committed to supporting Indonesia specifically in this endeavor. We are working with Indonesia on a variety of fronts to help Indonesia achieve its goals in manufacturing, innovation, investment, and workforce development. And the United States government does this in two ways. The first is through education, through support for Indonesians' own efforts to improve education and workforce development. Specifically, the USAID-funded Higher Education Partnership Initiative, or HEPI, which is the area we collaborate very closely with Arizona State University on, aims to help Indonesian institutions improve their science, technology, engineering, and mathematics programs. And the second way that we're supporting this is through direct sector support. The U.S. Department of State funds the International Technology and Security Innovation Fund, or ITSI, and very soon we will begin partnering with Indonesian institutions and companies and to begin promote secure semiconductor supply chain development in Indonesia. So for this conference, we have opportunities here to speak with not just our distinguished visitors and academic experts, but also with private sector companies, US companies and Taiwanese companies who have joined us to explore opportunities in Indonesia, to share knowledge, and identify strategies to overcome the challenges Indonesia faces to enter this field. But we are confident, as I believe all of you should be, that events like this seminar can provide a foundation to move forward and achieve Indonesia's ambitions in the semiconductor universe. So with that, again, I want to say thank you to our hosts and to our distinguished visitors. I hope that you all enjoy the conference and take advantage of the unique opportunities here to network and collaborate with such a diverse group of experts. Thank you very much.
Thank you, Consul General of the U.S. Consulate General Surabaya, for your remarks. We kindly extend our welcome to the Honorable Rector of ITS for your kind participation on today's conference. Before that, we kindly invite the honorable guest to come up to the stage as follows: Rector of ITS, Mr. Bambang Pramujati, President of Taiwan Tech Global Alumni Association, also CEO of Tool Corp Taiwan, Mr. Ted Chen, Representative of Taipei Economic and Trade Office Taiwan, Mr. John C. Chen, Consul General of the U.S. Consulate General Surabaya, Mr. Chris Green, Representative of the U.S. Consulate General Surabaya, Mr. Chris Green, Representative of Directorate of Research and Innovation Funding of BRIN, Dr. Ajeng Arumsari, Representative from Deputy of International Economic Collaboration Affairs, Ministry of Economic Affairs Indonesia, Professor Hamam Riza, to come up on the stage to receive a token appreciation from ITS and also Taiwan Indonesia Science, Technology, Innovation and Center. And to present the token of appreciation, the first one from ITS will be given by the Director of ITS, Mr. Bambang Pramujati, to Representative Consul General of the U.S. Consulate General Surabaya, Mr. Chris Green, Okay, let me count down for take a pictures from 3, 2, 1. Once again, 3, 2, 1. Thank you, please give a big applause for us, and thank you, please be seated. Thank you, and next one will be a group photo session together. So we kindly invite the honorable VIPs and guests and also all of the participants to stand up and move closer to find your best position to be captured at this momentous event. So please stand up and also move closer to find your best position. Okay, let me count it down from 3, 2, 1. Smile. Once again, in 3, 2, 1. Okay. Once again, 3, 2, 1. Thank you. Please give a big applause for us and please be seated. Once again, thank you very much to the Honorable Rector of ITS and also the Honorable respected guests. For the Honorable Rector of ITS, you may leave the auditorium to continue your next agenda. Once again, please give a big applause for us. Continuing our agenda, now we kindly invite representative from Directorate of Research and Innovation Funding of BRIN, Dr. Ajeng Arumsari, to come up to the stage and deliver her remarks. So please welcome Dr. Ajeng Arumsari. The time is yours.
Thank you, Honorable Rector ITS, Mr. Bambang Pramujati, Representative Teto, Dr. John Chen, Mr. Chris Green, Mr. Ted Chen, and then the Representative Deputy of the Collaboration Economic International, and then keynote speakers, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. It's with great pleasure and honor that I can join in this international seminar on sustainable semiconductor manufacturing today. As we gather here, we are embarking in a journey of knowledge sharing and then collaboration and innovation in one of the most dynamic and crucial sectors of the global economy. Next. Yeah, Indonesian government realized that semiconductor industry has profound impact on technology, innovation, and economic development. Also plays a play a role in shaping the future of the world. And Indonesia has potential resources such as the silica, tin metal, tin ore, etc. And we have target in electronic sector until 2030 to build the local capabilities for the advanced component manufacturing, including the semiconductor manufacturing. Next. And BRIN always support the research through the research funding and also the infrastructure on the semiconductor. And for your information, we have the three functions here. First, to policy support, and then as the funding agency, and also for the executing agency to conduct the research. Next, yeah. And this slide shows that one of our science and technology campus we have in Bandung. We call it the KST Sama Unsama Dikun, and in that place we have the one research center for electronics. So this research center conduct the research, the development, measurement, and implementation of the electronic devices and system. So there is several research group in here that relate with the semiconductor. So all of you can collaborate with our researchers relate with the semiconductor. Next. And this is the research framework. So they start from the design and simulation, and also the fabrication and the characterization. Next. And we have some infrastructure facilities here, including the clean room and also the characterization instrumentation like SEM, and then also the TGAS, etc. So all of this instrumentation is an open platform, so all of you can utilize these facilities. So you just go through our website and you can utilize these facilities. And next. Yeah, and now actually as our funding agency, BRIN also have we have the 8 schemes for the research and innovation funding related with the research grant. And of course, these 8 schemes can be accessed online and also open all year round for everyone. So all of the it's not only for the BRIN researcher, but also for the academia and then industry and also the startup. Next. Yeah, until now we funded more than 1,500 projects with the grant amount more than 365 billion rupiah. So through the 170 institutions are funded in here. And next. And we funded 5 projects related with the semiconductor. So it consists of from the researcher from BRIN and also from the campus. Next, and this is the detail of that 5 projects. So there are 3 from BRIN and then also 2 from the university, Universitas Gajah Mada and Universitas Riau. So of course we welcome all of you to submit in our scheme. Next. And now we also develop about the collaborative platform. So this collaborative platform is the scheme that we can do joint research activity managed by BRIN. Each topic will have the one manager, platform manager, and then they will conduct the open call for the proposal. So I hope that maybe in the future we will have the collaborative platform related with the semiconductor. And of course, it's not only about the research grant here, but also we do the how I can say the researcher mobility. So in this scheme, we also can invite the postdoctoral, the visiting researcher, visiting professor from overseas to come to Indonesia and do research together with the BRIN researcher and also from the national university. Next. And also now we are currently have initiated with the more than 16 funding agency. We have the collaboration and agreement from the several countries, and we hope also that soon we can have the cooperation with the funding agency from Taiwan. Next. This is the detail of our collaboration. First, we have the joint call. So in joint call, we have the agreement with the funding agency from overseas, and then we do the joint call. And the researcher from Indonesia have to collaborate with the researcher from the country partner. And also we try to make the industry engagement. We call it the scheme 2+2. So it means that the researcher from Indonesia and also the country partner have to collaborate with the industry. So we hope that through this program we can accelerate the research product to the commercialization by industry. And the last one is we have the scheme for the research collaboration center for industry. So in here, the industry will be host for the collaboration scheme with the researcher from BRIN and also the researcher from university. And then they can utilize our all infrastructure in BRIN and then the research funding and also the researcher mobility scheme. So as we embark on this journey together, let us embrace the spirit of collaboration and the creativity for the semiconductor industry in Indonesia and Taiwan. Let us seize this opportunity to learn from each other for a brighter and more sustainable future. I wish you all have the successful and productive seminar today. Thank you.
Thank you, representative from Directorate of Research and Innovation Funding of BRIN, for your remarks. Ladies and gentlemen, continuing this conference, we will have the first plenary session and also collective Q&A. As information, each of the speakers must finish their presentations within 20 minutes, and the collective Q&A must be wrapped up within 20 minutes. And now, we would like to invite our moderator, Dr. Aris Siddiqui, to lead the whole session. So please welcome Dr. Aris Siddiqui to come up to the stage. So please give it a big applause for our moderator. And now the time is yours.
Thank you. Ladies and gentlemen, good morning and welcome to the first session of the International Conference on Sustainable Semiconductor and Manufacturing 2024. My name is Aris Siddiqui, and I'm very honored to be the moderator of this session. Today we have an exciting presentation that will be delivering the state-of-the-art technologies in semiconductors. Our distinguished speakers will share their knowledge and insights, research finding, and practical experiences to give us a comprehensive understanding of the subject. Before we begin, I would like to remind everyone to keep their mobile phones on silent mode to ensure a smooth and uninterrupted session. Additionally, we will have a question and answer session at the end of the segment. So, without further ado, let us welcome our speakers. The first speakers that I would like to invite to the stage is Professor Dr. Cheng Xiu Liu. Professor Cheng Xiu Liu is the Dean of College of Electrical Engineering and Computer Science, Taiwan Tech, Taiwan. Please have a seat. Yeah. Right. Now, I would like to invite the second speaker, Dr. Astria Nur Infarsha. He's a senior major of the International Partnership Laboratory, Microelectronics and Embedded System Department of Electrical Engineering, ITS Surabaya. Pak Irfan. One minute. Okay, let us welcome Pak Irfan on the stage. The third speaker will be Professor Dr. Taufik. He's a director of Electric Power Institute, Cal Poly State University, USA. Please. And the last one is Professor Dr. Yu Hong Bin. He's the He's from the Arizona State University, USA. Okay. Thank you, Doctor. Thank you all for coming. Okay, let us start the first session today. It will be in a sequence from Professor Dr. Cheng Xiu Liu and then Dr. Astria Nur Infarsha, and the third is Professor Dr. Taufik, and last one will be Dr. Yu Hong Bin. So everyone will be presenting their insight for about 20 minutes, and then altogether we will have a question and answer session at the end of the session. So please welcome Professor Dr. Cheng Xiu Liu. Yes, on the stage, yes. The slide is, yeah. It's all there, sorry, yes. So let me shortly introduce Professor Dr. Cheng Xiu Liu. Professor Dr. Cheng Xiu Liu is an expert in telecommunications and computer science, specializing in heterogeneous network integration, mobile service, and platform design and distributed computing. So let us please welcome Professor Dr. Cheng Xiu Liu's speech.
Okay, good morning everyone. My name is Cheng Xiu Liu from National Taiwan University of Science and Technology, and I'm also the Dean for the College of Electrical Engineering and Computer Science. And thanks for being here, and also give me the chance to introduce semiconductor manufacturing in Taiwan. And I'm so happy that we can share our experience with you. Next, please. So here is today's outline that I plan to give you some background about semiconductor supply chain and ecosystem. And after that, and I also show some status about semiconductor in Taiwan. Then before I we go into the conclusion, I plan to show you our research capability from our college, especially in College of Electrical Engineering and Computer Science. Please. So let's just start by the semiconductor supply chain and ecosystem. Then, as we may know, Taiwan, particularly through some companies like TSMC or MediaTek, just play a crucial role in semiconductor industry. So we also lead some areas such as foundry services and IC design and the innovation. So based on this concept, we can find semiconductor supply chain just like this figure shows, that in the beginning, the customer will just raise up the specification for the semiconductor requirement. And then they will submit the requirement to the design house just like MediaTek. Then after they just design the ICware, they will submit the design file to the semiconductor foundry. And semiconductor foundry here, the typical example are TSMC and UMC in Taiwan. Then after they just finish the IC manufacturing, they will send the IC to some company for assembly and packaging and testing. Then they will send, after that, the packaged device will be sent to the contract manufacturing company for the final product production. Then the final production will be sent to OEM to bring them to the market. After that, we can just collect some feedback from our customer or end users so that we can just continuously improve the design and also use for developing the future products. So next, please. So this is a typical semiconductor ecosystem. You can find there are so many famous companies inside the triangle, including TSMC, Samsung, IBM, and ASML, tier to the Canvas or synapses. So please, next. So after the semiconductor ecosystem, they can produce some chips or IC to the some application company or system company to make the final products, like our smartphone, and also the like aircraft, and even fighter for the weapon. So next. So in this industry, we can just divide it into several segments. So from the very bottom, this is about the chip design. So in the chip design, they also have another type of company providing the license. We call it IP core company. We can just see ARM is a typical company to provide a license for the design pattern. So that means for the IP, for the IC design house, they don't need to design the IC from scratch. They can just get a license from the company so that they can develop their program on top of the IP core. Then the IC design engineer just use the core to develop the IC, as well as using the electronic design automation tools. So the typical companies for this part are Cadence and the Synapses. And then we also know that wafer is a fundamental unit for producing the chip and IC. So normally the wafer highly rely on the specialized material and the chemical. So the typical company include Applied Materials and also Shinetsu Chemical from Japan. Then the wafer fab equipment company will provide equipment to like foundry in such as TSMC, UMC to physically produce the chips. The typical company is ASML. Then if we just talk about the chip companies, there are normally two types of the chip design company. The first type is fabless chip company. In such kind of company, they don't have their own fab to produce the IC. Instead, they just focus on IC design. The typical company are NVIDIA and the MediaTek. And the second type of the chip company is the integrated device manufacturer, IDM. In such kind of company, they have their own IC design. They also manufacture their IC by their own, and they also sell their IC by themselves. The typical company include Micron for memory or Intel for the circuit. And after the chip were designed by the IC chip companies, the chip foundries just take the responsibility for producing the chips. So the typical companies are TSMC and UMC in Taiwan. Then after they just manufacture the IC ware, we still need to pass one process. We call it assembly, testing, and packaging. And the two typical companies are ASE, SPIL in Taiwan. So I'd like to use the following slides to show the status about semiconductor in Taiwan. So please, next one. So you can just look at this figure. They'll contain a mainstream for 4 processes. The first one is fabless, then mask, and fabrication. The final is packing and testing. So you can also see the process name next to the number, next to the process name, like fabless. We have more than 260 companies in Taiwan focusing on IC design. And we also have some company for fabrication like TSMC and the UMC. So in addition to the core industry trend, we also have some good partners surrounding the whole system. So that include material and also equipment and human resources, also the service support surrounding it. So that can make the whole the industry more committed in Taiwan. So I also allow me to also share you a small story that before I came to Indonesia, some professor from Brazil just visit us. We just talk about the semiconductor production in Taiwan. Actually, he is quite envy the professor in Taiwan. Why he just say that? Because, you know, when they just design the IC ware, they tap out. Do you know how long they need to wait for the real IC? Do you want to try to guess? 50 months? Actually, normally 1 year. Yes, more than 1 year, also more than 1 year. But in Taiwan, with the help from TSRI, normally professor can get the IC 4 to 6 months. 3.5 months, okay. Pocky just helped me a lot, yes. So no wonder around 1 month ago, there were 2 professors from Poland focusing on IC design. They also told to me that they quite envious because they also need to submit their their skeleton for IC design to some agent and then forward the request to TSMC. They also take a lot of time. So they also expect that if they can have a foundry in their country, maybe they can just make the process become more faster. So I think that's because we have a very complete industry in Taiwan, so we can enjoy the research in IC design. So please, next. So this figure just shows the foundry market share by region. So you can see Taiwan in blue. Normally they can just own around 60% to 7% of the total market share. Then if we just talk about the advanced semiconductor manufacturing, I mean for the less than 10 nanosecond fabrication process, TSMC can own more than 60% of the market share. So, and you can also take a look at this table. This table just look at the just provide the top 10 design house in the world. So in Taiwan, we have MediaTek, Novatech, and Realtek. 3 of the top 10s are in Taiwan. So I also like to spend some minutes to introduce the research capability about semiconductor from our college. So I just classify our professors into 7 categories. They are IC design, EDA tools, packaging, testing, and optoelectronic devices and materials, and finally smart application and system integration. So Professor Zhong just focused on IC design. I also want to share the news that actually before Professor Zhong joined NTUST, he has worked for MediaTek for years. So that means he has a lot of practical experience in IC design. Then next is Poki Chen is here. Then his expertise is about analog IC design. As I know, so many Indonesian professors know Poki. And Poki has his nickname is Indonesian Chen, right? Okay, so if you are interested in the analog IC design, during the workshop, you can just contact him in person. Okay, and the next one is Professor Wang focused on circuit design and also interconnections. Next one, please. And Professor Zhang just focused on RFIC design. Next. And Professor Chen just focused on chip design in power systems. Next. Professor Peng focused on IC design also. And Professor Xie focused on AI chips. And next, Professor Fang just focused on EDA tools and design automations. Then next, Professor Chen just focused on EDA tools and design automation. Next. And Professor Liu focused on EDA tools and design automation. And Professor Liu focused on packaging and testing. And Professor Li focused on optoelectronics devices and ICs. Next. And Professor Li focused on optic electronics and photonics devices. And Professor Xu focused on photonic semiconductors. Right now, this topic is very hot in Taiwan because optical semiconductor can not just be used for faster communication for the data center, but also they can just use for the communication between IC, and in the future, maybe we just expect they can just use for transmission inside IC. Okay, next one. And Professor Su focused on LED. And next, Professor Ye just focused on optoelectronics and optical communications. Next one. And Professor Sullivan, actually, he just graduated from our department with his PhD, and then he just continued to join our department to work as a assistant professor. He focused on semiconductor fabrications. Next one. And Professor Huang just focused on the narrow some materials for the fabrications. Next one. And Professor Li focused on materials and photonics ICs. Next one. And Professor Chen focused on intelligent edge computing. And next one. Professor Li focused on the computer vision and FPGA systems. And last one is myself. Actually, I'm a semiconductor guy, but we indeed put some effort in the algorithm study on chip. We also use the AIoT to integrate the IC embedded devices. Okay, so next one. So I just want to use this session to read up some key points for my talk today. Then in the beginning, maybe I just give you some concept about the IC fabrication processes. Then may include three main phases. The first one is IC design, then fabrication, then finally it should be packaging and testing. Then the second, I think based on factual, there we can see Taiwan plays crucial roles in the global semiconductor industry. And finally, I'd like to use the opportunity to introduce the semiconductor research energy from our college. And I truly hope any professor interested in this part, welcome to contact us to further cooperation. So next one. So Finally, I just want to use this slide to show you that I believe most of you know Jason Huang, right? He is the NVIDIA CEO. He just had a talk in Taiwan in Computex this year, this June. He just mentioned that Taiwan is one of the most important countries in the world because Taiwan provides many partners to support his business in NVIDIA. So I will believe Taiwan has not just a complete IC industry ecosystem, but also AI. So that's my talk today. Thank you.
Thank you very much, Professor Liu, for the talk. I know everyone is eager to question Professor Liu, but let us hold until the end session of this talk. Yeah, I would like to invite the second speaker, Dr. Astriano Rifansyah. His background is focusing on microelectronics, both in analog and digital systems, including digitally assisted analog circuits in current and future CMOS processes. So please welcome Dr. Astriano Rifansyah.
Thank you very much, Dr. Ari, for the introduction, and thank you everyone to be here in ITS. As one of the speakers from ITS, I would also take this opportunity to thank everyone to come to this event. I think this is a very rare event where we can meet everyone, like from the academia, industry, government, and students. At the back, I can see a lot of students at the back. Hello. So I will be talking about talent cultivation. My profession is a lecturer. I actually teach. And in a university, apart from teaching, we also do research. And so from the perspective of a university lecturer, I would like to share how we cultivate talent that we think is relevant for the semiconductor industry. Next. I want to highlight important questions for the talk. Why do we actually need to cultivate talents in the semiconductor area? Are there any industry in semiconductors in Indonesia? What do you think? We can't say there isn't, there is, but maybe it's not as much as we would like there is. And maybe the main part of my talk will be how do we cultivate the talent in semiconductors. So what have been done before? What have been done? Is it like something that we haven't done anything yet? So what have been done and what will be done and what should we do? Maybe we can ask ourselves after this event, what can we do? What can you do? What can I do related to this? Because I think there are a lot of opportunities in this event because we can meet together. Next. So a little bit about myself. So I'm a Javanese. I have a long name, but people call me Irfan. My parents call me Irfan. And my educational background, I did my PhD at UNSW. So I took pictures with my PhD supervisors just a few months ago. My thesis was about analog mixed signal circuits. So I looked into the possibility of exploiting digital circuits for analog purpose. I think similar to Professor Pokichan. That's why we have a lot to discuss. And I did my professional engineering in ITS, and I did my Bachelor of Engineering at Gajah Mada University. And when I was still an undergrad student back then, I had the chance to study for 1 semester at NUS, and that's when I first learned to use Cadence in their lab using the Sun Microsystems computers back then. And my role here in ITS, I'm not only a lecturer, but I'm also with the international office. We call it ITS Global Engagement. I handle international partnership. And previously I was with the IEEE Indonesia section as Vice Secretary, and still now I'm with the Industrial Electronic Society. I think the Vice Dean, if she's here, she's also in that Indonesia chapter. And just recently, together with Professor Trio Adiono over here in the front, and our other colleagues in Polytron, Professor Pak Jo, we formed ICDEC, Indonesia Chip Design Collaborative Center. Next. So, thank you, Dean Zhengshu Liu, for explaining the industry ecosystem, so I'll try to simplify in this very plain slide. So in the semiconductor industry, there's the design, there's manufacturing, and then there is the supporting industry, essentially. I personally belong to the design part, but let's not forget that there is also the manufacturing part and also the supporting industry part. And when we talk about talent, which one is it? Which one is it? Of course, when we talk about the roadmap of Indonesia, because we still need to develop the industry, which one do we want to go first? And because design is considered to be less intensive in terms of the cost, then from the Indonesian point of view, we would like to go for the IC design. However, for manufacturing, this is still our aim. And actually in Batam, for example, there is the back-end company, Infineon, for example, they still do packaging there. So there is presence of some of the industry in Indonesia in terms of IC design. Professor Trio can explain a lot about Sirka, for example, in Bandung. So, but there's still a lot to be done. Next. If you go broader, just going out of the Indonesian border, and you can see Batam is just very close to Singapore. You can see Singapore from Batam. There are a lot more jobs there for Indonesian students if who would like to consider semiconductors. If you go wider, yeah, to Malaysia, Philippines, Thailand, even further north, I'm sorry it's not in the picture there, to Taiwan, for example. It's there, right? The industry is there. So I think this is one potential that we should recognize. Although Indonesia may not have the industry right now, but right now there is the industry just very near Indonesia. This is a good opportunity. Next, please. Next. So let's talk about that. This picture we took last year when Professor Poki Chen shared and promoted this field to our students. So that was the picture in Electrical Engineering Department last year. So I will talk about these points. Next. And we do recognize there is a global need of semiconductor skills everywhere. Taiwan, Europe, US. And although Indonesia don't have the industry, but we do have potential talents. So I think that is one of the things that we are targeting. Next. So from the point of view from ITS first, let me explain the vision and mission of ITS. We would like to also contribute in a global scale. However, we have the innovation in ITS, existing ones. We call it Science Techno Park. We focus on 4 key areas. It's the automotive, ICT robotics, design, and maritime. So when we try to develop the semiconductor talents, if you look in ITS itself, we would like to make it in line with the other areas here. Next. So some fast facts about ITS. You are now in a university called ITS. For those who may not know yet, the S is not Surabaya in the ITS. It's Sepuluh Nopember. It's our university name is actually a date. Sepuluh means 10. November is November. So 10th of November is the Heroes Day. So our size in terms of the student body, 27,000 students. We receive 1,780 international students, mostly exchange and short program students. We have 8 faculties and 43 departments. Next slide. And speaking of talents, we must not forget the students. And so we're very proud of our students' achievements in here. So we keep updating this. So this one comes from last year. These are students participating in various international competitions. So this is one way we try to cultivate talent through competitiveness, like challenge that we give to the students. whether they can win, and they do win in many competitions. So for example, the prestigious one is the roboboat competition in Florida. We won 2 times in a row last year, but not this year, unfortunately. And there are many other robotics team. Next. Okay, so in terms of the faculties and departments in ITS, we have 8 faculties, but 4 faculties are related to engineering, as you can see here, and you might be able to identify departments that are related to the semiconductor skills area. Next. And when we talk about semiconductor skills, not all of the skills need to be engineers. They should also be technicians, for example. So in ITS, we have the Faculty of Vocational Studies. So it's a diploma program, but for 4 years. Next. And in terms of research and innovation, we have the Directorate of Research and Community Services. So this building is mainly that. This is the research building right now. We are in that. And in this building, there are 10 research centers, as you can see here in the slide, and also the so-called study centers. It's considered that like a research center, but they focus more on community engagement services. Next. And in addition to the Directorate of Research, in this building there is also the Office of the Director of Innovation in Science Technopark. They deal with research with technology readiness level 6 and above, ready for commercialization. So while I know there are some industry partners here, while you're here, maybe you can speak with the representatives from this directorate who are also here. I can see some now. Next. And some of the products from the Science Technopark, you can see the electric motorbike that has been commercialized and actually transferred to a different company, not ITS anymore. It's called Gesitz, and then there's the automotive, the autonomous car and the robot for COVID. Next. And we were also part of the projects, the tablet. Mr. Ali, I think you're here from Beda Panggung. He's there with our rector, and the bus is also the project from the government, and the electric motorbike. Next. Okay, so we have 2 strategies in ITS. First, about the talent development. The second is the innovation development. So one is teaching, and one is research and towards commercialization. Next. For the teaching part or training. Next. So we have some activities. So not only in electrical engineering, but coming from electrical engineering, I can explain a lot about the courses there. But I believe in engineering physics, the physics department, materials engineering department, they have their own courses, which is in the next slide. The second one, there is the MBKM program. It's this funding from the Ministry of Education. Previously, we had this idea to do this, but now there is ICTech. ICTech is having this one with the Ministry of Education and Polytron. And then some postgraduate programs and internship programs. So we did have some programs with NTUST, and we're trying to establish connections with KU Leuven for a double degree as well. Next. Okay, I think next again. Okay, here are the courses at ITS that are relevant in the semiconductor industry that we think is relevant. So mainly from the electrical engineering is for the circuits, and for device it's the engineering physics, and for the processing of the materials it's chemical engineering and materials engineering. Next. In electrical engineering, because I teach some of these are the mapping between the courses and the competence skills, particularly in IC design. I showed this once to Professor Pokichan, and I know in Taiwan it's much more intensive. This is a very bare bone version that we try to have in Indonesia. Next. I can also share some of the experience that we have in teaching IC design in our class. So we focus more on hands-on project-oriented based learning. So students are given design tasks as groups, and they need to design it, and through the process similar to when we do a real commercial product, through the schematic review, phase and also the layout, and they need to present it in front of the class. Next. Next. And I would like to highlight one very important ingredient, if you may, in our teaching of IC design in ITS is that we use open source tools because it's free. It's free, and luckily since 2020 there was this movement supported by Google at that time to encourage the EDA tools that are open source. So they partner with a foundry in the US, which is Skywater, and they provide the free PDK. Normally, the process design kit or PDK, if you want to design a chip, you need to sign an NDA, and maybe that requires some fees. But in this case, it's all open source, so for teaching purposes, it's very good. In fact, in the early stages, Google also funded free fabrication, and I tried to get a chip taped out, and they did fabricate the chip eventually. So it took, because it's free, can you imagine how many years? Yes. 1 year after, 1 year after tape out, I think. But it came to my door, like I didn't pay anything. But 1 year, yeah, that's correct. And with the open source tools, now there's no more free fabrication, but there is the low-cost version alternative. There is the Tiny Tab Out, and there are some other programs from IEEE, for example. There is the open source Pico challenge, if I'm not mistaken. That one is from the SSCS, and CAS, the Circuit and System Society, just recently opened another program for this free chip design. They do the mentoring. So this is just the breakdown of the course. We use open source tools, and that picture there, I think one of the students at the back, if you can zoom into the clock at the back, that's 3 a.m. Or 2 a.m. in the morning. You know, when you do tape out, you don't sleep. You know, so I didn't sleep either doing tape out with the students. But this experience of our teaching, we presented this in ISCAS, as the flagship IEEE Circuit and System Conference this year at Singapore. That's me presenting our experience. Next. And supporting programs with the partners, this is from last year. We have guest lectures from the industry and from our university partners, Nuvoton, NTUST. Next. And some records of the international partnership that we've been engaging in. Next. I think I'll just go through quickly. Okay, next is about the research side, right? Previously it was teaching, now research, because research also includes talent development in there, because we include students. Next. So this is the chip portfolio that we have in ITS, but mostly are not commercial, so it's just research-based, but then it can be developed further for these potential applications. Myself, I work more on mixed signal design, so it's ADC, DAC, and comparators. Next slide. Next, please. Okay. So in this slide, I list some of the names in ITS who had tape-out chips. So myself, and then Fajar Bunibran is another lecturer who did his master's at NTUSD in Professor Pakichan's lab. And then another lecturer from biomedical engineering. He did have some work with University of Tokyo in the past. And for students, I list their names. Some are at the back there. Radit, Johannes, Gilang. They taped out some PLL, and Gilang, I think, designed the bandgap reference, but still waiting to be tapped out. Next. So this is some pictures from the students. So the focus here is the students. So these are the student designs that I show, and one of the picture on top of there, that's actually from a chip testing session, not in ITS, but at NTUST, but one of our students was there under the TEEP program. So I want to highlight that for now, it's very important for ITS to partner with someone else abroad with the facilities And it's not only for myself, I also spoke to other professors in ITS. That is their strategy to keep things going in this research in semiconductors. Next slide. So going back to how we can apply semiconductor or IC design for ITS alone, we can try to make it in line with the automotive STP and the Sustainable Energy Research Center in this building, and then also the ICT and Robotics STP. So for the energy and the automotive, the overlap is power electronics. So we can try to go for that one. Next.
Another minute, Pak Irfan.
Okay.
Sorry to remind.
1 more minute. Okay. And this is just some roadmap for research. This is so in AI, neuromorphic hardware application, technology for renewable energy, advanced materials. So advanced materials, there's an advanced materials lab in ITS focusing more on graphene. And then there is the roadmap for the collaboration with the industry, audio chip, maybe with Polytron, who knows. And then there is also the LED idea. The picture there, that is one of our research interests, so we would like, and in that RC car, that small mini car, we put an FPGA board. It's a Xilinx one, which is now acquired by AMD. Next. And I think I'll go next again, because it's a bit too much. Next. 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 Okay, so this is the roadmap related to EV. We can go to the electronics part of the EV for semiconductor development. And next. Okay, this is also an important part, so the higher education industry collaboration and from the government. Next. So the main challenges of ICT development is the high cost, the hurdles, the software license. It's generally just high cost, and also the lack of the industry in Indonesia right now. Next. So that is why in Indonesia, us professors in the similar field of IC design, we form the ICDEC, Indonesia Chip Design Collaborative Center. So right now it consists of 15 members. 15 members. You can see the universities. So I'll try to mention the names. USU, Universitas Sumatera Utara, Andalas, and then ITERA in Sumatra, which is the west. And in Java, it's mainly in Java mostly. Prasetya Mulia, UI, Pertamina, ITB, Undip, Telkom, ITS, Gajah Mada, and Brawijaya in Java. And then one in Lombok, Universitas Mataram, and then one in Kalimantan. The rector is here. Thank you, Prof. Pak Agus. The ITK, it's also member, going to be member, and UNHAS. So we form this ICDEC for talent development and easier technology access for the universities, because these universities come from very different background, and some may not have sufficient resources to enter this field. Next. So I took these diagrams from the ICDEC profile. Professor Trio, maybe, who was the one who drew this. Thank you, Professor. So this is the program of ICDEC. So we would like to connect universities, startup companies with these activities. So the national chip, and then master's, PhD program, conferences, incubation, design. And technically, it's PCB also is developed, packaging, and wafer fab. Next, please. So essentially, I think the keyword is we would like to facilitate chip fabrication in Indonesia, because the hurdle is very high. If we don't work together, I think it's almost impossible. That is why we need to work together. And technically, you can see the design flow from the design, technology files, and so on, until you can get a chip fabricated, packaged, and tested. And ICDEC is aiming to facilitate this with our partners, of course. Next. And in terms of training and workshop, right now, the most upcoming program is the training at Polytron. It's going to be funded by the Ministry of Education. 50 students will be given scholarships. They'll be given full scholarships by the government, and Polytron will support the rest. But the trainers will come from us in ICDEC. Next. So in addition, from the government support, we see that this huge effort from the government from last year and continuing to this year. So the coordinating Ministry of Economic Affairs actually launched the task force for semiconductor development, and ICTech is part of that task force. The LPDP provides scholarships for two purposes: for education, master's and PhD in semiconductors. Right now, the target university is German, and then LPTV. Okay, I think that's all.
Yeah.
Thank you so much.
It wasn't me actually.
Yeah, we can continue next. Thank you.
I thought it was me. Okay, thank you very much, Pak Irfan, for giving us a very fruitful insight about the semiconductor technologies and industry in Indonesia and the prospect that it has. Also the role of ITS in this particular area. Next, I would like to invite Professor Dr. Taufik to give a speech. Professor Taufik expertise is in power electronics and power systems. His work focuses on DC-DC converters, utility and renewable energy applications of power electronics, microgrids and rural electrifications. So please welcome Professor Dr. Taufik. Yeah.
Check. Auzubillahiminasyaitonirrajim. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good. Is it still morning?
Still in the morning.
It's morning somewhere. Good morning. Selamat pagi, everybody. It's an honor to be here. Invited to this event. I was kind of surprised when they called me up and asked if I could participate in this event, because as you can see, my background is not really semiconductor. My background is more into power electronics. But then they mentioned that it is actually good to be able to have some insights on this whole ecosystem, if you will, of semiconductor industry from the application side. So that's where I'm going to be speaking of today, more on the application side. As you can tell, I was born and raised here in Indonesia. Unlike Dr. Irfan, who said that he has a long name, my parents decided that I don't need a first name or last name, just a name. But I can tell you from my experience, I migrated to the US in 1989, so I've been there 35 years, is that if you are planning to have a kid, especially the younger people, please give them 3 names. Especially if someday your kid is, decided to go to the US, it makes things so easy if they have more than 1 name. A good example, if I go back, I'm going back in a few days. When I'm going through the custom, this is always what's happening, right? They're going to ask you, what's your first name? I said, Taufik. What's your last name? Taufik. And then I have to explain, of course. But anyhow, I have lots of stories about my name, but today we're not talking about my name. We're going to talk about power electronics. Let's see. I graduated 1993 from NAU, Northern Arizona University, with electrical engineering major, and then computer science as my minor, and then pursued my master's in Chicago, graduated in 95, and then finished my doctoral in 1999, all in electrical engineering. My tie to semiconductor, maybe just a little bit. When I did research for 1 year in Chicago, I actually worked in a microelectronics fabrication lab. So I worked in the clean room for 1 year. But I decided that that was not really my interest. More like because at the time safety was not number one. You know what the professor said the first day to me when I worked for microelectronics fab back then? He said, Taufik, you be careful with this liquid, chemical liquid. I said, why? Because if you inhale it, you'll be blind. And he said, I don't want any blind PhDs. I was like, oh my God. Okay. Anyhow, and then later on, my work experience has been with the application side. Right? I work for companies who make power supplies for many things. Have you ever seen F-35 fighters, in the sky flying? I get 3 babies in there. I design 3 power supplies for that jet fighters. Army, the tank, Abraham tank, I design 2 power supplies for those. And those are high tech, and I have to kill you if I share the design. But anyhow, as you can see, my background is more on the practical side. And I hope you don't mind me standing here instead of there, because I just got here 2 days ago, practically speaking, and I'm still half awake or half asleep, I don't know, whichever one. And I might be falling asleep if I'm standing there. So I decided to just hopefully be able to keep me awake by walking, if you don't mind. Okay. All right. Next. I started teaching at Cal Poly in 1999. And just briefly, Cal Poly, I don't think many people know about Cal Poly. Cal Poly stands for California Polytechnic State University, which is a university, originally was a polytechnic college, but then it converted into university in 1972. But we still carry the main philosophy of learn by doing. So basically lots of labs, hands-on, very hands-on curriculum. Next. Engineering is the biggest college. Just like any regular universities, there's science and there's social sciences, there's business, all kinds of colleges, but engineering happens to be the biggest, and we are known in California to be the biggest, one of the biggest engineering programs. Next. In terms of ranking, in the US, we have this US News World and Ranking system. They categorize 2 different types of universities. Universities that have PhD programs and universities that don't have PhD programs. Cal Poly don't have any doctoral programs, and we are number 5 in the country. Out of 1,900 universities, we are number 5, and so we take pride. We take pride of this accomplishment. Next. Location-wise, you might be familiar with US, but California is way on the west coast, and we are located in the Central Coast, the area called Central Coast. There's North California, and then there's Bay Area, which is Silicon Valley, and then we have the Central Coast, and we have the inland, and then we have the Southern California. So we are strategically placed in Central Coast, right? Very close to the beach. So it's like 15-minute drive from the ocean, Pacific Ocean. Very beautiful place. And next, the reason why I said it's strategic, because as you can see, we are located in between 2 big or huge industrial areas. That's the reason why I'm more on the practical side, especially after I started teaching at Cal Poly. I became more connected to the surrounding industries. But mostly on the north side, which is Silicon Valley. I put those big names because I have quite a few former students working there on those companies. I've been working on some projects with those companies. Consumer electronics, avionics, aerospace, defense, you name it. So those are our strength, which is strong ties to industries. Next. And in addition to that, because this is hosted by ITS, I gotta show this picture. Because myself and ITS, we've been having this wonderful long relationship. And this is a picture of a group from ITS, from this campus, who visited Cal Poly right before COVID. So that's the picture. Next. Okay. So I'm gonna extend the invitation to all of you. If you happen to be visiting California, right, or US, Amen. You should say Amen. Let me try again. If one day you visit United States or California, I mean, oh my gosh, nobody wants to go to the United States. So in case you're going there someday, now that you know me, just give me a buzz. Right? I can give you a 3-hour tour, if you will. All right, next. All right, my talk today, I'm gonna try to be brief because I know I have my colleague here from ASU who's also going to speak. What is power electronics? Perhaps this is something new to you. Briefly go over importance of power electronics, challenges, future directions, and finally I'm going to close it with summary and conclusion. Next. Next. So what is power electronics? Power electronics, there are so many definitions. There's so many textbooks out there that define power electronics, so why not me coming up with another definition, you know, just another definition. But in general, power electronics involves the efficient conversion and control of electric power using semiconductor devices. So as you can see, this field really is related or directly tied to semiconductor devices because we are the users, right? We use semiconductors in order to do what? In order to convert energy from electrical energy from one form to another form in the most efficient manner, right? So that's the basic definition of power electronics. So if I translate these wordings into block diagram, then you can see the three shapes there. So you can see that we have, in power electronics, we have mainly three components: the source, the controllers or the device itself, and then the load, right? And the sources side, how would that be impacting semiconductors? In several ways, at least three that I can think of. The first one is that the sources side uses semiconductors that would drive fabrication equipment in terms of being able to making it low cost, making it energy efficient. Right? So that's the impact on the source side. Also, in terms of the impact to the energy provider, in this case PLN, in Indonesia we have PLN, right? How would that impact the energy provider? And then on the controller side and load side, it impacts a couple of things at least. First one is it drives semiconductor-based products. So you have consumer electronics such as smartphones, tablets, laptops, what have you. And those would be driven by how we actually use those in power electronics. Automotive is the big one today. Another thing is data centers. So if you ask companies in Silicon Valley, one of the focuses that one of the emphasis that they have nowadays is to provide designs for or chip designs for automotive and data centers. Avionics, aerospace, military, those are different. Those are different beasts because the requirement is very different from consumer electronics. Consumer electronics typically cost-driven, whereas aerospace, military, those are reliability, right? You don't want fighters to just go down, right, for no reasons, right? So that's high reliability products. And then on the load side, also affects what we call market segments, right? Different type of applications: logic, memory, analog, power, discrete, and finally micro and opto. Right, next. To give an example, so my bullet right there states that power electronic systems are used extensively in the complex tools used to fabricate semiconductors. So we are not directly the technology that make the chips happen, but we are the technology that support the fabrication of ICs. Right? And here's an example of extreme ultraviolet lithography machine capable of producing more than 200 wafers per hour. And as a power engineer, my interest is actually different. My interest is not on the number of wafers per hour. My interest is on how much power is this thing sucking, right? And as you can see, this equipment consumes lots of power, 500 to 600 kilowatts per unit. This is just one equipment. Imagine if you have multiple equipments, not just this one, but other ones as well. Right? So as a person from the power side, you got to think about many things, such as how do you make it such that the user can save energy, so that way it can lower the cost, because these energy consumptions, they accrue over time. So if you ignore efficiency when you use this, then you're going to pay the price, right, over time. Right? So the same thing with the utility side, provider, energy provider. You have to think about being prepared, to supply this power. Just like electric vehicles, right? Now it's popping up everywhere, right? Almost every campus will have electric vehicles, but it's an ecosystem, right? We need to also take a look at the supporting infrastructure, supporting technologies, right? So it's the same way as electric vehicles. And the challenge there is that power electronics inherently creates noise, because what happens is that we are using switches, right? And just like the light switch, when you go home, what do you do first is you turn on the light, right? So it's going to on, the light's going to turn on and off, right? So you're interrupting power by doing that, right? You turn it on, the light's on, power flows. You turn it off, power stops, right? Power stops. So you're interrupting power flow. That's like the inherent disadvantage of power electronics. Next. So if you look at the single line diagram, the wiring diagram of the equipment that I just showed you, every single subsystem in that equipment is run by, guess what, power electronics. And every single one will make use of semiconductors, which in turn will drive the design, the chip designs. So you can see now the loop is being closed, right? Next. Now, this is a table that shows you that every single semiconductor tool that I can think of would require power electronic system. So on the left column, that's the power electronic systems. On the right columns, those are the semiconductor tools. So every time you see that check mark, that means for that equipment, it would require that power electronic component. You can see that every single column will have a check mark, at least one, right? Or maybe two or three. So that means every single semiconductor tool will have to utilize power electronics. So I hope that I convinced you enough about the importance of power electronics in semiconductor tool. Next. So what is the big deal? The big deal is that, as you can see from this curve, is that the global market for semiconductors is increasing. That means we have to be prepared for, at least from the power side, being able to supply this amount of power that's going to be needed to run this equipment, right? Coupled with the increased popularity of renewable energy, such as solar panels, hydropower, and so on and so forth, right? So that would add to this stress to utility grid, for example, right? Next. How would power electronics create stress? I'm trying to depict this, hopefully, within just 1 minute, right? Electrical system in general would love to see DC to be flat, right? When we talk about DC current, it's flat, right? When we talk about AC current, sine wave, yes? But in power electronics, we interrupt the power flow such that the DC is no longer flat and the sine wave is no longer sine wave, as you can see from the picture, right? That's ideal DC, that's the choppy DC. That's the ideal sine wave, that's the choppy sine wave. So of course, that's going to affect performance of the system. Next, I'm going to go through this real quickly because I know I'm running out of time. Next. So just like in any technology, there's always trade-offs. Next, please. So we have also some trade-offs with power electronics. I won't go through this in detail because I'm running out of time. But as you can see, these are the different issues with the distorted waveforms that if you're not careful, then you're going to have to deal with it later, which is going to be costly. Right? Next. Right here. This is actually a good summary of it. So you have issues on the left side, the different type of issues, and then the impacts that they have. Right. So, okay, next. I know I have 1 minute. So how do we address this? Well, from my point of view, power electronic system in the future should be high density. It means that we should be able to push more power per given volume. 20 years ago, no, not 20 years ago. Yeah, 20 years ago, when we talk about power supply as an example, we were able to push 100 watts per cubic inch. But 10 years later, guess what? 1,000 watts per cubic inch. Imagine in 1 cubic inch, we can push 1,000 watts. Right? So I have more. Unfortunately, I'm running out of time. For engineering programs, consider holistic approach to engineering educations pertaining to power electronics. So one thing that I think is missing from Dr. Ivan's list is power electronics. When he talks about the different courses, and I wish that every single supporting courses, so that our students have the whole understanding of the industry would help, right? Okay, so I think as a conclusion, in order to help establish a complete ecosystem for the nation's semiconductor industry, we need to investigate the potential and business opportunity to develop home-based fabrication equipment. I'm not talking about the big, $100 million, $200 million, but the small ones that from BRIN, the lady from BRIN shows, right? Not even a handful, 9. Now, today, we have more than 100, right? 100 professors in the US from Indonesia. Now, talk about professionals, that's even bigger, right? Professors, yeah, maybe 110, 100 so, but professionals?
IC used for other things. One particular component called a passive component inductor, very hard to integrate, especially for small form factor. But that's leave another day. Yeah. Again, my name is Hongbin Yu from Arizona State University. You can see I have also a second title there. My formal title, director for National Science Foundation Center for Efficient Vehicle and Sustainable Transportation System. But that's actually a very different topic, which involves some automotive, electric vehicle, and autonomous vehicle. But this is not a focus that we're going to talk about today, perhaps tomorrow and later if you're interested. But here, talk about some recent effort in United States, probably all around the world as well, about the chips. I think previous speaker mentioned actually that sustainability is not just only about energy efficiency, lower consumption, but it's about the continuation, be able to manufacture, right, in this case, semiconductors. So therefore, supply chain, right, is about sustainability as well, right, in addition to the energy consumption. So what I'm going to today to do is actually to look at, introduce some of the U.S. CHIPS Acts, and then some effort, especially the last couple of years, and the significant ASU's role and activity in this space, with an intent to introduce ASU's capability among other university, other organizations in the U.S., and seek a collaboration opportunity, which is the spirit of this conference. Next slide, please. So in particular, thanks for the first two speakers. They talk about the semiconductor supply chain. The first speaker, a little more detailed version, and if I'm probably a little simpler version, so I'm going to skip altogether. Thanks for the order. But what I wanted to focus actually more on the challenges, right? The Moore's law, which is about the transistors. It's getting smaller and smaller. I heard of a 2 nanometers Intel 18A, which is almost split atoms, right? Atomic level. So therefore, you cannot do too much on the level, right? And also getting more expensive, right? I think it's just the ASML, the EUV2 itself, $700 million US, right? Just not many companies can afford that. So therefore, if you look at the trend, right, then the system wanted to improve. So therefore, the so-called the trend is the chiplet system, ecosystem, and supported by advanced semiconductor packaging integration, which also showed up in the earlier slides among the supply chains here. So that's some of the focus at Arizona State University and also the U.S. ecosystem on the BRIN, right? And then Dean Liu showed actually the design. U.S. very strong. The top 4 actually from U.S. companies, right? Large market share. But there's no, there's some fab like Intel, but there's no packaging assembly. So the ecosystem is not complete. Next slide, please. So therefore, there are a lot of interest is to bring back U.S. some of this packaging, assembly, and testing capabilities. So I will not go through these slides with time constraint, but just a really brief history about the packaging and assembly there. Next slides. Yeah, so we'll first talk about 5 minutes quickly to go over. I'm not U.S. government, but I think we participate a lot, so that's why we are familiar to some extent this CHIPS Act. So the total dollars is $52.7 billion here. Next slide. And I'd like to give you a little breakdown if you're not familiar. So among these $52.7 billion, there's a big chunk of that actually on the third column there from the Department of Commerce, right? It's about if you look at it down there, $39 billion. And for manufacturing incentives, I will talk a little more. And then another R&D, $11 billion. So on the left side, there's Department of Defense, $2 billion. And today we're going to focus more on the Department of State. There's $500 overall million on this international technology security innovation EC program that the Council General talked about earlier. So which ASU actually participated actually on the red bracket here has significant activity in there. Next slide, please. Yeah, so to break down the CHIPS Act, actually there, like I said, the $39 billion is about incentive. What I will do throughout this presentation, the previous slide, I'm going to show up again, so you know where I was talking about this, our activity related to this CHIPS Act. Next slide, please. So among the $39 billion, right, these are actually up to date. Not all $39 billion been distributed, but I think if you look at the website, look at it last night, about $30+ billion been sort of temporarily, right, kind of assigned. Right. So actually, what I circle here is actually the significant effort in Arizona. So MCOR, which is OSAT, the number 2 OSAT headquartered in Arizona. So have themselves invest $2 billion to build an assembly testing packaging facility, and then also money invested here by the U.S. government, and also the Intel Corporation, $8.5 billion, also has significant presence in Arizona. Next. So the other two actually Microchip, which is also headquartered, is this company also making a lot of automotive chips, right? Not the high-end chips, but actually also very important in many aspects. They're headquartered in Arizona. The bottom, of course, is a TSMC that mentioned earlier. The representative John Chen mentioned, the significant investment, I think $65 billion, along with the announcement of the $6.6 billion from the incentive program. So also in Arizona. So they give you a sense of actually a lot of activity already happening in Arizona. Next slide. Yeah, so that's the incentive part, right? So that's just the Department of Commerce, so handle that. So what I'm going to talk about there also a little bit the R&D, $11 billion, which like a university institution now that can go on a bit. Next slide. Yeah, so this is called a National Advanced Packaging Manufacturing Program. As I mentioned, so U.S. does have some the chip fabrication, Micron in the memory, Intel in the logic. But what's lacking is actually the packaging, right? Especially the advanced packaging. That's why U.S. government sees that's probably opportunity really to promote advanced packaging, right? The research, the R&D to promote that, to bridge the gap. So actually there are some already starting. That's okay. So one of the ongoing bidding program been looked at. Yes, hopefully in a few months some more announcement will come out. So now what I give you the U.S. CHIPS Act. So I wanted to show you what ASU's microelectronic kind of effort, right, and related to this CHIPS Act. Next slide, please. Yeah, the color code is not that clear, but this slide's meant to show, the title shows the Phoenix. It basically is the ground zero for semiconductor US, right? So what this map is actually showing the Phoenix area. I know it's quite busy, not meant to show you all the details, but to give you a sense, a lot of companies, right? From the top, you have TSMC, the new fab, and then the new AMD build also fabulous, but they also now have an office there trying to work with this. And then the bottom, we may not see very clear. Actually, there is Intel and also MCUT, OSAT, yeah, as I mentioned earlier. And then among others as well, right? On semiconductor microchip, the other IBM, they also have office here. So really there's, and also a lot of supply chain companies. For instance, ASML, right? Tokyo Electron and Applied Materials, all this, they have a presence in Arizona. And it's material supply because ecosystem, thanks to Intel and earlier Motorola, right? You probably still remember Motorola probably decades ago. They've started building the fab over there to build up ecosystem, so that the ASU is probably is the opportunity to work with this company. Next slide, please. Yeah, so because this collaboration, all this ecosystem, so the last years, yeah, so some are probably very recent, last year and a half, right? It's a lot of new ASU industry collaboration. For instance, Applied Material announced a $270 million front end that this equipment put at Arizona State University fab, and also with NSP, right? Another chip maker, the legacy of the Motorola, also invests a lot in Arizona. And also, significantly, the packaging-related effort, so ASU with DECA technology, which is used to have a facility in the Philippines, but now they are working with ASU. We're building a 300 millimeter fan-out wafer level packaging. So just to give you a scale, I think if I mentioned, so a lot of universities are just more low TIL 1, 2, 3, but very far from the really industrial scale. So this pilot facility trying to bridge the gap, right, from TRL level 4 to 6. So we can do prototyping and a pilot line, so we can significantly bridge the gap. Next slide, please. Right, just to give you why Arizona State can do that. Again, thanks to Motorola. So actually, what you're seeing here is a satellite view of a facility. Actually, we're building, in the process of building a 300 millimeter fan-out wafer level packaging pilot line. It was built by Motorola in 1998. So now ASU a few years ago started to convert that to a advanced packaging facility. As you can see, they're actually quite large size because we initially are built by industry Motorola. Next slide, please. All right, and again, this is another map showing where that facility is located. It's in the center, in between TSMC building facility and the south Intel, the fab, and their R&D packaging facility. And in the middle, MCOR is going to build the $2 billion ATP facility, packaging facility, to support, to get wafer from TSMC, and then to supply eventually product from Apple, right? So now you can see this will complete a sort of a US ecosystem. So where this lead to ASU? Of course, we definitely wanted to work with the companies. Now we have this packaging pilot line. Next slide, please. Yeah, so that's the facility, and then the other part of the CHIPS Act from Department of Defense, like I said, they also wanted to bridge the gap between research, university research, versus industrial mass manufacturing. So here's the Department of Defense, $2 billion over next 5 years. So ASU actually was selected as one of the 8 hubs, right? They call it Microelectronic Commons Hub. Right, each will develop kind of capability, and Arizona actually state we call it a SWAP hub, Southwest Advanced Prototyping Hub. Significant, actually, the effort is going to be on the heterogeneous integration, which is about the packaging side. Next slide. So because time, I'll probably only show this slide. The prototyping hub is a 5-year, $100 million itself. So the first year, a lot of money will go to tens of millions of dollars will go to buy equipment to establish this fan-out wafer level packaging. And also we're trying to create this ecosystem where big companies, big and small, can work with us using our facilities, work with our faculty. So actually now the number, instead of 70 at the beginning of the year, now it's already swelled to about 160 companies, big and small. Next slide, please. All right. So next few minutes, I'm going to focus more specifically on the very relevant program, about the EC program. Again, this is the International Technology Security and Innovation Fund, right, or EC Fund. So ASU, if you look at the bottom of the column, so ASU received the State Department a $13.8 million grant, which announced February. Actually, the kickoff was at in Asia, so with the ASU president. Yeah. So basically, in this particular effort, at the beginning, it's both assembly, testing, and packaging, right? This capability for partner with this the countries we're going to show you, and to help support the U.S. manufacturing semiconductor companies. Next slide, please. Yeah. So again, this is the show. Yeah. The State Department would kick off, and the next slide is the ASU University President. Next slide, please. Yeah, so that's actually the announcement of the event. Next slide. So the initial stage, actually, this EC program addresses 6 countries. Right, so Indonesia is one of the 6 countries that fit along with Philippines, Vietnam in Asia, and Mexico, Panama, and Costa Rica. So this actually just started probably half a year ago. So we're going to show you the next few slides. What are we doing here? Next slide, please. Right. So this is basically the EC program, the purpose, right, to build a more secure and resilient U.S. semiconductor supply chain, right, to make sure that the sustainable manufacturing. And also trying to work, in particular, both the semiconductor assembly, test, packaging, or ATP capabilities, work with these countries. So 3 kind of pillars, if you will, to increase business environment by expanding ATP facility capability, right? Yeah. At the second one, expand and diversify the workforce that we talked about earlier, Ifan talked about, and to boost ATP talent in partner country. The third one is to improve the regulation environment to promote diversification and growth. So that's why this is actually the goal of this. So that's why we see where we can align with the partner here, to really take advantage of this opportunity, especially maybe now added to the Taiwan delegation research opportunity and this also probably diversified supply chain opportunity, which seems like you're also very much interested in doing here as well. Next slide, please. Yeah, so I will not go to the details. So this is actually what are the technical program in terms of workforce training, right? So the ASU have been thinking about, right? These are already existing courses, right? So additive manufacturing materials, so on and so forth. And also more significantly, semiconductor packaging. So ASU actually, because the presence of Intel only a few miles from ASU campus, so we have very close collaboration with Intel. So for instance, Arizona State University provided the most engineers at Intel. I think the number was 15,000 the last few decades. And also, so because they're so close proximity, Intel actually asked ASU to help establish more than 10 years ago a packaging course, electronic packaging, so they can help train our students, then can be easier transition to become their workforce there. I think the model we're trying to expand that more than anything, right? Because now that domestically there, we expect a lot more going on in the packaging area. So next slide, please. Yeah, so one of the, so there's already existing graduate certificate in semiconductor processing. So now we are trying to get also a certificate program in semiconductor packaging. The next slide, please. So for instance, the now, of course, especially for packaging assembly and test, may not need a graduate student, right? So you may think about some other undergrad or some other level. That's why we are creating this sort of a stackable micro credentials where we pick up, instead of you need a degree, a year, 2 years, or even 4 years college, you can specifically design the material 4 semiconductor packaging, right? Fundamental concept and 10 hours micro batch, right? This and learn some of the fundamental, and then you can stack together, right? Some even we call the upskill or reskill some of some existing workers in some industry can take some of this micro credential course and then become more familiar with packaging and test. Next slide, please. Yeah. So this is actually the program we're trying to put together this. So in particular, through the EC program, so we come up with this. We're already doing this prior to EC program. We call the train the trainer program, meaning because like if you mentioned everywhere, so you originally need a workforce training, right? So for instance, TSMC looking in Arizona, look to Arizona to train workforce, but in the packaging area as well. So how can you train quickly? So ASU come up with a train the trainer. So instead of train all the students, so why don't we say work with faculty, right? With university, say let's train a group of faculty, then they can design courses specific to their needs, to their skill sets, and to their interests. Right? We call this certificate program that enable many universities to participate. Then we can amplify much faster in the process. Next slide, please. Yeah, so I guess this is a sort of a process. Yeah, so applying, accept, and learn, and also we're gonna have this sort of a teaching course. And also, once the lecture finish, then we can have a design, right? Work with the university, see what kind of needs, right? And what material needs, what kind of a new, for instance, packaging testing capabilities need, right? To design new course. So there you can amplify what resource, what course you already have, and quickly expand, and then teach students and get into the ATP area. So that's the sort of idea. Next slide, please. Okay, right. Next slide. Yeah, so these are so represented. Yeah, we have a level 1 and level 2, right? For instance, introduction, the level 1 into semiconductor packaging design, electrical concept, semiconductor packaging, intro to thermal, and then they move to level 2. They can have actually look at 2D packaging and assembly, material selection, and application, and also tests and data analysis. I will not show the level 3 and 4. Actually, the pilot line advanced packaging, we're also putting together resources we can train when needed. Yeah. Next slide, please. So these are some of the faculty, including yours truly, at ASU to do some of the teaching here. Next slide. Given the time, I will not be able to talk about a lot of research, but just give you a highlight. Yeah, like the pilot line mentioned earlier, the 300-meter fan wafer level packaging pilot line we're building. So when it's done, hopefully next year, the first half next year, then we will be able to do a lot of prototyping, work with various partners, where industry, startup, all the way to corporation and universities, and even trying to bring some of the partners to our facility to look at advanced packaging capabilities there. The next slide. I'll probably just go skip next few slides because these are really the research on the packaging, advanced packaging side that the ASU is based on that capability. Next slide. Yeah, these some of the other things designed for manufacturing for modeling. Next. Test. We're going to have really the 300-millimeter wafer level testing as well. Yeah, package. Next slide. And the digital twin concept, right? The co-design and how do you build it from the beginning, understand the process there. Next slide, please. All right. Yeah, of course, this is very important now. Workforce, a lot of needs. This is just a number needed. Next slide. All right. Yeah, so in summary, right, we're building a lot of packaging capability, right, advanced packaging, but through EC program, we're trying to leverage the knowledge we learn, right, the capability we're building, and hope to work with the countries mentioned in the EC program, and see where we can find the pathway move forward. Next slide. Yeah, so the other one actually want to say the sustainable manufacturing. Yeah, as we also received that grant, the decarbonization through electrification process, a $70 million grant. Next slide. I think probably I'll stop here because I did prepare a number of slides from our ICD, our circuit design group, but I don't think I have time. But I definitely want to share with organizers so we can see what are the capabilities so ASU faculty has that we can leverage to and collaborate. Thank you very much.
Thank you very much, Professor Hong Bin Yoon, for giving us the thoughts and insight about the significance of manufacturing incentive and R&D programs. Yeah. Now we are going to enter the question and answer session. We still have approximately 15 minutes to have this session. So I would like to open the first batch of the questions from the audience, please. If you have any questions, just raise your hand and the microphone will be there. Yeah, one, and yeah, maybe another one, please, if you have any. If not, then we can give the chance to the gentleman. Yeah, thank you.
Oh, sorry.
To which person you are asking?
Do you listen to my question?
Yeah, I did not hear the first part. Can you repeat again?
Oh, sorry to waste your time. Anyway, I would like to ask what roles we can play. I mean, from Taiwanese side, Taiwanese companies, Taiwanese universities, what we can do with you, with your packaging and testing project. That is the first question. And the second is, from the six countries you talked about, Malaysia is not there. I'm curious because from the very beginning, I knew that there are quite many American companies, just like NS, Intel, blah, blah, blah. They have already many of the packaging sites in Malaysia, right? So why? I'm ex for Malaysian. Any Malaysian here? Oh, okay. Two very simple questions. Yeah. Thank you.
So thank you for the question. Actually, they're not easy questions. I think especially the second one, because that's probably the State Department probably will answer that question for you, right? But I guess probably because the intent, I just say probably is to promote country that may not have the infrastructure, because Malaysia you mentioned probably already has for decades, right? So industry already there. So hopefully the State Department will help initiate some effort then to promote those and then track industry coming to here. I think that was the intent on that. And the first one, I think, yeah, so definitely, yeah. So I think about the collaboration, that's exactly what we're trying to promote because the facility once we have the facility, Taiwan university companies, global, so that's why we're I mentioned to you probably some other probably the later a few months later probably come back to this region and they probably visit Taiwan and trying to see what other collaboration from the research side, how to collaborate, right? Because we expect, right, because it's so close to TSMC, Intel, so a lot of interest to collaborate and do research in the vicinity of those companies they can then adopt, right, into productions, close to production. Yeah, I think the definite opportunity, and also materials, others. Yeah, so definitely, but the other way around as well. So we are also intended to work with to go to Taiwan and see other collaboration opportunity. So that's why mutual. Yeah.
Thank you so much. Welcome to visit Taiwan.
Yeah. Thank you very much for the question and answer, Professor. The next question, maybe from the audience, we would like to have inquiries to the speakers. Right. Okay. Now I have questions probably for Professor Cheng Xiu Liu and Dr. Astriano Ridwansyah all together. Okay. What do you think? How is the perspectives of manufacturing semiconductors in Indonesia? And then possibly, what is the role of ITS in it? Yeah. So you're discussing more about manufacturing technologies in semiconductors. So what is the prospect in Indonesia? But like maybe we can develop, we can build some fabrics plans for semiconductors in Indonesia. What do you think?
From my personal opinion, actually it's not easy to build a whole ecosystem for semiconductor immediately. However, Taiwan also learned a lot in the past 10 to 20 years. But I believe right now, just like Poki, we have a strong cooperation relationship with ITS. So it's a very important fundamental for build the relationships. So I believe the fostering talents is the first step. So I'm so happy that we already have some fundamental chances to build a relationship, especially between the professor. As I always mention that if we want to build a strong connection or cooperation relationships, professors need to make friends first, then introduce their students to each other's lab, then learn a lot, not just for the talents, but also the culture. Then gradually, I believe we can make it together. Yeah, that's my comments.
Thank you. I agree, and I would second the opinion of the fostering talent is one of the main priority now. If you want to build, before answering that question, how do we build semiconductor manufacturing in Indonesia? But all of us agree that semiconductor technology is critical, right? There's a need from everyone for this technology. We really felt the use during COVID. It's understandable that now all the governments realize how important this is, including the Indonesian government. Because of the lack of the industry here, what can we do? Which is correct. We have to develop the talent, and when we build the talent, then there will be more confidence in building the ecosystem, and it might. I know there are companies here, maybe you can correct me if I'm wrong, it might attract more companies to invest in Indonesia because we will already have the talent. But to build the talent first, that's a tricky challenge because the students, will they choose this field? Because where is the job here in Indonesia? Yeah. That's why we need to work together with our international partners, the US, the Taiwan, Malaysia, Singapore, in this region with close proximity. I think that's one of the best way. And I mentioned this in my presentation that we rely on partnerships to do this talent development. Thank you.
So building a good environment will be the answer for that. I think it's not only from ITS side, but also from the government, perhaps the Ministry of Education and everyone related to it. Okay, thank you for the answers. Perhaps I would ask the audience if you have any questions to ask. Yeah, one more, please. Thank you. The lady on the stage. Yeah.
Good morning, professors. Yeah, I'm Ardila. I graduated from ITS and NTUSC and currently at Taipei Tech. Yeah, so I would like to, it's very interesting that I learned semiconductor from this conference because actually my topic is focused on thermodynamics area. So I have quite interest with the semiconductor field. First questions for the Professor Yu. Yeah, so, and Professor Taufik. I would like to know that what is actually like, how's the challenge of the semiconductor manufacturing and the fabrications in US? So how's the current state currently like in the US, especially in the semiconductor? And the second's like, in the future, perhaps like this question for the all professors, I believe that professors expert on the thermal analysis, like it's curious, like perhaps like in the future we will go where the size is reduced to the maybe 0.5 nanometer. I'm not sure, but perhaps like lower size. So like what's the important factor for the thermal analysis, how to control the semiconductor, especially in the thermal, to stabilize the power or even like to reduce the resistance for the IC. Thank you so much, Professor, for your question.
Right,
thank you for the opportunity.
Yeah.
I'll probably take a quick step here. Yeah. So I guess so the manufacturing probably may not be our role to answer that. I think probably later this afternoon, the next session will be, I think, from Intel, from Micron. They really actually manufacture. Yeah, they probably will share more insight how challenging it is, or moving forward, how they're going to look forward to that. But I mean, in terms of, I can answer the last question there. I skipped very quickly. So the packaging side, you're right. On the transistor side, and also on the packaging side, yeah, when they put the very dense chips and the device together, thermal is a challenge. So that's why one of the 6 topics on packaging is about the power delivery and thermal management. Yeah. So this particular one is actually called on packaging, especially if they like TSMC and just 3D stacking memory stacks and on logic. So tremendous amount of heat generated, and they need to be. So that's why they look for R&D. So to answer your question, whether they have solution or not, no, right? That's why they need R&D, right? I guess, and also for power electronics, they definitely a lot of thermal issues as well.
Yeah, I second the answer there, but if I may add, also in terms of the materials used, that I come from the application side. So what's hot today from the power semiconductor application type will be going into the different wide band gap materials, such as gallium nitride, silicon carbide, and making sure that we can keep pushing the limit, keep pushing the envelope, right? And so packaging is one, and then materials another one, the different type of materials. How can we be able to, as I said earlier, push more wattage into a smaller volume, right? That's packaging, that's thermal analysis, that's material science, right? And so what I forgot to mention is that nowadays you can have like a chip module is about this small right there, about that small, that can push 100 amps, right? If you understand 100 amps, that's a lot of current, right? And how can you push 100 amps into a very tiny area, right? So that's thermal analysis, that's thermal dissipation, right? Packaging as well, and different type of material. So that's my observation in terms of future, direction, in terms of new applications of chips on the power side. Yeah. You want to add?
Yeah, I think that there definitely are U.S. various agencies, the Department of Energy and the DARPA, right, the defense side, the Advanced Research Agency, the program. One of them is called a minimum 3D, which is talk about in the 3D IC how to look at the 3D the heat removal. And in fact, for a lot of power devices, they even talk about material. Now diamond's been talked about how to incorporate diamond because it's very good thermal conductor, right? It help put in close proximity to that devices. There are a lot of research going on. Yeah, definitely area to look into. Yeah.
Okay, thank you for the answers. I hope that answers the question. Okay, we still have one more question, if any. Okay, if not, then I think that will be sufficient for this session, the first session of this conference. I would like to thank to every speakers for this first session, and I hope this very fruitful discussion will be an enlightenment for all of us, especially for me. I think I have a lot of new knowledge, especially my background is not actually in the semiconductors. I'm in computer science, but I can follow the explanation of the speakers quite easily. Yeah. Okay. Thank you all for coming to this first session. Thank you for all, and then let's give a lot of applause for all of us. Thank you, professors. Yeah.
Okay, thank you all speakers and moderator. As an appreciation, we would like to present certificates to the respected speakers and moderators. So please kindly come to the front of the stage. And to present the certificates, we kindly invite Director of Taiwan Indonesia, STIC, Professor J.C. Liu, to hand over the certificate to the speakers and also the moderator. Okay, please give it a big applause. To recall the speakers are Dr. Zheng Xiu Lu, Dean of College of Electrical Engineering and Computer Science, Taiwan Tech; Dr. Astria Nur Irfansyah, Senior Manager International Partnership Program from ITS Indonesia; Dr. Taufik, Director of Electric Power Institute, Cal Poly USA; and also Dr. Yu Hongbin, Arizona State University, USA. And also the moderator, Dr. Ari Siddiqui. Okay, let me please move closer to take a picture together. And let me count it down from 3, 2, 1. Okay, thank you. Please give it a big applause and please be seated. Okay, we will have a break for lunch and praying time. For the VIP guests, we kindly inform to have your lunch at the VIP room, and for all distinguished participants, you can have your lunch at the right side of the auditorium. We would like to inform you too that the musola for praying room is behind this auditorium, specifically next to the men's restroom. Or you can simply ask our committee and they will help you to find it. And please note to return to this auditorium within an hour, because after the break, we will have other presentation. And thank you. See you in an hour.
Cek.
Distinguished guests, ladies and gentlemen, the conference is about to commence shortly in 5 minutes, so please kindly find your comfort seat and return to the Auditorium Research Center ITS campus. Once again, the conference is about to commence shortly in 5 minutes, so please kindly find your comfort seat and return to the Auditorium Research Center ITS campus. Thank you. Distinguished guests, ladies and gentlemen, now we're moving forward to the second plenary session and also collective Q&A. As a reminder, each of the speakers must finish their presentations within 20 minutes and the collective Q&A must be wrapped up within 20 minutes. And now, we would like to invite our moderator, Dr. Ratih Nur Esti Anggraini, to lead the whole session. Please welcome Dr. Ratih Nur Esti Anggraini. The time is yours.
Okay, good afternoon, ladies and gentlemen. My name is Ratih Nur Esti Anggraini. I am from Informatics Department ITS, and this afternoon I'm gonna be your moderator for this second session. And I would like to call our speaker. The first one is Ms. Anna Bawe, the Director for International Government Affairs from Intel Corporation, USA. Please. Okay, and then I would like to call Mr. Han Su, the CTO of Mega Union Corp, Taiwan. And then the third speaker is Dr. Ruri Agung Wahyuwono, the Deputy Department Chair, ITS. Okay, please give a round of applause to our three speakers first before we start our session. Okay, so we can start the speeches now. I would like to remind you that each of you will have 20 minutes to give the talks, and then at the end of the session, for after the three speeches, then we can start the question and answer. For the first one, we will start with Miss Anna Bawe. Please, you can go to the podium. Thank you.
Okay, thank you, Dr. Ratih. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon, everyone. I know this is a very challenging time. The hardest part after a very delicious lunch is to focus on anything else. I'll do my best to make sure that this is as painless as it can be for all of us today. So allow me to first introduce myself. My name is Anna Bawe. I'm the Director of International Government Affairs for Intel Corporation. And I'm responsible for advancing Intel's interests with governments across ASEAN. And I'm so glad to be here today to talk about two of the most critical topics facing our time, semiconductor and sustainability. As you all may know, Intel is one of the few remaining integrated device manufacturers in the semiconductor industry. We design and we build our own products, and moving forward for other companies as well. As an IDM, we need to look at the broad environmental impacts that we have and that we can have. So join me today to explore how Intel's approach to environmental sustainability is integral to our purpose in creating world-changing technology that improve the lives of every person on the planet. Next, please. Okay, so Intel's global manufacturing network is foundational to our operational success as we build a resilient, trusted, and sustainable supply chain for the semiconductor industry to meet the accelerating global demand for semiconductors and also to advance our own IDM 2.0 strategy. We are expanding our manufacturing capacity across the globe from the US to the Europe and Asia. And with our expanding worldwide presence, our responsibilities to reduce the manufacturing carbon footprint continue to grow. Our commitment to being a leader in sustainability remains stronger than ever. Next, please. So this is a broad umbrella that we follow as a company, and you may hear always that's a reference to RISE. And RISE means responsible, inclusive, sustainable, and enabling. These are the 4 pillars that guide Intel's global impact and corporate responsibility goals until 2030. And RISE 2030 is not just a framework, it is our commitment to action. It shapes every aspect of our operations, especially our manufacturing processes. And at Intel, we understand that how we make our products is just as important as the products themselves. This is why our manufacturing is guided by RISE principles. Next, please. So let's drill down a little bit and look at our corporate-wide overall sustainable business practices. There are 3 buckets here, or 3 levels of activity that are going on within Intel today. And the first one is to reduce our environmental footprint. How do we use less water? How do we use less energy and create less waste and recycle that waste? That creates the foundation of everything that we do as a manufacturer. Within our Intel products, sustainability leaders are working on how to make Intel products and platforms and software services more sustainable. That's the second one. And finally, on the last pillar, we collaborate with our customers, suppliers, and also others to enable solutions that meet sustainable goals. So today's presentation, I'll primarily focus on the first bucket to describe what we have done to reduce the environmental footprint of Intel and our commitment to further improving our sustainability in the future. Next, please. So let me share here Intel's key operational sustainability goals and the concrete actions that we take to achieve the goals. Our commitment to sustainability is integrated across the entire operation, covering these 6 main areas. The first one is on greenhouse gas emission. We are committed to reducing our absolute Scope 1 and Scope 2 GHG emissions by 10% by 2030 and reaching net zero by 2040. To achieve this, we are focusing on innovative emissions abatement solution and chemical substitution, optimizing our process and increasing the use of renewable electricity. Then the second one is on air emission. So we adhere strictly to regulatory requirements for air emissions, and this is supported by robust internal air and exhaust treatment systems to ensure we minimize what we can on environmental impact. The third one is on water stewardship, how we aim to conserve 60 billion gallons of water and achieve net positive water use by 2030. So this involves extensive water conservation program and funding external water restoration projects. Then comes on energy management and how we use the renewable electricity. We aim to conserve about 4 billion kilowatt per hour of electricity while we transition to 100% RE by 2030. And we have been making significant strides through energy conservation and RE purchase programs, whether it's through certificates or we look at other programs that the government avail for us at where we are. And the fifth one is on waste management. We aim to recycle over 95% of solid waste and ensure zero waste to landfill by 2030. And our approach includes comprehensive solid waste recycling, waste stream management, and we look into advanced waste treatment systems as well. And finally, it is on chemical management, because as semiconductor manufacturing, we deal with a lot of chemicals. And our goal here is to meet all regulatory requirements through a well-structured chemical inventory and management system. These goals represent our strong commitment to sustainability and our proactive approach to make sure our operations worldwide are not just efficient, but also environmentally responsible. Next, please. Okay, so here is all about how we reduce energy use in our operations, which is core to our overall climate strategy and sustainability goals. So cumulatively, we have conserved approximately about 1.6 billion kilowatt per hour of electricity from the 2020 baseline through the end of last year, and we are on track towards our 4 billion kilowatt per hour 2030 goal. And since 2020, we have invested about $96 million in energy conservation projects in our global operations, resulting in cumulative cost savings of approximately $118 million. And to reduce our Scope 1 and 2 GHG emissions, we purchase RE and operate on-site alternative electricity projects that provide power directly to Intel buildings. And over the last 5 years, our RE supply attribute purchases have totaled more than 37.9 billion kilowatt hour, enough to power more than 3.5 million US households for 1 year. So last year also we continued our RE100 purchase for our US, Europe and Malaysia operations, and we have achieved about 100% RE in Vietnam and China for the first time. We are approaching 100 in Costa Rica, bringing the global total to 99% as of last year. And over the last decade as well, the number of Intel's on-site alternative and RE installation and installed capacity have grown significantly. Okay, next. Okay, this is our journey to net positive water. We believe that by responsibly managing our water use as guided by our own global water policy, we aim to meet our business needs and those of our communities. The strategy has 3 focus areas, which is reduce the water use in our operations through innovative water conservation, reuse water within our operations through investment in state-of-the-art water treatment facilities, and third, restore water to our watersheds in collaboration with local communities. And as part of our RISE goal, we aim to achieve net positive water by conserving 60 billion gallons of water and fund water projects that will restore more fresh water that we consume to our local watersheds. And our water conservation efforts have saved approximately 10.2 billion gallons of water last year, and new projects completed during the year are estimated to save more than 200 million gallons annually once it is operationalized. So since 2020, our water conservation efforts have saved more than 36 billion gallons of water, enough to sustain about 330,000 US homes for 1 year. Okay, next. So when it comes to water stewardship, I'm happy to share that the significant progress we have made in demonstrating Intel's commitment to conserving and restoring water resources. Last year, we achieved net positive water across our sites in the US, India, Costa Rica, and Mexico. This is a major milestone, showing that we're not just reducing our water footprint, but actually we are giving back more water than we consume in these locations. And our conservation efforts over the last 2 decades are substantial. We have invested $1 billion in water conservation projects, and in just past 5 years, we have conserved over 10.2 billion gallons of water, an impressive 162% increase. And since 2020 alone, we have conserved a total of 36 billion gallons of water. And beyond conservation, we are also focused on restoration. In 2023, Intel funded 45 projects that were carried out in partnership with environmental nonprofits, and we aim at restoring watersheds in areas where we operate. And this project restored 3.1 billion gallons of water. Our initiative spanned across various locations, including US, Malaysia, Ireland, Mexico, Vietnam. And we remain committed to sustainable water management, and this has not gone unnoticed. I'm proud to mention that our Ocotillo site has received the Platinum certification by the Alliance for Water Stewardship last year. Next, please. Okay, this one is on circular economy. As a leading tech company, we are also committed to responsible waste management, and we implement circular economy strategies worldwide. And we are focused on improving how we manage waste that comes from our construction and also manufacturing activities, ensuring materials are kept in use longer and reducing our environmental impact. And this component is key to achieve our goals of zero waste to landfill and implementing circular economy strategies. I think in semiconductor manufacturing, some of the major waste streams we manage includes like lithography-related solvents, metal plating waste, there are specialty-based cleaners and many more. And beyond that, our operations also generate various types of waste, like including plastic, metal, kitchen and general office waste too. So last year we made significant progress on that with our waste management efforts. Around 63% of our manufacturing waste was upcycled. That means it was recycled, reused, or recovered. And manufacturing waste, on the other hand, which includes both hazardous and also non-hazardous waste from wafer production, represent about 41% of our total waste in 2023. So for our circular economy solution strategy, we define it according to Ellen MacArthur Foundation, where we upcycle waste and focus more on keeping the product and materials in use via reuse, resale, repurpose, and recycle. And this includes recovering and also restoring products, components, and materials through strategies like reuse, repair, remanufacturing, use as feedstock, and also recycling. So through these efforts, we are not just managing waste, I think we are transforming how we think about waste. Next. So that is from our manufacturing part, where I look into the first pillar of reducing our carbon footprint. Now let's go into the handprint, where we make our own products. So our commitment to sustainability also extends beyond our operation. It is deeply embedded in our product design and platforms. And we aim for a 10x increase in product energy efficiency by 2030 for both our client and also server microprocessors. We are leading the way in sustainable AI. We are offering a full range of products that make AI more sustainable with innovations in both hardware and software. And this includes industry enablement using AI to drive broader sustainability outcomes. And finally, our approach to innovation in design focuses on materials, the layout, component selection, and also modularity. So by rethinking all these elements, we are increasing reuse and significantly reducing the carbon footprint of our products. Next. Okay. And as part of Intel's ongoing commitment to environmental sustainability, I'm going to the third pillar of our goals. We are also deeply engaged with our supply chain to make a meaningful impact. We are committed to lowering supply chain risk and also decrease cost. So here we are actively collaborating with our suppliers on how to reduce greenhouse gas emissions, water usage, and waste. And this also includes implementing the circular and economy strategies where resources are reused and recycled as much as possible. And our procurement team are working closely also with the logistics and packaging suppliers to rethink the materials we use for shipping products, pushing for more sustainable options. And in addition, we also work closely with our first-tier chemical and gas suppliers on green chemistry initiative. This means we are focusing on safer, more sustainable chemicals that have less impact on the environment. So last year, we reviewed our goals and we set an ambitious new target to achieve net zero upstream scope 3 GHG emissions by 2050. So we no longer have just scope 1 and scope 2, we add in also how we can contribute to scope 3 reduction of GHG emissions. But we are not stopping there. We have also set an interim goal to reduce supply chain GHG emissions by 30% by 2030 compared to what they would be without our current investment and actions. So to reach these goals, we are identifying areas of synergy and collaboration across our supply chain to accelerate these reductions. For instance, last year we asked about 130 of our first-tier suppliers, those with higher environmental impacts, to submit data on their carbon footprints through the CDP Climate Change Questionnaire. So the response was overwhelming. I think we received 99% of those suppliers actually submitted the questionnaire back to us, and around 97% of them made their responses public. So this transparency provides Intel and other stakeholders with crucial insights into the environmental performance of our supply chain. So next. Okay, I think this is my last slide. So to conclude, a sustainable future for Intel requires deep commitment to achieve our own goals of net positive water by 2030, our zero waste to landfill by the same year too, and net zero greenhouse gas emissions by 2040. And thus, we keep on continuing to invest and also innovate on how we manufacture, how we design and develop our products, and how we collaborate with our own supply chain ecosystem partners to deliver products, platforms, and services that are environmentally sustainable and also responsible. I think for more information, I invite you to explore those links on the slide to get more information of what we do in this space. Thank you very much.
Thank you, Ms. Anna Bawe, for your speech on environmental, social, and governance of semiconductor manufacturing. It's very insightful. Next, we will listen to the speech from Mr. Hansu, the CTO of Mega Union Corp, in practices of circular economy of semiconductor manufacturing.
Good afternoon, everyone. Okay, and thank you for opportunity to speak to you today. And allow me to introduce myself. My name is Hans from Mega Union. And I'd like to talk about the presentation is the practice of a circular economy of the semiconductor. Next. This is an outline I have introduced the three parts about, let me the page to introduce my Mega Union. Then, the water recycling in the semiconductor is very important in Taiwan or anywhere. Then the water usage trends and the type of the process, the wastewater and the trend in stream separation. And how to get more water in semiconductor. I have shared the example is the 3-stage and the case study, including recurring system and how to get more mineral extraction from wastewater. And finally, I give you the conclusion. Next page. Okay, next. This logo is a Mega Union's logo. We provide a total solution, including the water solution from irrigation. And when rain to the storage, we provide ultra pure water in the fab or in the semiconductor. Because ultra pure water is very important, the quality of the chips. If the ultra pure water is not well, maybe the chips, the defect is maybe the damage and a big problem. Then we several the recurrent system or wastewater in the semiconductor, how to get more water in the semiconductor. And finally, our business model is supply the chemical into the wastewater. Okay, next slide. So this service in Taiwan, we headquarters is in Taoyuan, and research and development and study in Taoyuan. because in order to provide a faster service, so office is in Taoyuan, Hsinchu, Taichung, and Tainan. So in order to faster service, so we have the storage center in Taoyuan, Hsinchu, Taichung, and Tainan. And 2017, we locate in China and Shanghai. And in 2018, because of the Vanguard or UMC or SSMC, the client, so we set up the office in Singapore. And in this year, we set up the office in Arizona, USA. Okay, next. So it's a total water solution. In the past, we provide a total water solution for clients, such as we provide a construction UPW system or seawater distillation and the reclaim system. And we provide a system operation 24 hours. And we have another service including reserve the osmin, the membrane, reclaim, or racing crane and spare parts and another service. But now we provide a total green solution. How to say example? If your RO membrane is 1 year per time, the lifetime. But we take the RO membrane from the client to our factory to clean more and clean. You can use the 2 years or 3 years per time, so you will increase the lifetime in the client. This is a good energy save, waste reduce, and resource management. Next. So the next two parts is the waste, the recycling in the semiconductor. Okay, next. So this is 24 to 2021. Taiwan, the semi-process evolved in then 19 nanometer to the 3 nanometer. And we provide the 40 phase from the 90 phase, the 12 phase forward to phase 18 for 4. So this is we provide a wastewater treatment and also water treatment and construction. Then when technology evolves and the technology will speed and the faster, and how to save the water. Okay, next. So you can see this one, the water consumption per unit increasing significantly into the capacity in the water. So you can see this one, the the first is the layer, is the increase the water, the consumption per wafer layer is non-linearly. So the water consumption is very bigger and bigger. So when you will the save the water, the next page will show how to do. Next. So you can see the purpose of the wastewater diversion to achieve the most efficient the treatment. So you can see this figure. We will diversion different equipment and diversion low concentration and high concentration. And if you wastewater contain the fluoride, the ions, we will diversion another piping. So if you go to the semiconductor in Taiwan, you can see a lot of piping is above the type. Yes. Next. This page. Okay, so this is short in the past, the 1998, just will 4 or 5 the total classification. But now we increasing the water recycling or increasing the chemical reclaim. So you can see the wastewater classification increased to the 20, and the waste chemical increased to 16. So this is the reason why, if you want to get more water reclaim and get more the chemical to reclaim, you have to diversion a lot of piping from the quality or collapse. Next. So this patch is the total solution from the diversion of the piping and the recycling and the wastewater treatment. And you will get more the mineral from the wastewater. Okay, I was sure you can tap water and provide to equipment to use. Then the treatment to the liquid the clarification, we will depart for depending the water content from line or S and organic wastewater. And the metal content of wastewater and a high concentration of water liquid. So we will 38 the different liquid clarificates. Then the recycle system, maybe the local scrubber or HF system. Then finally, we will get more the product recycle the metal such as ammonia sulfate or TMH or IPA or sulfuric acid. You can recycle to the semiconductor. Okay, next. So we provide in the past we just to improvement standard better than the law, but to such is recycle rate have to higher than the 87%, and total solution is a waste recycle. Finally, we get more environment, the little impact in the future is our goal. Next. So you can see this one in the past. We just want the low, so the fast, the wastewater treatment, just the 4 units per phase, including the S-based, the wastewater or HF-based water. But including in order to get more water, so you will advance the recycle system, such as the ACF UF or the RO membrane UF or biotreatment. But you will get more recycle, waste recycle. So you will provide a membrane degas or vapor crystallization in the system. So this is the reason why this is 22 units per phase the semiconductor. Next. So there is some case study for the semiconductor. Because the local scrubber equipment in the semiconductor consumes a lot of water, so you have to recycle the water to the local scrubber, but it contains some of ammonia or fluorine iron. How to do? We go through to the RO membrane to concentrate. Then you have to use the membrane degas MD to get more ammonia sulfate, about 30%. And you can see our permeate. You can reclaim to the local scrubber system the equipment, so you can decrease a lot of the water consumption in the semiconductor. Okay, next. Okay, the last page is mineral extraction from the wastewater. Next. Okay, this is a total solution for waste. So we will determine the two difference, the concentration, the low concentration and the process waste for liquid high concentration. The high concentration will to recycle the process in the fab and product maybe the creatine or copper or cobalt, the load and ammonia sulfate. But if the waste liquid is a low concentration, we will to be the concentrate. Then to go through to the initial process to concentrate. And final, in the future, we want to get more regeneration plants in outside and recycle to the semiconductor to reuse. This is very important, and in the future, our goal. Next. So this case study is waste the sulfuric acid to recycle to the industrial recycle. Because of the waste sulfuric acid in the semiconductor is very large the chemical. But how to reuse? We use the HCl to react with the sulfuric acid, and you can see the total reaction is the H2O2 decomposition to the water and the oxygen. So you can see this picture. we can reuse to the wastewater or acid-based or resin regeneration and reaction with the ammonia. Okay, next. So you can see this the picture. We combine ammonia, the wastewater, and the waste sulfuric acid to the ammonia sulfate. So we use the membrane degas to the 30% ammonia the sulfate and the crystalline laser to the 99% to ammonia sulfate. So this product you can reuse to the agriculture or another way. Next. Finally, we provide two method to recycle. One is copper sulfate to recycle. So when the low concentration, maybe less than 300 milligram per liter, have to concentrate to the 5%. Then we go to the electrode, the method to the copper, and the copper, the loads. Okay, next. This is a cobalt. Yes, the cobalt is the same process by the resin and the electrode painting to the remove and the recovery in the semiconductor. Okay, next. Okay, this is the conclusion for the mega unit or the clients. So in response to the United Nations adoption of the 2013 regarding the sustainable development, we have the 3 points. Is the 6, 12, and 14. Increasing the water use efficient to ensure sustainable and supply and recycle. And the signification reduction of waste regeneration through reduction, recycle, and reuse. So this is the reason why when the process design, you have to diversion a lot of the piping and how to the diversion. And finally, reducing the chemical discharge into the water body by the 50% is important in the future. So this is our today's speech. Thank you, everybody. Thank you.
Thank you, Mr. Hansu, for the speech. Now, without further ado, we will continue with the third and our last speaker, Dr. Ruri Agung Wahyuwono, regarding the metal oxide semiconductor.
All right. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, ladies and gentlemen. It's also a great honor for me to talk here, presenting our recent research about semiconductor development, particularly that our previous two speakers talking about the wastewater management and also about the water recycle and so on. And now I'm going to talk about the metal oxide semiconductors applications, particularly for photoelectrochemical solar energy conversion system. So I'm Ruri Wahyuwono, Deputy Chair or Deputy Head of Department from Engineering Physics, ITS Surabaya. Okay, next. All right, so what I'm going to talk is what is the urgency to talk about photoelectrochemical energy devices using metal oxide semiconductors, and sort about the methodology that we have developed so far, and some results regarding oxide semiconductor development in our research, and summary and outlook how, in the end, I will summarize my talk with is there any possibility that we use a solar energy conversion device to do both for environmental application and also for energy conversion devices. Next. So yeah, as we already know that we have solar energy potentials up to around 100,000 terawatt, which can actually fuel the whole world energy demands. Therefore, a lot of solar energy conversion technology is emerging up to now. And one of them, if we look at the, for example, solar energy chart there, we can see one of the promising solar cells technology is a dye-sensitized solar cells. Of course, if we talk about semiconductors, sometimes we already directly discuss things about microelectronics and things. But here, oxide semiconductor or semiconductor itself could also be used for another application. And for dye-sensitized solar cell itself, it is considered the third generation solar cells that is low cost and simple for fabrication, and also has a high performance under diffuse irradiations, also high stability under high thermal working temperature. And further, if we could build a tandem dye-sensitized solar cells combining N-type and P-type semiconductor, we could possibly break the Shockley-Queisser limit. But unfortunately, up to now, we have limitations on the P-type solar cells that hinders the higher conversion efficiency. So let's now understand how this photoelectrochemical device work. Next, there will be an animation here. All right. So the first is a photoexcitation. Once the solar cell or the photoelectrochemical cell is irradiated by the sun, so there is charge excitations that leads to the formations of charge separated states. And this charge separated states is crucial for having high performance or high efficiency of photoelectrochemical devices. And once it is excited, it is followed by charge injection and then dye regeneration and redox mediator. But we have to note that here there are some limitations about the recombination reactions that typically researchers in semiconductor manufacturing or semiconductor materials already understand that recombination reaction is not beneficial for the devising. And hence, here in understanding charge injection and also recombination in the photoelectrochemical device is substantial to guide the semiconductor development and also the device enhancement. Next, oops, there should be one back. No. Back to the previous slide. Yeah, back to the previous slide. Is there the rule, okay, next. So what we have to note here, next, that this charge transfer process occurs in femtosecond time scale. Imagine, 10 to power minus 15 second. And it spans from femtosecond to microsecond time scale until millisecond time scale. So in these photoelectrochemical devices, we have at least 4 components here. The semiconductor as the working electrode materials, the dye sensitizer as the light harvesting unit, the redox mediators, and also the counter electrodes. And here we are talking about the semiconductor optimization and also the dye design. Next. So yeah, for semiconductor materials, we already perhaps know that typically we need to have a high specific surface area of semiconductors to allow more dye sensitizations of the device and a high dye loading, and then it should have a low defect concentrations to limit the recombination reactions within the semiconductor and also appropriate redox properties. Next. And for the dye design, we focus on a P-type dye-sensitized solar cells. Why P-type dye-sensitized solar cell or P-type photoelectrochemical cells? Because P-type, it is now developed for the development of photoelectrochemical devices for hydrogen generation. So we are able to generate photocatalytic hydrogen generation for such photoelectrochemical device, as well as the development of solar cell itself. So the design of the dye for this device, it should be has a electron density for for charge-weighted states away from the core of semiconductor to allow efficient charge injection. So that's why we developed there some ruthenium sensitizer that is typically has a broad absorption spectra. Okay, next. So yeah, in this talk, I'm focusing on the structure, properties, and performance. I'm sorry that it's a bit technical for you perhaps, but I think it is important to understand the structures of materials, because if we want to develop a company to fabricate semiconductors, so we need to know what we have to fabricate, we have to synthesize, especially the oxide semiconductors here. And later I'm discussing how if we use ligand modifications of the die and also external stimuli to enhance the performance of the photoelectrochemical device. Okay, next. Next. So here we produce nickel oxide from different nickel source, use wet chemical method. Of course, this is not sophisticated fabrication technology, but it works. And do some characterizations for materials, and also use a different dye sensitizer developed from our cooperation partner from University in Germany. Next. And yeah, as mentioned earlier in the talk, that our process occurs in a femtosecond time scales until microsecond time scales. So how do we probe such process in the photoelectrochemical device? We use this transient absorption spectroscopy using pump probe spectroscopy. There will be excited state absorption with positive signals, ground state absorption, and stimulated emissions. And next. And yeah, to probe the slow process, we will use electrochemical impedance spectroscopy that is typically used for also electrochemical device characterizations. Okay. Yeah. For the first result, yeah, I hope you can follow the material sections here. So in the first section here, we develop nickel oxide photocathodes. So this is semiconductor P-type, but we develop these nickel oxide photocathodes from different nickel hydroxide precursors. So next. Yeah. So typically nickel oxide is synthesized through oxidations of nickel hydroxide, which is polymorph of some alpha, beta, and gamma. And we normally use alpha and beta nickel hydroxide, which has a different characteristics of its crystal structure. And why we do care about this preforming nickel oxide? Because it is eventually affects the performance of nickel oxide. So we prepare nickel oxide nanostars there, nanoparticles, and also nanoflakes. Next. So here we built 3 different photoelectrochemical cells using 3 different materials, and now we have significant difference performance. And now it raises questions why the nanostars has high efficiency. Next. Yeah. It turns out that the nickel oxide nanostars that we have synthesized, it's preformed from beta nickel hydroxide, from the TEM, from the Raman spectrum, from the thermogravimetric analysis. And if we compare next with the other structure, from the crystal structure perspective, we see that different nanostructures has led to different electronic density distributions, that this will eventually affect the performance of the photoelectrochemical device. Next. Yeah. And now, from oxide semiconductor perspective, typically we always say that high surface area of the materials will have a high performance of photocatalytic devices. But in this work, we prove it wrong. Higher surface area of oxide semiconductors materials doesn't always give higher performance. But we highlight our finding here that the important thing is that the surface characteristic, the electronic characteristic on the nickel oxide surface controls the device performance. And this is further confirmed when we build our solar cells. In next slide. Okay, that's a bit too technical, but the result says that even though the nickel oxide semiconductor has a lower surface area than the other nickel oxide structure, but looking at the electronic density on the surface, that is beneficial for binding with the dye sensitizer for the photoelectrochemical device, and this led to high performance of dye sensitized solar cells. Next. Yeah. Now I come to the second part of my talk, that now if we know how to design the electrode materials, how if now we design the dye materials for these photoelectrochemical devices. So now we are talking about the excited state of charge separated states in ruthenium DPPZ complex with nickel oxide. Next. Okay, so as mentioned earlier, that the charge separated state is essential for the device performance. So our goals is actually to extend the lifetime of the charge separated states so that it doesn't recombine and limit the current generation in the solar cells particularly. So we examine some dyes, ruthenium complex with extended ligands. We put vanillin and also triazole there to extend the ligand so that we expect that the electronic state is away from semiconductor, and then it allows more efficient charge injection. So in principle, we do this strategy, and then we see from the fluorescence time resolved emission spectra that there is a quench on the emission, indicating that, okay, charge injection occurs. But if the charge injection occurs, is it efficient or not? Next. We try to look at the electronic nature of the dye, but unfortunately when we put linkers there, the conjugated linkers, to put away the electronic, the charge density state or the charge separated states away from nickel oxide, but it turns out that the result shift in close to nickel oxide, which is unfavorable for this device. Next. Okay, next. I think we can skip this part. Yeah. So in principle, our results conclude that the extensions of the dye on the semiconductor surface, it should also take care of the electronic nature of the dyes. So if the electronic density of the excited states is pushed away toward the nickel oxide semiconductors, then it will not produce a high performance of the photoelectrochemical device. That's why in this research actually we find things that if we extend the ligand that attach to the semiconductor surface, then it gates the whole injection or the charge injection. So we have to take care of this dye design when we develop this component for photoelectrochemical device. And last, in our result is how to make these charge separated states stable. So we already talked about the semiconductor and then the dye sensitizer as light harvesting unit, and then could we do it from external stimuli? So we are trying to give electric field outside of a photoelectrochemical device. So in the third part of my talk, it's bias dependent charge separated states in ruthenium, platinum co-catalyst, and nickel oxide surface. Next. So yeah, here I'm just going to note that we probe the charge separated states in two ways. So there is the B-pyridine ligands and also TPPHC ligands. So there are two ligands that responsible for the charge separated states, And we see at the delta OD signals there in the highlighted chart that if we have a smaller delta OD, that means the charge separated state is stable. Higher delta OD means destabilized charge separated states. And we look there for TPPHZ ligand under positive bias, so everything declines, it's fine. But then how about negative applied bias? Why one is becoming higher, one's becoming lower? So next. The results indicates that from the kinetic analysis, we see at the negative bias, all charge separated state signals is decaying. But for the PP ligand, up to 100 that's picosecond. So the signals from TPPHZ ligands builds up. So that means there is interligand charge function. So there is charge separated state that is pushed away to another ligands because of the electric field applied from the photoelectrochemical device. Is this good for the device? Yes, it helps to improve the performance of the photoelectrochemical cells. So, in summary, next. So, I want to note that the oxide semiconductor can be used for photoelectrochemical device to some extent, not only for solar energy conversion device, but it's also could be for environmental application. For example, we have developed a lot of photocatalytic system for wastewater treatment. For example, I do not put this research result here. There are several wastewater treatment technology that already mentioned earlier by Mr. Hans, for example, reverse osmosis, UV, active carbon, and so on. But in this case, if we want to develop a semiconductor device, particularly based on nickel oxide, so the preforming nickel oxide is important. One, the die design is also should consider the electronic nature of the dies, and the bias-dependent experiments could be extended to upscale photoelectrochemical device. And as an outlook, next is metal oxide semiconductor-based photocatalysis could enable simultaneous hydrogen generation and organic pollutant degradation. And this, if this is scaled up to industrial level, so how to realize this scheme? So we propose already a decoupled cell. Next. This decoupled cells is to separate the photocatalytic devices for pollutant degradations and also electrocatalysis for hydrogen generation. So in this scheme, so we can use this technology for wastewater treatment, not only for degradations of the pollutants, but we could also generate new energy in forms of hydrogen. I think that's all from my perspective. We can go to the end of the slide, the acknowledgement. Yeah, so, yeah, the last. Okay, I would like to thank the DAAD for giving scholarship during my PhD study in Germany, and also Thüringer Aufbaubank, and also DFG for funding the research on photocatalysis, wastewater treatment, and also photocatalytic for hydrogen generation. So yeah, that's all my talk for this afternoon. Thank you very much, and I giving back to moderator.
Thank you, Dr. Ruri Agung Wahyuwono, on the speech regarding the application of photoelectrochemical solar energy conversion system. So those are 3 speeches from 3 wonderful speakers. Now we will move on to the question and answer session. So if any of you have any question, please raise your hand. We have time, I think, for 3 questions from all of you. Anyone want to ask to our wonderful speakers here? Yeah, there are 2 over there.
Check. Okay. Thank you very much for the wonderful speech from every one of you. Okay, I would like to ask, because Dr. Anna and also Mr. Su and all the speakers already mentioned about the circular economy of the water in the semiconductor or high technology production. But I'm curious about how can you see the potential of the electronic waste to support the circular economy? For example, maybe to collect the materials to recover the materials from the electronic waste itself. Maybe for Intel and also from Mega Union. Okay, that's my question. Thank you very much.
We can have one more question from, yeah.
Thank you very much for the question. For my question is, I do like to ask to Mr. Ruri about microcity, especially about the material for metal oxide semiconductor. First, the question is why nickel oxide? There is like other material like copper oxide, zinc oxide, or titanium oxide. Why you choose nickel oxide for the topic? Yeah, that's all. Thank you.
Okay, I think we can answer the first two questions first. The first one is to Miss Anna Bawe and Mr. Hansu regarding the potential of waste in our economy, because it is very important for all of us. Yo, please.
This is a good question about electro waste in semiconductor. In my opinion, we find a lot of the waste in semiconductor recycle, or maybe in the waste liquid recycle the opportunity. So if you want to get more value about the semiconductor from the waste, you can get a lot of the process, maybe the evaporation or crystallization for this one. And in our waste liquid, we get more the high value the metal, high value the chemical, the material, maybe recycle to the semiconductor, the low material. This is in the future is real. Yes, that's all. I hope you answer your question, but if I can detail in answer you, you can email to me. I can send the answer to you. Thank you.
Thank you for the question on electronic waste. I think like in Intel, as you look at it, we do employ circular economy strategies across our operations, and that means that we try first, rather than we throw or go for recycle, we go for repair first or remanufacturing it, and that's why like a lot of machines actually in Intel, they are like 30 years old, 20 years old, but they look new because we always go for innovation first on how we can, still use the same technology and upgrade it rather than like throwing it. And when it comes to our own product, that's why we strive as well to look at how we can look at material and design it in a modular way where we only throw or recycle something, the part that cannot be used anymore, and just replace that part only rather than the whole computer, the whole thing. And then at the same time, we run programs with community. I mean, especially at places where we have sites where we create more awareness on recycling and on e-waste, where we have like a pickup collection programs. And then we work together with the authorities. I mean, I can give an example. In Malaysia, we work together with the regulators like the Malaysian Communication and Multimedia Commission, where they run and collect e-waste, or together with the Department of Environment. I mean, those are the things that we can do to address electronic waste that are currently, like, I think, rampant out in the market as well. I hope I answer your question.
Thank you for the answer from both of you. Hopefully that answer your question. Okay, we will continue with the second question to Dr. Uri regarding the choice of the material.
Okay, good. It's good questions. Why I use nickel oxide instead of copper oxide, for example, for the same P-type semiconductor, or zinc oxide or titanium dioxide that is typically used for N-type semiconductor materials for photocatalytic activity, for examples. Actually, it's simply because nickel oxide has a simple structure. So if we, again, in terms of materials, nickel oxide has a cubic structure. So it's very simple materials that we want to understand the correlations between the structure, performance, and relationship of materials. So if we modified nickel oxide, or if we engineered nickel oxide and see how the engineered structures of nickel oxide, which has a simple structure as a electrode materials or semiconductor materials for photoelectrochemical device, and we see the correlation between its properties, structure, and performance, then we can do the same to another complex structure. So the reason why we choose nickel oxide is simply because it has a simple structure to modify. I hope it already answered the question.
Thank you for the informative answer. Does that answer your question? Okay. Okay, thank you, Dr. Uri. Now we can continue with the second question and answer session. Do you still have any question to our three speakers here? Anyone? Okay. I want to ask the three of you then, while we are waiting on the question from the participant. What do you think the future of, well, I know you might not very familiar with Indonesia, two of you, because you are not from Indonesia, but what do you think regarding the research or the manufacturing possibility future for Indonesia itself? Do you have any suggestion or maybe any insight regarding this potential in our country? Dr. Uri, maybe you can start first for Indonesia.
Okay, thanks, Dr. Ate, for the questions. These actually intriguing questions to ask. How to look at the future of, for example, semiconductor manufacturing in Indonesia. I think, well, we know that semiconductor technology in, for example, Taiwan is best, I think, one of the best in the world. For example, TSMC is in Taiwan based, and so on. And to come to this level, I think it's a long way, it's a long journey. But the first step to be developed in Indonesia, I think it starts with simple semiconductor manufacturing for other applications. For example, for sensor developments, for instrument development based on semiconductor technology manufacturing, it is still possible in Indonesia. And research facilities, particularly for semiconductor research, I think it needs to be instantly upgraded. I think we need a lot of support to build advanced semiconductor research development in Indonesia. I think only few of university that only have, for example, a clean room for the development of semiconductor technology. Yeah, I think that's our homework. Yeah, thank you.
Mr. Yes, Mr. Hans, do you have?
Okay. In my opinions, and yes, I see Indonesia is in the future for semiconductor because maybe the labor and we need many humans research and in the semiconductor. So like in Taiwan, we are strong for labor in the semiconductor. So this is the reason why in the future maybe Indonesia in the semiconductor have to the development and the potential this way. Okay.
Yeah, we have the human factors. Yes, that is very good. Thank you. Miss Anna?
Okay, I think Indonesia has the potential to carve out a role in the semiconductor value chain. But I think as one of the earlier speakers has said, you need to focus on talent development. But the way I see now, a lot of the talent development program that are being done is catering to the professionals. How about the skilled talent on the TVET aspect? Because if you want to have a manufacturing, you need to look at skilled workforce as well, and not just at engineers and above. So I think the government need to look at the whole, when the government is like charting out policy and roadmap for the semiconductor, in it to look at the depth and breadth of the whole semiconductor value chain and try to find the sweetest spot for Indonesia. It's going to be a $1 trillion market by 2030. I think we in ASEAN, I mean, if we collaborate together, rather than competing with each other, we can definitely have a huge share of a pie in this $1 trillion industry.
Thank you so much for your answer. Very insightful. Okay, before I close this session, do you have any other question? Maybe one more question, if any question from you? No? Then we can conclude this session, especially with the last inputs from our three wonderful speakers regarding the future of semiconductor, especially in Indonesia. Now, the first one is regarding the research facilities, because we need more research regarding semiconductor, and then we, as Mr. Han said, we have the potential because we have humans. We need a lot of humans to create the semiconductor. And then also from Miss Anna regarding the talent that needs to be found and needs to be nurtured. So in the future, we will have our own manufacturer, maybe by collaborating with what is available in the world now. Thank you so much. Let's give a very big round of applause to our speakers today. Thank you.
Thank you all speakers and moderator. As an appreciation, we would like to present certificates to the respected speakers and moderator. Please kindly come to the front of the stage. And to present the certificates, we kindly invite Vice Director of Taiwan Indonesia STIC, Professor Felicia Edi Sutarjo, to hand over the certificate to the speakers and also the moderator. The first certificate is for Ms. Anna Baweh, Director for International Government Affairs, Intel Corp, USA. Thank you. Move to the next speaker for Mr. Hansu, CTO of Mega Union Corp, Taiwan. And also the last speaker, Dr. Ruri Agung Wahyuono, Deputy Department Chair, ITS Indonesia. And also to our moderator, Dr. Ratih Nur Esti Anggraini. And please move closer for all respected guests. And let me count it down from 3, 2, 1. Thank you, and please give it a big applause for the respective guests and also the moderator. And now please be seated. Now it's time for a coffee break. And please note to return to this auditorium within 30 minutes to continue to the next session. See you in next 30 minutes.
AMD does more than advance AI. AMD makes the limitless potential of AI possible.
Distinguished guests, ladies and gentlemen, the conference is about to commence shortly in 5 minutes. Please kindly find your comfort seat and return to the Auditorium Research Center ITS campus. Once again, the conference is about to commence shortly in 5 minutes. Please kindly find your comfort seat and return to the Auditorium Research Center ITS campus. Thank you. Distinguished guests, ladies and gentlemen, please return to the auditorium because the conference is about to commence in 2 minutes. Once again, please return to the Auditorium Research Center ITS campus because the conference is about to commence shortly in 2 minutes. Thank you. Welcome back, distinguished ladies and gentlemen. Following the previous agenda, we're moving forward to the third plenary session and also collective Q&A. As a reminder, each of the speakers must finish their presentation within 10 minutes, and the discussion must be wrapped up within 20 minutes. And now, we would like to invite our moderator, Dr. Hazik Fabroyer, to lead the whole session. Please welcome Dr. Hazik Fabroyer. And now, time is yours.
Check. Right. Good afternoon, ladies and gentlemen. I hope you all had a refreshing break. Welcome back to our third session of the day. My name is Hadik. I have a Chinese name as well. Ha Ming Fei. Ha 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 de ha. Ming Tian de Ming. Fei Chi de Fei. It's a pleasure to be your moderator for this session today. In this session, we will delve into the critical role that semiconductors play in the AR revolution. We will explore the future of semiconductor research and discuss the advancement in high-performance computing and their implications for our industry. Before we begin, to make it a bit different, let me share with you a quatrain. In Indonesia, we have what's so-called pantun. In English, it's a Malay quatrain that speaks to the spirit of innovation. Let me share with you. In circuits deep, where thoughts ignite, the future's course begins to weave. Through every chip, we grasped the light and dreams of what we can achieve. Thank you very much. Here we will have an impressive lineups of speakers who are experts in their fields. Each speaker, as the Master of Ceremony announced, will present for 10 minutes, followed by a 20-minute discussion at the end of the session. We encourage you to jot down, to note down your questions, as we will have an interactive discussion after all of their presentations. And please allow me now to call all the panelists or the speakers. The first one is Eric Hong, the Senior Manager for Process Integration for Micron. Please give a round of applause to Mr. Eric Hong. And then the second one is, or if you want, Louis, yeah, you can also accompany Mr. Eric. You may choose your seats. And second one will be our Director of Research Center for Regional Development and Community Empowerment in ITS, Dr. Fadilatul Taufani. The third one, Mr. Brandon Lubis, the AMD Commercial Lead for Indonesia. And last but not least, Dr. Chun Chen Yang, the Chair Professor from Mingzhi University of Technology. Okay, as for the first presenter, so as I mentioned, we would like to have you 10 minutes presentation, and then we will follow up for each 10 minutes presentation, and then we'll follow up with the discussion. Mr. Eric Hong, maybe you can go to the stage, to the podium, to start your first session, If you, yeah, it's preferable if you don't mind. Thank you very much.
Okay, since. Okay, sure. Okay, since good evening, everyone. So I would like to show Micron is the heart of the AI. So me and Lois will introduce the AI and the Micron. Next slide, please. Next slide, please. Okay, I just quickly introduce by myself. It's an honor to join this seminar. This is my first time to Indonesia. So I'm Eric Hong. I'm coming from Taiwan Micron. I am the process integration of a senior manager. And I used to be PFA department and the ELS department. So today, sorry, next slide. In the first of all, I would like to quickly introduce my company, Micron. And Micron is a global company, both memory and storage produce enablement currently AI, 5G, and automotives and IoT. So actually, we are a global company which we have a fab site located in US and Japan, US, Singapore, and we also have R&D and manufacturing in US and Taiwan and Japan. So we total have 44,000 of team members in Micron. And next slide, please. And especially in Taiwan, actually we have 10,000 of team members in Taiwan, and the 60% of DRAM are shipment from Taiwan. So actually Taiwan is quite important role in Micron. So it's okay, so you can see we have 1/4 of team member in Taiwan. So that's the reason why we have first a photo of the best tool, EUV, in 2022. And we also produce the most advanced DRAM HBM, and have R&D manufacturing fab site. And we have right now we are produce the best technology from 1 alpha to 1 gamma. So that's the reason why Taiwan is getting more and more important right now. And in the future, we also plan to hire more and more people due to we will have a new fab site and assembly fab site in Taiwan now. Okay, next slide, please. Okay, I think this is the first, most important thing is to play this video. And this request from my boss, yeah. So please help to play this video, I think. It's quite cool. Thank you. You can also try the ChatGPT and Copilot to check the answer. Okay, next slide. Okay, as everyone knows, AI is already changing our life and world and transforming the world. So it has many of applications, as everyone already knows this, like automotives. And AI enables self-driving car to navigator and to recognize objects by machine learning and computer vision. Like healthcare, and AI also enable the doctor help to take care of the patient and find out the new medicine by medical image. Like whether AI also to based on the bigger data to predict when will happen a typhoon or earthquake is later. And personal and workplace productivity. As everyone know, like ChatGPT and Copilot, like I'm going to write down weekly. I must to go be my weekly center to ChatGPT help me to check the grammar, yeah. Sorry. And learning. I hope sometime I will have an AI translation help me to translate my language. Anyway, okay. And learning actually right now, some of the students right now AI can enable to understand their weakness, to give them a personal content. And smart manufacturing, this part I would like to introduce how the smart manufacturing is changing our Micron now. Okay, next slide. Okay, so actually not only the current, as everyone know, it's already changing our life, and our Micron is also developing our AI in Micron. We also hope a similar of ChatGPT can help us in Micron. So actually we start from the Micron from 2015, in beginning of Hadoop big data, and after the 5G and some application developer. Right now we already have a similar called the Gen AI, which can help us to do a similar thing. And also like right side of the image, we have a three kind of application, like automotive guide vehicle, which is it can avoid people to handle heavy equipment is more efficiency. And like the second one is Micron advanced scheduler. And as everyone know, the flip side tool, some parts have a PM, have a cycle time. If it have a longer of a PM cycle time, it will become an issue. So it can enable earlier issue resolution, and also can help to product efficiency and the capability. And the final one is open AI analysis and simulator, which is I'm the process integrated engineer, sorry, manager. Anyway, so my main task is to identify the issue and the failure model to have a solution. So right now we already have a similar function which can help us to give advice the issue what is happening before, and given some solution we can try. So right now before we are based on our experience lesson learned to solve the issue, but right now even though the young engineer already can fix some simple issue now. So based on this, we already have a 40% of reduction in product downgrade and 20% reduction from new product ramp, and 34% is a reduction in the machine downtime, and around 18% of labor productivity efficiency. Okay, next slide, please. Okay, the next one I would like to show. The first one is how AI enablement to Micron manufacturing. Another one is how we do the product for the AI. So on the right hand side, as everyone can see, the AI, what the AI application grow so rapidly is due to right now we can handle the task at the same time and the amount of data. So from the chart can see right now, from our ChatGPT 4, it need around 1.7 of a trillion of amount of a parameter. And in the future, right now we are still at a narrow of AI phase. In the future, when after 5 years, we predict we will have 10 times of parameter data, which will need. So Micron is one of 3 global memory can produce the advance of HBM DRAM, and also is the only one of a US-based company. So the bottom button is our, like the video show, is our product, which is we have the high speed of 1.2 TB bandwidth. And the most important is we, compared to other competition, is a 30% of reduction for a lower power. Yeah. Next slide, please. So, okay, so based on this, Micron Taiwan is fueling the AI revolution. So the three of a key strategy in our future, not future, actually is already working on it. The first one is like advance of sampling and testing in Taiwan. So right now, so right now Taiwan have a front side and back end side. So you already 10 minutes? Okay, I speed up. Okay. So, okay. This is a key strategy right now, and we already started produce HBM3E key important product to NVIDIA. Yeah, next slide. Okay, this is currently a three-phase of AI. This one just one quick summary one. AI is be the part of the future in Micron and in everywhere, in every slide. Even though right now we are still in the narrow of AI, in the 5 year to 10 year will become the more and more need. We still need more and more. Sorry, this one will be a part of future. We hope that will become. We will need more. Anyway, okay. Next slide. I would like to introduce our Micron culture right now. In Taiwan of Micron right now, we have a 33% of a movement in Taiwan, and we have a 30 country of people. It's diversity global team in Taiwan now. So in the future, right now we have a 3% of a team member is from different country. In the future, we hope we have a 10% of a team member in our Taiwan. So based on this, we got some reward from like best workplace and our family good. Sorry, it's quite simple. Anyway, okay. So I cannot explain it well. So I will introduce an engineer from Lois. Here, yeah, Lois.
Hi.
To explain more, to think what about the Micron. Let's welcome the Lois.
Okay. So yeah, hello everyone. I think we have passed the 10 minutes, but I'll just share 2 bits of myself. Okay, maybe I use this one. So as can go to next page. So as what Eric mentioning is that Micron is currently one of the best semiconductor company, and it also won several awards like best workplace to work. But is it really true from the points of view as it's an engineer? So today I would like to share a glimpse of my life in Micron and my perspective as a foreign talent engineer. So hello everyone, my name is Luis, and yeah, I'm from Indonesia. From Medan to be precise. So to put my long introduction short, just focus on the timeline of my life experience. So actually, I'm pursue my further educations in Taiwan. Right after in one of the best university, which is NCTU. Right now it's NYCU. So right after I graduated, I joined Micron as an equipment engineer. I learned a lot of things like productions, tool troubleshootings, and also some KPIs like manufacturing availability. And right after around 2022, I just till now I'm taking a role as a quality engineer, which role is just to ensure all the process and the product is meets the customer requirements. And so basically I've joined Micron for 3.5 years, and I believe with this I have enough resource to share my insights and to share the highlight of my life in Microns. Okay, next page. So I summarized the last page with 3 highlights of my life in Microns. I'm going to share what's Micron really good at, and also like why it's deserve this Best Workplace to Work award. So the first one is related to the DEI activities. So DEI stands for diversity, equality, and inclusions. I believe all of you must heard about this one. So actually, because Micron is a multinational company, we have fab in Japan, in India, in Indonesia. Sorry, there's no Indonesia. So we have in Malaysia, Singapore, and US. So we actually celebrating cultural events every year, just like this Ramadan. So we teach our team member for what is important about Ramadan, and also like anything related to Ramadan. We also have Diwali festival celebrations. Like Diwali is one of the most important events for India peoples, which is the festival of lights. And we believe by having these DEI activities, all the foreign international talents that join Micron will have these inclusions working in Micron. And for the second highlight, I'll go through quickly for the corporate events. Actually, this is the events that I joined personally that I think Micron is really good at. The first one is the Micron Employee of the Year. So actually, I'm one of the awardee. This award is basically just to recognize the team member that implement all the Micron value in Microns and be a role model in the working environments. We also have a CIT, which is continuous improvement competitions. I was happen to be the host for that. So Micron has this continuous improvements activity every year. And for the last one, we also often go to university to share like what Micron really are, just like today in ITS. And for the last one is the volunteer activities. I was lucky that I'll be able to to meet the Taiwan presidents and also the CEO of our Micron, which is Sanjay. And also we have a Taiwan leaders team building with CEO. So all these volunteering activities is also a good opportunity for all the Micron employee to join in. Yeah, that's basically my life in Microns. I hope with these two bits, people get attractive to Micron. Thanks.
Thank you. And next slide. Just a final of one sentence. Micron is the best workplace in Taiwan, one of the workplace, and AI is the AI of heart of a revolution. Thank you.
Okay. Thank you very much, Eric and Louis. So we can now move to the second presenter, to Dr. Fadlatul Tafani. Stage is yours.
Good evening, everyone. Dear my teacher, Prof. Liu, very nice to having you again. Director Frank, thank you very much. And everyone, welcome to ITS, especially for the research building. Yeah, consists of 11 floor, dedicated for research, innovation, and community outreach activity. Yeah. Okay, next. My name is Taufani, you can call by that. Okay, next. Okay, a little bit introduction with the ITS. We are currently having around 1,000, 1,000 of the faculty members, and a part of that we have around 26,000 students, and non-academic staff 1,000. Okay, next. And we have actually 8 faculty staff. I have I'm continue. We have 8 faculty staff, and currently we have a 17 doctoral program, 27 master program, 20 international undergraduate program. I think the one that I'm recently mentioned, I think this is a strong candidate that we are going to have a collaboration. 20 international undergraduate program. So they have a mandatory program to have international exposure. either like a student exchange or like a curriculum. Next. Okay, next. Why? Yeah, next again. Okay, this is the one that the motor of research, innovation, and as well as the community engagement center. We have 10 research center. Yeah, all the office are located in this building, 10 research center, and the others we have a center of community engagement study center. Yeah, and then we have 5 center of excellence, and the last we have a cluster of innovation, the one that translating the research and innovation into commercial. Yeah, and as you can see, the target is to improve the local content from our partner, while the other is our research innovation based on the market driven. Yeah, next. And we have existingly we have for innovation cluster for innovation, and next. And currently we are having ADB funding to improve the innovation ecosystem to support our university funding. Okay, next. Okay, this one a little bit introduction about what is going on about the semiconductor, especially in East Asia. As you probably know that 75% yeah, semiconductor manufacturing capacity actually dominated in East Asia. And the interesting part is in the level of below than 10 nanometer, yeah, it's very limited actually. The technology is belong to the South Korea, but 8%. But while the rest, the dominant part is 92% in Taiwan. So actually, it's an interesting condition. But there is some issue, yeah. Of course, that East Asia, especially with Taiwan, is incidentally exposed to geopolitical condition. Yeah. Next. And this is the global, yeah, the global for the semiconductor market, yeah, in the span time of around 10 years part, yeah. As you can see that the figure is going up, yeah, always going up. Next. Including with the market share, yeah, including with the market share, you can see there is an increase in CAGR, yeah, in all aspect of our industry, automotive, communication, data processing, all, yeah. This is the projection data, and all the data always shows the increasing number, yeah. Next. Next. This one is interesting part. This is the trade balance in Indonesia. All the figures shows we are deficit in all aspect, yeah. Deficit, except for the car. Yeah. We are deficit in semiconductor, component, computer, telephone, medical supply, and so on. But this year there is the car, yeah. We have a surplus, but all actually the data we see that we are deficit in semiconductor trade balance. Next. And I tried to find quantitative data from the statistic, yeah, Bureau statistic. And interesting is the highest 10 imported commodity in Indonesia are strongly related with the semiconductor. Yeah. Yeah. So it means that Indonesia are still importing the semiconductor. Next. Next. But this is the good news from Indonesia. Yeah. As you may know that Indonesia are rich with the raw material supplies. Yeah. Particularly in silicon. Yeah. Particularly in silicon. So in our opinion that we can play important role, yeah, Indonesia government to become the raw material silicon supplier. Yeah. Next. This one
I can give you more detailed data actually. I summarize it within one slide. So the potential location for the silicon, is located in Sumatra, Java, Kalimantan, and Sulawesi. This is the candidate for the silicon supplier. Next. And this is the semiconductor line production ecosystem in Indonesia. Of course, it's not complete actually, it's not complete. But the one thing that I need to emphasize from this slide actually, from the bottom, that part, we have a chip design, we have chip design. And for the recent years, we have initiated the Indonesia Chip Design Collaborative Center, ICDEC. So we are quite strong in this part. And then for the silicon processing and wafer production, of course, we are also producing, but for the front end, the back end, we are still not so strong, compared to the other company. And for the back end, in Batam, we have Infineon. We have Infineon, Next. Okay, this is I mentioned earlier for the chip design. The ICDEC actually is some member actually that based on the degree of coordinating ministry for the economy. So it's a national actually, it's national movement, consists of a lot of at least 15 university partner, including with the industry. In this part, industry is the Polytron, Polytron, I think ICDC, the president also come here from ITB, and the vice president is from ITS, Dr. Asria Irfan. Next. And we are open actually as the Ministry of Industry. They have several incentive, several incentive. In terms of fiscal, fiscal incentive, we have 3 different parts. The one we have a tax holiday, and then tax allowance, and the last one, this is quite famous, super deduction tax, and up to 300% tax deduction, 300% tax deduction, and it's also applies for any topic, any research, not only for the semiconductor, in all any aspect topic research, This is a common super tax deduction up to 300%. Next. And this one, I think we are eager actually to introduce you at least 2 national flagship programs that are still running in ITS. This is a representative program, national actually. We call it REIDI, Renewable Energy Integration Demonstrator, and our campus support at least 1.5 hectare to realize this idea. Basically consists of hydrogen, biomass, and solar PV, and I think semiconductor is strongly related with this idea. And the program is come from Ministry of Education, Culture, Research and Technology, but the funding is come from LPDP, Ministry of Finance, through 3 different renewable energy. Next. And this is the representative design. As I mentioned earlier, we have solar PV, even when on the ground, and then floating PV, hydrogen, battery, and then we have a charging station and so on. And I think all these things are related with the semiconductor. Next. And the second project, this is also national project. We call it PRIME. PRIME is the one that I mentioned earlier with REIDI. The partner is come from Singapore, Nanyang, NTU Singapore. But the second, this one is the Australia, University of Melbourne, and the locus of our research actually innovation is in IKN, New Capital City. New Capital City. So all the research funding, research innovation will be implemented in IKN, including with the smart city is one of the topic. Yeah. Okay. Next. This is the concept of smart city in IKN, and some of them are designed by ITS. Yeah. Next. Next. Okay, I think this is the important part. I think I need to emphasize that although the government recently giving us various funding, but internally ITS, including with the ADB, give us particular funding for the improving what we call is infrastructure for the semiconductor. To be specific is clean room, yeah, clean room facility. We are going to have that kind of facility funded by ITS and IDB. Research, and then we have several funding from the ministry. And potential applied topic, of course, LED light bulb is still import, and the LED driver is also still import. Yeah. Audio chipset, yeah, audio chipset is the project that we have together with the ICDEC for the chipset. Tablet, electric scooter, and so on. Yeah. Next. This that we have commercially, a tablet digital. Yeah. Next. Next. This is LED light bulb. Yeah. There is a huge opportunity to initiate the collaboration in the topic of LED driver. Yeah. LED driver. Commonly in Indonesia, even though this is a LED, is still imported. Still imported. Yeah. Next. Next. And this is, of course, ITS quite strong in transportation, electric transportation. This is already commercial, average. Yeah. Next. The first generation cassette. Yeah. Next. And the smart city that already implemented in Surabaya. Next. Smart pool. Okay. Next. I think we can go through the digital water, and then the last one. Yeah. This is the, I think, since the curriculum, especially with the Department of Electronic, yeah, they are quite strong in IP and design, yeah. So this is the portfolio that what they have done, yeah, in ITS. Next. Next. The last one, recommendation. Okay. So we can assume, yeah, and recommend that Indonesia, yeah, should be as a raw material for making semiconductor. Yeah, that is the target. And then we need to pursue that the government to giving another kind of incentive for the semiconductor investor. There is a lot of open opportunity for the collaboration for the national project ready prime engineering in IKN, and then possible collaboration with the ITS, ICDEC, and so on. Yeah, this is the possible collaboration. Thank you very much.
Okay, thank you, Dr. Taufani, for all of your shared materials, especially with any research and products in semiconductor field. Now we continue to the next speaker, Mr. Brandon Lubis. Stage is yours.
Yes. Good afternoon. Thank you for this opportunity. My name is Brando Lubis. I'm commercial lead for AMD Indonesia. So what I do in AMD, actually I manage for all the business commercial for data center, commercial PC client for every institute and government in Indonesia. So basically what I want to share today about the future of high performance computing in the AI era, what AMD do in like in this industry and in this all like in our daily life. Maybe we can for the next slide for the video.
AMD does more than advance AI. AMD makes the limitless potential of AI possible. From AI PCs to edge to cloud. Powered by some of the most advanced GPUs, CPUs, and NPUs on the planet. And enabled by an open software approach that's accessible to all. Together with our partners, AI from AMD helps make more imagination possible. Innovation, breakthroughs, and healing possible. Peace of mind and thrills possible. The impossible is now possible.
Yeah, okay, next slide. Basically what AMD do is like in the cloud business, healthcare, industrial, automotive, like in client, in gaming. So we have like our CPU, our GPU in this area. So we want to make sure that what we offering is like high performing computing. So we trying to delivering like the technology, the new innovation. So like we changed like our architecture for AMD. It start from 2012, like since like Lisa Su like joined in AMD. So we changed everything, our architecture. So in the industry, like in CPU for device client, like we have like Ryzen, and then we have also in data center for EPIC, and in GPU we have in AMD Instinct. Next slide. So this is that product that we have in the cloud, HPC, like enterprise, embedded, and client device. Next. And we have like a broad portfolio for product for AI, for training, inference, and then we have developed for ours open software, we call it ROCM, and we are also open like ecosystem for any innovation with every like alliance partner in the world. Next. So this is like a product that we are produce like in data center is AMD EPIC. In GPU for we call it is AMD Instinct, and for even in client device AMD Ryzen AI. So this is already like developed for AI engine inside. Next. And we like have like a range data center workload. So from CPU, from general purpose, AI inference, and AI training for GPU, like we have like all this technology. Next. Okay, next. So this is like data center for EPIC, like the majority for hyperscaler that adopt our technology is mostly from AWS, Alibaba, Azure, ByteDance, Google Cloud, IBM Cloud, Oracle, Meta, and Tencent. This is like the hyperscalers that adopt our technology like from beginning. Next. And talking about like a supercomputer, till now like we have like Frontier, the #1 for top 500 supercomputer in the world. That this is Frontier is developed using AMD CPU and AMD GPU. So this is like for develop anything for this product, and we plan on this year that we also launching for El Capitan, the new supercomputer that developed under MI300. Next. So this is good, like footprint from AMD itself. Like we start our data center, like since we changed our architecture, from 2018, and now from 2024, like we have like revenue market share is now is increased until up to 30%. And next. And our technology now is AMD Epigena using like 96 core. Like the performance with competition is now is basic, like it is like compared to our competition that now better than when we testing using VMmark for the performance. Next, if like we doing like some like comparison, the easy like the if we want to like change or renew our data center that using the old server with the new server, like it is like we only need to replace 5 servers to only 1 server using AMD technology. And next, for end-to-end AI performance as well, like the performance is like it is like almost like 70% better. Next. And this year we will launch like the new technology. It is estimated in Q4 2024. Like we have like 5th gen AMD EPIC. We call it Turin. That this is will be using per CPU 192 cores for per CPU. So this is like our new technology for this year. Next. And we are already doing some like comparison performance from AMD Turin using summarization, chatbots, and translation for AI that the performance like is better from our competition. And next, for GPU itself, next, from last year that we have like AMD Instinct MI300. That this is one of the product that from AMD story, like this is product that the growth is very fast because you know that now is like industry about the demand for AI is very high. So this is the product that already like many our partner, our alliance like adopt this technology. And we also build like open software ecosystem. Next, we call it AMD ROCm. So this is like open source software from AMD to build anything under our GPU hardware. So next, even though we also like doing some like testing performance using AMD MI300 to our competition. And the result also significant with the performance using Metalama and Mistral. Next. And this is like the ecosystem that we have for AMD MI300 as now. So we growing, and we many AMD do now is like doing like some investment for AI ecosystem and software. That's all from me. Next, and thank you very much.
Check. Thank you very much, Mr. Brando, for your insights. Now we'd like to move to the next session. It's going to be the talk from Dr. Chun Chen Yang from Mingzhi University of Technology. The time and stage is yours.
Okay. Yeah. 10 minutes. Ladies and gentlemen, good afternoon. I think I'm the last one in this session, so let me make it quickly because maybe I just did a bit introduction about university MCUT in Taiwan. I served this university already close to 30 years, and also we are like engineering oriented and more close to industrial. We call academic and industrial partner is our motto for this university. Okay, next page.
Yeah, this is our campus. We have a little bit good spacing, 62 acre in New Taipei City area. Next. This school, I think we established in 1963, about 60 years old. Similar age like ITS. In the morning I talk with a senior supervisor here. ITS around 63 years old, so pretty similar. I think our school is sponsored by private entrepreneur. You may have heard it, Humosa Plastic Group. This is the biggest industrial in Taiwan. They have around 100 company, variety aspect. Particular, also have a 3 university. Chang'an University more like medical oriented. They have more than 12 hospitals in over all island. And we start because you go back to Taiwan, 1960. We want to boost the industrial. So our founder, we need more like very efficient engineering. So we I think Humosa from 1953. Then our school 1963. 10 years later, Humosa have a good business. So we need a lot of engineering participate in this industry boosting. So luckily, this big company, giant company born and boosting the Taiwan economic. I think Humosa contribute a little bit this driving force. All right, maybe next page. I think our university very close to Taipei area. You go to 101 Tower, maybe 30 minutes, and also you can know majority airport in Taoyuan Airport, maybe 35 minutes. We are middle this transportation area, and also very easy to access downtown, subway, convenient campus. You know the Taipei city around 2.3 population. New Taipei city maybe 4 and 5 population. So we are right now have a lot of mass transportation system, pretty convenient. So I also take a look at Surabaya. Right now you don't have a subway, so you're going to build up the subway in the future because you have more population. It's good for population to commute it. Yeah. Okay, maybe next page. All right, this is recently we are local mechanism survey our university. General University we are around maybe ranking around 9. Technology University we are maybe recently number 3. I think in the front number 1 is Taiwan Tech, and the second one maybe Taipei Tech. So we are quite strong engineering on this university in Taiwan. Next page. Yeah, this is our campus. We originally have a 62 acre. Unfortunately, our founder already passed away. Before he passed away, we another 16 acre together. We have a 62 acre, a big campus in Taipei City area. Maybe next. Yeah, this is our campus. We have very beautiful campus on the New Taipei City. Next page. We recently quite accelerate. We call internationalize and globalize. Cooperate with a lot of South Asia countries. Particularly, our government promote the TIC program, IPP program. And also, we right now have more like a graduate program right now available for master and the PhD. So also we have a lot of program available for provide this tuition free, dorm free. Also give a very nice stipend to invite the talent South Asia country young people to join us. Maybe next. We roughly, I think, MCUT is quite unique. In the undergraduate or 1 year, you have to go outside of campus and practical training 1 year, and then come back to campus. So still the majority is quite good practical skill on the engineering area. So we have more than 120 local, including USA. They can practical training 1 year. Also, they have a payment, average salary around 25,000 per month, NT dollars. Okay, maybe next page. This is another, we have a lot of, including FastCon, E3, National Lab. We have a lot of students can go over there, have practical training 1 year. Maybe next. Yeah, this academic, maybe, yeah, next. This is our entrance, university entrance area. Yeah, our school is quite small, maybe the smallest one in Taiwan. We have around 200 faculty. Student maybe 4,000. Graduate school maybe 600, and undergraduate maybe 3,500. And 3 colleges, 10 department. Maybe next page. Yeah, also we are quite encouraged our faculty to research. Particularly, we have 10 research center. We established in 2010. I particularly in charge is battery research center. Last established in 2012. Right now it's more than 10 years. Maybe next. I belong to College Environment and Resource. We also have available for semiconductor program. And recently more high is AI program also available. Maybe next. You can see this program, majority I think in the morning, a lot of experts already talk about semiconductor manufacture. I think undergraduate program, all, including lots of different aspects already, yeah. Go next. These are our department, chemical engineering department. We are more than 20 faculty right now. Okay, maybe next page. This different, I think this department classify different aspects, 4 aspects: material, bio, and new material development. Next page. I think research, you need a lot of human resource, funding, and talent people together. I think for MCUT, we are quite luckily, every year we have quite, very plenty of the funding available to purchase our heavy equipment to allow students to personally using. So this is an advantage. Maybe go next. So one of 3 centers belong to this college. One is we call bio, and later have a China Herbal, and more recently is battery, our battery center. Go next. And this is a battery center we established in 2012. We have 2 aspects. One is lithium battery, one is a fuel cell. But 90% is more like a lithium battery oriented. Okay, go next. And we also have a PhD program. We applied this program in 2015, and luckily approval 2016. Then we start have a student, and currently we can allow to recruit a PhD student every year is 16. Okay, yeah, and currently around 40 PhD students join this center. Go next. Yeah, this is our center. We have different motto. Right now, more focus on pilot plan, in situ analysis, DIT calculation, a different more like advanced analysis technique developed for lithium battery. Go next. This is my personal. Actually, school provide quite excellent stipend for students, monthly 15,000 NT. And actually, our faculty, we have 15 faculty. We also provide additional. If you perform so much better, you can have a more like a stipend. Also, this is when you make a list this candidate, your tuition free don't available. Also, you have a stipend available, so students can really enjoy and research on our campus. Maybe next. Yeah, this is our campus. Maybe. Yeah, or maybe go further, because my time is almost end. This double degree also available. Yeah, maybe go down. I think Taiwan is a nice and a beautiful island. Whole season is quite different. Also, we have Aboriginal people like Arnhem Mountain. Maybe you can have some enjoy our culture and local, different particular wood in Taiwan. Go next. Yeah, there's a variety of food available in Taipei and downtown area. I hope you can have a chance to come to Taiwan, enjoy them. Maybe next. Okay, this is some sightseeing spa in New Taipei area, particular Ximen, Night Market, Kending, all right? So maybe this is the last one. Yeah, okay. So hopefully my introduction can impress to you. Yeah, thank you.
Thank you very much, Dr. Yang, for your presentations. We now have some time for questions and discussion. I would like to have the audience maybe to share some thoughts or questions. You may raise your hand and we will bring a microphone to you. Maybe to initiate some discussion, I would like to ask first to Mr. Eric and Louis. With respect to, you said that you also kind of, the Micron, the memory technology in Micron also kind of working to support AGI as artificial general intelligence and also artificial super intelligence, right? However, I saw that you said that the evolution of the memory advancement is like a linear. Do you see, in terms of supporting the AGI, it will be still linear or it's going to be exponential? What do you think?
It's a good question. Actually, the AI is used from beginning of the 1950. So actually, it's not a new of technology. And the reason of AI why the development is so quick is due to the numerical modeling. Like recently, the 2017 started Transformers. Transformer which is used in ChatGPT natural language. So even though like Mr. Brando and me, I spend right now we have an advance of technology of the product from DRAM and either NPU. And then the future, the most important thing is another one is I think is multiple of a model and architecture. The multiple model right now, what we just can input is like a text or image. And in the future, we must to input like a sound or the video, which can help to assist them more and make more of decision like a human-like. The ANI and AGI different is AGI is similar like a human. Right now, the currently ChatGPT and Copilot still is in the ANI location, ANI the face. So I think the future, the advance of a model will be more and more important in the future. Like if we have another like a transformers architecture, and it will be a more rapidly of achievement to AI, exponential. Yeah, yes.
Okay, so you agree with this perspective. Okay, thank you very much, Eric, for your thoughts. Do we have some questions maybe from the audience, please? Can we have somebody to help to pass the microphone? Or should I? Okay, let me go down. Please also address to which presenter you would like to ask the question.
I want to ask about from Micron, Eric Hong. Maybe I want to ask about the, from what I see that the company is focusing on the memory, right? And from my knowledge about the AI, there's a new kind of AI which is compute in memory, where we're using memory store to compute the architecture itself in the memory. What is your opinion as your company is focusing on the memory itself? So what is your opinion about the computation in the memory? Maybe that is my question.
Okay, sorry, I needed some time to answer this. So let me clarify your question is what is the future of Micron, the DRAM, the product, how to help the AI?
Yeah, maybe because from what I see that maybe there's a future where we are using a new technology, which is do Micron have like a plan to go to this road?
I see. Okay. The current DRAM, like I just mentioned, HBM, DRAM, the most advanced of technology product is HBM. The HBM3E, the first one we need to have a wider bandwidth. Right now it's 1.2 T, but we need to get more and more bandwidth. Another one is DRAM of assembly TSP of bonding is quite important. Due to we need more or less power, and due to like AI cannot like a human. Human thinking just need a few and less of a power, but current AI still need a lot of power currently, even in currently new of modeling. So I think what the Micron of a strategy. First one is still as wider of a bandwidth, and second one is less of power. So that's the reason why our Micron compared to other competition is 30% of power consumption. Yeah.
Yeah, thank you very much.
Thank you.
Okay, thank you very much. Do we have any other questions maybe? Maybe to other presenters? Okay, great. Or still the same? Or to other presenters?
Thank you very much. I have a question to Professor Yang from Mingchi University. It's about the opportunity for the PhD program. So my first question is, do you have any requirement for your students? I mean, from their education background, for example, from the bachelor or for the master degree. Because I see that your department is a something specific from battery technology. So that's my first question. And the second question is, what is your requirement for the graduation? For example, how many papers to publish? Is there any SGI papers and so on? Thank you very much. That's all my question.
2 questions for Dr. Yang.
Oh yeah. I think majority before the PhD, entering PhD, your background can be chemistry, physics, material science, chemical engineering, chemistry. We are quite welcome. And second one, normally you become adapted, officially, everything is tuition free, dorm free, also stipend available. Normally, our programs require normally 4 years.
4 years.
First year you have to take a course, and we give you a coin cell training, everything platform, be ready. And second year you become synthesize your material. And we are qualified also. And final, we have a final defense. Normally, I think we have a couple Indonesian students come from different, not Surabaya, from Bangkulu, from Kanamuna, I think, Pakan, and Padi.
Right.
Normally they can publish 3 and 4 Q1 paper.
3 to 4 Q1.
I was saying maybe Indonesian is number one, my favorite student in our center. Yeah, honestly speaking,
Number one favorite students.
They show up very early and go home very late. Yeah, but they working very hard and learn very good skill. Yeah, I publish good paper. Yeah. Okay.
All right. Thank you very much for your response. It's okay. Great.
But normally 2 papers you can 10 points you can graduate. Yeah, normally. But they always do more.
Okay.
Yeah.
Normally 2 papers, but most of the students do more than that. Okay. All right. Okay. Can we have another question from the audience, from the floor? If not, I would like to maybe follow up what Eric said about the performance and Brando, you said about the performance as well from the AMD perspective. But I would like to ask you from the other perspective, which is the efficiency. How do you balance between these two in AMD, between the performance and the efficiency, especially for the data center?
Yes, that what AMD focus on, like we are not only focus about, we focus on three things actually. One is performance, second is security, and third is power efficiency. So what we built like with our product, that we need to consider the three things. That's all. That's that we need to focus, like we just on not like doing like good performance, but this is like power consumption is very high. But you can see like in the evidence in like top 500 for green HPC, that majority is built by AMD technology. So we understand that the consumption for electricity now is higher and higher, right? So we understand that we must like build some product that we like concern about the sustainability, something like that.
Great, very great response. Thank you very much, Brando. Any questions from the floor, from the audience? Otherwise, I would like to ask to Dr. Taufani, speaking about the advancement in the semiconductor, I would like to ask your perspective. How do we as an Indonesian, or maybe especially ITS, set the research stance? So in which field or in which area we should focus on, especially in the semiconductor, whether we want to focus on the design, or should we go with the manufacture, or just supporting the raw materials as you mentioned in your presentation? How do you see that?
Thank you for the question. As you may know that ITS is engineering actually. Yes, engineering institution. So of course we are focusing on that, and we have a representative quite huge amount of funding, and we got it from ADB. And some part of the funding actually we invested for the semiconductor infrastructure, to be precise, for the clean room, yeah. And of course that means that the clean room facility can be utilized for various applications, including for the solar cell, yeah, any requirement for the clean room, yeah. So in that case, of course, manufacturing, we try to enter that part. And for the curriculum, I highlighted two big parts in ITS. For the semiconductor, one is the IC design, yeah, and the second is the nanomaterial for the supporting the semiconductor. And the other thing is we are very open, yeah. Of course, we have two big projects from the national, from two different ministries. We have REDI, renewable energy, while the other one is prime engineering, that going to be implemented in new capital city of IKN. So we are very eager to have industrial entering the collaboration with the REDI, or as well as with the prime. And of course, in that facility, there are a lot of innovation. Industry is also entering that one. For example, like LED is still import. LED lamp is import. Yeah. And one particular industry, yeah, they enter and collaborate with the ITS, and then they are very happy since their local content can increase past the minimum TKDN, yeah, local content. Indonesia is 40% local content minimum. Yeah. Otherwise, you cannot enter the market for the government. Yeah. It's mandatory. So several industry entering ITS to boost their local content TKDN. and the other is based on their problem. Two perspectives. Yeah. Thank you very much.
Very good. Thank you very much, Dr. Taufani, for the perspectives. Okay, one last question. Maybe. Yes, go ahead. Can we have the microphone over there? Down there. That one. Yes. The guy that's standing. Yes.
Okay, good afternoon. Thank you very much for the opportunity. My name is Epino Ginting. I'm a fresh graduate from ITS. I want to ask for Micron representative maybe.
Micron.
A couple moments ago, I see like Micron recruit talent from University of Indonesia and also ITB, and I heard that more than 20 people from there invited to Taiwan. And I want to ask a question: will you also open recruitment from ITS students? I think that's it. My question.
Whether you want to also, he said that you invited ITB students for some opportunities to Taiwan.
Yes.
Okay.
Will ITS students have the same opportunity? Maybe.
Will ITS students will have some opportunity for that?
Yes.
Do you? Yes. Yes.
Yes.
Clear, concise answer.
We will take action.
Okay,
Micron will support you.
Okay. Thank you so much.
Okay. Thank you, Eric. Yes, I think that's all. Thank you to our distinguished speakers. Please give a round of applause to them. The discussions we've had today underline the importance of continuous collaboration and innovation in semiconductor technology, particularly as we navigate the complexities of AI and advanced computing. As we conclude, I would like to share yet another quatrain or pantun, but now it's in Chinese version. Hopefully it works. Let me try. Okay. 科技开新路，千里共一程，奋进逐梦去，创新应新生. This means technology opens a new path. We journey 1,000 miles together, striving forward to pursue our dreams. Innovation echoes our heartfelt voice. Okay. So it works. Thank you. I hope you found this session as valuable as I did. And please, again, join me in giving our speakers a round of applause. And now I would like to bring the session back, pass the session back to the Master of Ceremony.
Thank you, our moderator, and also our speakers. As an appreciation, we would like to present certificates to the respected speakers and moderator. Please kindly come to the front on the stage, and to present the certificates, we kindly invite Director of Taiwan Indonesia STIC, Professor J.Z. Liu, to hand over the certificate to the speakers and also the moderator. For the speakers, there are Mr. Eric Hong, Senior Manager for Process Integration from Micron, Director Fadlilatul Taufani from ITS Indonesia, Mr. Brando Lubis, AMD Commercial Lead for Indonesia, Dr. Chun Chen Yang, Chair Professor MCUT Taiwan, and also our moderator, Dr. Hazik Fabroyer. And now please move closer and take a picture together. Let me count it down from 3, 2, 1. Once again, 3, 2, 1. Please give it a big applause for the speakers and also the moderator. And now please be seated. It's time for the last plenary session and also collective Q&A. As a reminder, each of the speakers must finish their presentations within 10 minutes, and the discussion must be wrapped up within 20 minutes. And now, we would like to invite our moderator, Mr. Fajar Budiman, to lead the whole session. Please welcome Mr. Fajar Budiman to come up to the stage. And now, time is yours.
Okay, test. Okay, welcome everybody to our last session. Hopefully it's not at least, but it's, of course, it will be wonderful to close our sessions to be wonderful. So we will have three speakers for the last sessions. That's number one is Dr. Ing Doti Dewi Risanti, STMT, the head of AFM lab from ITS. And the second one, so he's Professor Dr. Taufik. So he will give again a speech like he was giving the speech in the beginning in the morning, and then he would like to close also the speech in his year. So it's so interesting. And then the third one will be Professor Dr. Yang Feng Wang. I would like to invite Professor Dr. Yang Feng Wang. Okay. So she's from professor from CICU. CICU is an expert of air pollution control, waste treatment, and recycle sustainable environment educations. So please give them applause for our three speakers. Okay, so because we are running out of time, I would like to invite, so let's begin. The first one is Dr. Ing Doti Desi Risanti. Please, the stage is yours.
Thank you very much for the time for me. Good afternoon, ladies and gentlemen. So my name is Doti Dewi Risanti. I came from ITS, specifically from Laboratory of Advanced Functional Materials. So I am the head of the laboratory. Okay, next. So what we are talking about, so now I will introduce ourselves and also what kind of courses that has been offered in our department, and also some student works, and also some simple devices that has been created by the students. Okay, next. Okay, this is our department profile. So we are engineering physics department. We have 5 fields of interest, in which I came from materials engineering. So we are actually somewhere in between mechanical and electrical engineering. So this is why we are the only few departments that focusing on engineering physics in Indonesia. But actually our works is quite wide, and can also close the gaps between the engineering fields. So this is our department profile. So we also have a master's degree and also doctorate degree, and we also already been accredited as excellent. Okay, next. This is our laboratory structures. So our laboratory is actually only advanced functional materials laboratory, but right now we have industrial collaboration, so we will expand our labs into 2 labs. Okay, next. This is our lecturer profile. So I am as the head of the laboratory, and also we have 3 others lecturers here, and the last one perhaps you already know that he has given talk this morning. Okay, next. Well, this is the research that has been conducted in our labs. So it's quite wide actually, that it is comprising of the energy materials and also polymer and composites, which right now I have a collaboration with other university as well. And we also have some semiconductor and superconductor, catalyst and photocatalysis, and also biosensors, spectroscopy and others. Okay, next. So this is the interesting part, that we have several courses that actually leading to how we could creating such kind of simple devices in the base of a semiconductor. So we start from the bottom, that we have a quantum physics, in which we learn about electronic states, etc. And basically also we learn also about the basic of spectroscopy. And then the next one, we move to the physics of materials, in which we learn about those things that I have written in my presentations. And the next one, we have material engineering in this field. So we have some focusing on how the semiconductor is fabricated. So particularly starting from oxidation and also doping of the materials. And then the last one, the final courses in compulsory courses that we have is, we have a smart materials courses, which also comprises of how to create a sensor or even actuator materials. Okay, next. So this is the scope of the semiconductor major processes that perhaps all of you already know, but the one that I put the red box is actually the main contribution of our courses. So particularly we are focusing on the doping materials. So we are not right now not focusing on the wafer preparation, etc., but we are focusing on the doping of the materials. Okay, next. So this is how we taught the students. So because it is very limited resources that we have, so we have to be creative in somehow. So we have to include some softwares as well to allow the students to calculate how the basic properties of the, for example, here the PN junction. So we use also MATLAB code, and also find other resources which is free from NanoHub, so which allows the students to learn the basic properties of the materials. Okay, next. And then, well, this is still written in Indonesia, but this is one of my slides that I taught in our class. So we let the student know about how the device has been manufactured. So from this device manufacture, then we let the students to design the process parameter which is required for certain devices. For example, if we want to manufacture the bipolar junction transistor, so which one that you need to design first, and what kind of parameter that you want to employ, so you need to put into this kind of processing. Okay, next. Well, that was the compulsory part, but we have also some elective part that we offer from our labs. So basically we have four big scope here, which is energy materials and also sensor technology and also the nanotechnology that has been mentioned by Mr. Taufani before. And also we have material characterization, which is also supported by computational materials. So from these elective courses, we hope that we could put some emphasis from the elective, from the compulsory one into the elective one. So for example, right now that we are really focusing on is on the sensor materials. So that's why we need some specific semiconductor that is required for this process. Okay, next. So this is the example what the student has been done in our lab. So we are playing with some oxide semiconductor, which is quite easy to do and also to obtain here in Indonesia. So here we use it as a photovoltaic materials. So as an example that some students also has incorporating zinc oxide or even making some heterojunction for this photovoltaic device. Okay, next. So this is how we taught the students how we could engineer the semiconductor materials into a specific device, for example, like creating heterojunction or putting some quantum dot inside, or even by playing around with some doping materials or making some composite materials, or even try to modify the layered materials. So the last one is the layered material. We use tungsten disulfide, so we want to make the multi-layers materials to become monolayers. So what we are using is actually the simple liquid phase exfoliation processes. Okay, next. So this is just an example of the work of the students creating a core cell structures for being doped into the photovoltaic device. So here we could create some kind of gold nanoparticle which is celled with the titanium dioxide and also silicon dioxide. Okay, next. So we can also play around again with the modification of the nanoparticle size by using the computation, which is also free. So that's why the student can also play around with this, so we can improve the material that we have. Okay, next. So this is also another student working with the hydrogen production, for example, here. So we have two materials from semiconductor which has been creating in a heterojunction. So we can also resulting hydrogen production in this from these materials. Okay, next. And this is from the photovoltaic. So we use also titanium dioxide, which has been combined with nano gold particles, which we hope that we can improve the energy harvesting of the materials. Okay, next. And this is the simple devices that has been done by the students. So this was we create some kind of a spectroscopy which is made from 5 lights. So this also has been publicated in a seminar. Okay, next. And this is the other one. We use a microfluidic for biosensors. Okay, next. And this is the last one, that we have also a capacitive sensor, which also based on this parallel plates capacitor principle. So this is also for detecting the aquaporin 5 from the saliva. Okay, next. So this is the device. So perhaps still written in Indonesia some words, but I hope that you can get with the value. Okay, next. Well, thank you for the time, and that's all for my presentation. Thank you very much.
Thank you, Dr. Doti. So the next, I would like to invite Professor Taufik. The stage is yours.
All right. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everybody. Hello again. This is the second time you seen me on stage. This morning I gave a talk on role of polyelectronics in semiconductor fab equipment. And I mentioned earlier during my talk that my tie to semiconductor is more on the application side, right? So I'm going to talk more about that. In particular, role of polyelectronics as driving technology for semiconductor industry. I don't know if you remember what the Consul General mentioned earlier this morning when he gave the speech. He said something that really resonates to my interests. I don't know if you remember this, but he said that, believe it or not, to that extent, right? He said that semiconductor, realize it or not, is the device that is responsible in powering our world. Right? That's what he said. And I totally agree with that, especially being a power guy. And if you don't believe me, well, check out your pocket. You have a smartphone, right? That smartphone these days is not going to work. It's not going to be that small. It's not going to be that powerful without power electronics, right? The semiconductors being used in power electronics. I don't know if this is LEDs or not, but if these are LEDs, believe it or not, behind that LEDs are power electronics, because you have to convert AC to DC, right? What else? Solar panels. We have any solar panels on the rooftop, your house. Same thing. In order to be able for you to use the energy from solar panels, you have to convert from DC to AC, another power electronics, right? So I won't go through the list, but as you can see, it's realized or not, it becomes part of our daily life. That semiconductors being used in power electronics really power our our activities every day. So I want to kind of emphasize on that. And since this is a forum, more so than like a speech, a keynote speech, I only have one slide. So next, which is last. All right, so you remember this picture I had earlier, right? That in power electronics, we have three components: sources, the controller itself, and the load. Right? So how are these power electronic components drive chip technologies or IC technologies? And these are all based from my personal experience, personal observations, personal experience. I don't know if you remember what I said earlier in the morning, that since I came to Cal Poly 25 years ago, I've been basically interacting with Silicon Valley type of companies, semiconductor type of companies. Of course, they are interested in the application side of it. Texas Instruments, MPS, analog devices, you name it. And we do student projects together. And from those interactions, I've observed several things that I would like to share with you today. I know 20 minutes went by very quickly earlier, so 10 minutes is going to be even quicker. So I'm going to try to be brief. On the source side, we have this driving industry that would impact how IC is being designed or chips being designed. Sources means energy provider, right? So therefore, we talked about utility side industry, such as PLN here, or a bunch of them in the US. So their application called for semiconductors that could handle higher voltage. Right? Higher voltage, higher power. So when I went to school a long time ago, when we talk about electronics, people think about just a tiny bit of IC, right? Nowadays, that's not the case. Because if you ever visit, for example, high voltage DC, HVDC right there. So high voltage DC is basically transmitting power with DC instead of AC. In order to do that, you need power electronics. And we're talking huge power electronics, not small ones. And the electronics that they use to be able to convert from AC to DC and transmit the power big time in LA, outside of LA, is about 7-story high. Can you imagine? Electronics that are that humongous in size. So, electronics doesn't mean small anymore. It could be big. That's why the name power electronics, the big ones. And so high voltage DC, as an example of application of electronics that would demand for IC design that can handle high power, high voltage. That's one example. On the source side. Renewable energy, for example, that's another one, right? That's becoming very popular these days with rooftop solar panels, as I said earlier. And as you know, solar panels outputs DC, but then in order for us to be able to use it at home, we have to convert it to AC. And so therefore, for those kind of applications, the IC that we are using do not require high frequency, for example, right? 60 hertz is okay. Or the switching frequency in terms of the switching frequency could be lower kilohertz. That's fine. But high voltage still, relatively speaking, right? Because 120 times square root of 2 in the US, it's still 170 volts. Here it's 220, it's worse. But you get my idea that in terms of application of power electronics in renewable energy, that would drive chip design that require high voltage, right? But not so much on the frequency, right? Let's move on to the load side, because I'm sure I'm going to be running out of time soon. Is it 5 more minutes, hopefully? Okay, right. On the load side, totally different world. I think I heard from the previous forum about processors' power requirement. Right? So that's different. It's not high voltage, but it's high power. And it's not low current, but it's high current. So processors right now, for example, requires very low voltage, under 1 volts, as an example. So it is common to have like a 1 volt processors, 0.8 or something like that, very low voltage. However, power is high, right? And the reason being, we want to maintain efficiency, high efficiency, right? Because if you do a very large voltage, right, then it would suck energy faster than higher current at low voltage. And so one example of a project that I did was with Cisco. Anybody knows what, yeah, you know. So it's a big company, and they're using processor that requires 1,000 amps at 1 volt. Can you imagine a processor that requires 1,000, right, amps at 1 volt? Now, for those of you who are not sensitive enough about current, it may be just numbers, but for us, you know, power electronics, who deal with power electronics design, 1,000 amps at 1 volt is a pain, right? Because Ohm's law, basically, I don't know if you're familiar with Ohm's law. Voltage is equal to I times resistance, current times resistance, right? So if resistance is 1 ohm, let's just say, simple math, right? Voltage is equal to I times R, right? R is 1 ohm. I is 1,000. How many volts is across? 1,000 volts already, right? So if your input is already low, 12 volts, you want to get to 1 volt, how can you do that if you lose 1,000 volts? No way, right? So therefore, the driving technology will be different for the chip there, right? So another thing would be, let's see, DC to DC converters. That's also a different beast, right? Nowadays, the push for DC to DC converter would be very high frequency, like megahertz. You know how many times per second is megahertz? Millions of times, right? The way I explain it is this. If you go home, try turning on the light switch. How fast can you do turn on and turn off in 1 second? How many do you think? 2 times, 3 times? In 1 tick? Maybe 3 times, right? That's how fast our body can do that. 3 times per second. But solid state or semiconductor switch, nowadays for DC to DC converter is being pushed toward or upward 5 megahertz. 5 million switches per second. Can you imagine in 1 second it has to go like 5 million times? It can only be done with semiconductor. That's how the DC to DC converter industry is driving the chip design for DC to DC converters, because they're pushing on the right, on a different direction, high frequency more so than high power, as an example, right? So I know I'm running out of time, but you get the idea that, you know, different application would require different requirements and specification for chips. Yes, and finally, I just want to mention one more thing, share with you, that I believe I mentioned that as well in the morning, that in the US, at least in the US, I asked my friends who work in Silicon Valley, and I asked them what would be the biggest, you know, market segment right now for ICs, and they said two things. Right? The first one is data servers. No, it's not data servers. What do you call it? Huh? The name escaped me. The second one is automotive, and the first one is data centers. Oh my gosh, data centers. You know, I'm still having jet lag. Sorry. So, data centers and automotive. Those are the two biggest markets right now in the U.S. at least. The rest of the world, I don't know, but in the U.S., that's what they share with. All right. So with that, thank you for your time again, and I hope that you learned something from there. All right. Good afternoon. Thank you.
Thank you, Professor Taufik.
Oh, yeah, okay.
So the last one I would like to invite.
Thank you. Solomon Soray. Yeah, good afternoon, ladies and gentlemen. I'm Yafeng Wang from Zhongyuan Christian University in Taiwan. Today I would like to share a different topic on the semiconductor industry. It's not the most important issue, but I think it's the basic issue, because if you cannot handle the West very well, I think no matter you are the leader in company, in city, or in the government, it's hard for you to run for the second term. So my topic is the circular and sustainable utilization of resources in Taiwan. Okay, next. Before the speech, I want to express how lovely in the city, because I have friends, I have students in Surabaya. So I love Surabaya very much, and I also have a great time with my students. For the past week, we went to the Zhongba to visit boutique enterprises by students to help them to build a demo with the water treatment plant. So I'm so proud of him. And this is my past week photo, and I would like to share with you how lovely the city. Okay, next. And because the 2050 net zero is the global trend, so to echo the target, the Taiwan government has announced the 2050 net zero as the national goal at 2021 on Earth Day. And for the net zero pathway, we have the 4 strategies, transition strategies, and 2 governance foundations. Next. And to support the net zero goal, next please. To support the net zero goal, we also have the 12 key strategies. The next. Yes. We also have the 12 key strategies, and resource recycling and zero waste is one important strategy. It's managed by the Taiwan EPA. And the next. And I would like to give you a general summary for the Taiwan West. The total West at 2022 is around 32.3 million tons in total. For the general West, it's around 34.7%. For the industrial West, it's around 65%. However, you can tell the recycling rate for the general West is over 50%, and for the industrial West, it's over 80%. So it means the recycling rate in Taiwan is top 2 in the world. Next. And we have a very famous 4-in-1 program I would like to share with you. Under the 4-in-1 resource recycling program, there are 4 important components that include the community residents that will to do the waste sorting. And the local government is responsible for the collection and the transportation for those recycling waste, and the private company that will purchase this recycling waste from the public, from the community, or from the local government, and they will do the recycling very well. And after they do the recycling, the recycling fund will give them the subsidy. Okay, next. So we have a big recycling fund, and this recycling fund, under the recycling fund, we have the 73 products under 14 categories. Those products has to be recycled by law, and the responsible enterprises has to pay the fee. So this fee built the recycling fund. Under the recycling fund management system, we have the fee rate review committee to evaluate the reasonable fee for those regulated product has to be recycled. Also, we have the audit and the certification committee to audit if the recycling company do the recycling well or not. And the recycling fund was well managed by the recycling management board. It's under controlled by the Taiwan EPA. Okay, next. So these 4 components complete the recycling system. And last August, the Taiwan EPA was restructured into the Ministry of Environment. Under this, the Waste Department has transferred into the Resource Circulation Administration. Okay, next. So for the most important policy for the Resource Circulation Administration, we abbreviate as RECA. We redefine the waste because waste, most of the waste are misplaced resources. So we redefine the waste as we maximize the resource utilization and minimize the waste. So we extend the scope of resources recognition and try to reuse, recover, and recycle the resources. And in the end, the minimized waste can be properly disposed. Next. And for the policy, RECA divided the resources into 4 categories. It's the biomass, organic matter, and inorganic. Next. And for the waste industry, now we call it the resource industry. We divided it into 2 categories. One is the venous industry, another is arterial industry. Venous industry is turn the solid waste into the reusable material and become the secondary material. And the arterial industry is it's a manufacturing process, make use of the natural sources. So take the automobile industry as an example. The car maker are the arterial industry because they use the natural resources to make a new car and sell to the market. And the dismantle or recycling company, they will recycle the old car. It belongs to the venous industry. After the recycling, they will produce the secondary material and try to make them into the production process again. So a solid and the quality, quantity, and the certification of the secondary material market is very important. So it's still on processing. Next. And this is the major strategies for RECA, include the green design, recycling, reuse, and the balance and the management of the treatment capacity, and based on the 2 pillars that are a complete circulation network and innovative technology, and those 10 key actions are the main target. Next. So for the strategy 8, they have the 72 actions, and they create 2 performance indicators. The priority strategies include the green design and the resource reuse, energy recovery, and establish a well-functioning circular economy network and innovative technology and system. Next. And extended life of product is one principle of the green design. Because the government encourage the manufacturers to repair and to maintain and do the after sales services capacity. This will drive the producers to extend their responsibility. So this create a new business model. We call it a product as a service. This PaaS subscription model will accelerate resource circulation and also to reduce the carbon emission. Next. And also the waste to energy is an important policy. So we divided the sources into 3 categories and provide the related responsible technology for reference. And the next. And building a complete circular economy value chain is very important. And now, you know, we redefine the waste. So your waste might be my resource. So how to complete the circular network is very important, and it's our next goal. And the next. And building a circular society need technology. So this is the draft of the resource circulation technology blueprint for your reference. Next. Taiwan EPA tried very hard to maximize the resource circulation and minimize the waste, and to build a circular society or a circular country is our future goal, and I think it will come too soon. So this is my presentation. Thank you very much. Thank you.
Thank you very much, Prof. Dr. Yayan Fang. Thank you. So for the next, I would like to invite the audience for the Q&A. Is there any questions or discussions? No? Okay, then I would like to begin to ask questions first from the last presenter was Prof. Dr. Yang Feng. You mentioned regarding the classification of the industry, venous and arterial industry. For the, you know that Taiwan has the biggest company, TSMC is in the world, the biggest foundry in the world. So TSMC like manufacturing semiconductor, which category, which is a venous or arterial industry, and then how you like trying to have a zero waste, because in the semiconductor you have manufacturing, you have a waste like chemical waste and things.
Okay. The venous or arterial industry belong to the resource industry. It's not for the semiconductor industry. So after the semiconductor process, they will produce the waste. If the waste can be recycled, it will belong to the venous industry. Yes, but if you produce some product and buy the natural resources, it will become the arterial industry. Yeah, okay?
Okay.
Yeah, thank you.
Thank you very much. Is there any follow-up questions to Dr. Bang? Okay. Any more questions? Okay, thank you. Is there any mic?
Okay, check. Okay, thank you very much for the very wonderful presentation. I'm Jenny from Widya Mandala. I am an academia, but I would like to ask, I'm interested in the Professor Wang presentation about, because you mentioned that in Taiwan, you already have done the circular economy, especially in the electronic waste or any kind of waste. You already have the pathway how to recycle it. But my question is, what is the challenge of the circular economy in Taiwan, especially for the semiconductor or electronic waste? Thank you.
Okay, thank you very much. Because it's not every waste that is under regulation. The recycling fund is responsible for the regulated product. There are still some product is not under the regulation product. So I think if the recycling product will have the market value, it will have automatically economical chain on the market. But if the waste is hard to recycle and there is no market value, I think this is the government responsibility to handle it, because every waste should have a proper disposal way. Yeah, okay, thank you.
Okay, any other questions? Okay, Dr. Irfan.
Okay, thank you. I want to ask Dr. Doti. Sorry, I know I can ask this directly to her in my free time, but I want you to maybe share with us, because some of your slides were about device fabrication with the current limitation in ITS. How do you go about and still continuing to publish results? Do you work with international partners or maybe Indonesian partners, especially for the device fabrication? Thank you. That's my question.
Thank you very much for the question. So basically, we have two ways of tackling this problem. So the first one, because we are having this limitation in the tools that we have, so that's why we are focusing on using photon in this way. So that's why we are going into the spectroscopy. But the second one, we have the opportunity since the early this year, we have been invited from MCUT actually, so that perhaps we can continue with the collaboration with MCUT to change this photon-based device into semiconductor-based devices. So that's the two strategies that we have up to now. I think that's all.
Okay, thank you. That was actually my question to you. So it's by Mr. Irfan already. So actually I would like to, because right now, do you, I mean, maybe you heard that we already have visited Germany and others for roadshow and everything. That actually maybe Dr. Doti can enlarge the collaboration between Taiwan, also Germany, to do the, because we have a limitation of the things. But how is your talk regarding that? Dr. Taufani already told that we are going to have a clean room in the maybe next 1 or 2 years later. So
well, I had experience with clean room, but it was a long time ago when I took my undergraduate degree. So at that time, it was in Bandung. So I did my bachelor work also in that, using that clean room, so particularly. So it's very nice if actually if ITS can have one clean room which is particularly for education, perhaps educational purpose. So that would be very nice, because I know that it is costly and it is also required well, precise technology and so on. But I believe that the human resource that we have could handle that one.
Great, yeah. Okay, any more questions? Okay, to begin, I would like to ask for Professor Taufik. So from your slide before, I just imagine that this is only one directional, right? For your diagram, because I was thinking like right now we have a bidirectional. So, but what I was thinking is a DC to DC converter. The second is for the automotive right now. A lot of research regarding, device and control in the power electronics, including the bidirectional DC to DC converter. Have you ever experienced and thought regarding that? Like right now, like some of my institute, they're doing in the semiconductor. We have a lot of robots, Franco robot and other robots, and they do some kind of harvesting for the using the more of the power cell right now. Like for example, in the automotive, they have a two dual battery, the 12 and 24. So you have to give a source and generator in the same time. So can you give like some explanation regarding that? Thank you.
Yeah, very good question. Thank you. Bidirectionality in terms of the way we address that, at least two approaches. The first one is by having a semiconductor device, in this case switch, electronic switch, that can actually handle bidirectionality of current. A good example of that would be TRIAC. I don't know if you're familiar with TRIAC. So TRIAC is AC. AC application requires bidirectional, right? By definition, AC is alternating. You got plus, minus, right? So current goes back and forth, right? So for AC application for a long time, they've been using semiconductor device that is able to provide currents in both directions. Right? So nowadays you have more fancier solutions. You can have MOSFETs that you can stack over this way and that way, right? So that's the second approach, which is topology. Right? So circuit topology is another way to address the issue of, or the challenge, I should say, in bidirectional power flow. So yeah, that should be the answer. Hopefully that answers.
Thank you, Mr. Taufik. Is there any questions more for Professor Taufik? Okay.
Thank you. Good afternoon, ladies and gentlemen. So my name is Yohanes Stefanus, and I am from Electrical Engineering, Institut Teknologi Sepuluh Nopember. And I want to ask to Professor Taufik. This morning you said that you're working with some military companies. So I would like to ask about what is the constraint in power electronics as in defense electronics. So that's the first one. And the second one is there any special specification for semiconductor in defense fields, in military chips? So that's it.
Yeah, yes. Okay, thank you. Very good. Another very good question. Thank you. I don't think I have the liberty to share, many, but I can share you a couple maybe that I believe is fine to share. When it comes to defense or military applications, as well as avionics, aerospace, number one has to be, temperature. Temperature range will be very different from consumer electronics, right? Not just semiconductor devices, by the way, but also passive devices, capacitors, inductors. When it comes to military applications, aerospace, their temperature operation is much, way better than consumer electronic, which is why they're very expensive. I can tell you, I've designed 2 different power supplies. As an example, one is for consumer electronics, for charger, right? So cost is the driving factor, right? The lower the cost, the better it is, right? Aerospace, military, cost doesn't matter, right? Money doesn't matter. So I had fun actually designing military design. Why? Because when I design consumer electronics, right, I start selecting components, and I went to my manager, said, look, I found this capacitor that costs 1 cent. And the manager still said, oh, that's too expensive. 1 cent, come on, right? Still too expensive. Whereas when I design for military purpose, for example, I found like a very good capacitor that costs $20. 1 cent versus $20. 1 cent versus $20. Went to the manager, yes, go for it. That's why I had fun actually, you know, designing power electronics for military applications. So the first one is temperature operation is way better than regular application or consumer electronics. Number 2, radiation hardened. Has to be able to withstand some level of radiation. Very expensive devices. You have MOSFET without any radiation hardened that costs maybe 50 cents a piece versus, and always in stock, by the way. You can buy right now, right? You call up the manufacturer, they can send you right now. No, no delay, right? No long, what do you call it? Like a long time to get it, right? But military purpose or avionic aerospace, it requires radiation hardened. It has to be able to handle lots of radiation, which makes sense, right? Because we're shooting up electronics to the sky, for example, right? So it has to be able to handle lots of radiation. And that's a very expensive device. 50 cents versus, for example, $250 a piece, right? So those are the 2 examples that I can provide you with, right? Okay? Hopefully that's enough. Thank
It's
you.
also good for the medical application in the power electronic, because medical is also is the same level of the military. I mean, have you ever experienced?
Yeah, to a certain extent, medical is higher grade than consumer, but still lower than
military.
Oh yeah. In medical systems, I think the priority is also safety, right? So it's not just radiation hardened, which is for some applications they don't really need it, but the most important thing is safety. How do you put safety around, power electronics?
Yes.
Yeah.
But for the military, it's not safety, right?
More than safety.
Because
yeah.
it's for war. I mean, just
when you buy $20 capacitor, yeah, it should be safe.
Of course, yeah. So it's more safe, right? It's safer than the medical. Is there any questions? Any more questions? Oh, Dr. Afwe.
Thank you very much. Allow me to raise a question to Professor Wang from Chungyuan Christian University. Very nice topic that you have been delivered to us. I would like to ask one simple question from your slide regarding with the recycling fund management. Yeah, you mentioned that the fee actually is coming from the responsible enterprise, and that fee is going to be used for a subsidy for the recycling system. Okay, is it in equal amount between the fee and then with the subsidy?
No, of course not. Yeah, every product has its value. So the the fee will be evaluated by the right fee committee. Yeah, so the committee will give a reasonable subsidy fee to that recycling company. Depends on what kind of product they recycle. Yes.
It means that the government still receive some funding actually and give the fund. Is it? I'm sorry.
It's under discussion. Yeah.
Okay.
Yes. Thank you.
Very interesting topic actually. Thank you very much.
It's interesting. Thank you.
Yeah, maybe we can imitate for Indonesia when we have a semiconductor industry later for the waste. And is there any more questions? We have actually, we actually ran out of time. So is there any more questions? If not, we can conclude the sessions. So it's really interesting for these closing sessions. So thank you very much for the speaker. It was like really interesting with the closing of the Prof. Yang regarding the environment that we need to remember when we have a clean room and everything, and then industry, of course. All right, give them applause first for all of them. A big applause. Thank you very much. Okay, I would like to give off to the master ceremony. Thank you very much for the speaker. Wait, we need to wait for the master ceremony. I think she will come in few minutes. I think she was, because it was like for speakers, but it's 3 speakers right now, so it's 10 minutes and then 20 minutes and then 5 more minutes. She's coming.
Thank you all speakers and also the moderator. As an appreciation, we would like to present the certificate to the respected speakers and also the moderator. And to present the certificates, we kindly invite Director of the RPM ITS, Mr. Fadlilatul Taufani, to hand over the certificate to the speakers and also the moderator. And for the speakers, is for Dr. Doti Dewi Risanti, Head of AFM Lab, ITS Indonesia. And the next one is Dr. Yafen Wang, Professor CYCU Taiwan. And also to Dr. Taufik, Director of Electric Power Institute, Cal Poly USA. And also for our moderator, Mr. Fajar Budiman. All right, please now move closer, and then we took the photos together. And let me count it down from 3, 2, 1. Once again, in 3, 2, 1. Okay, thank you. Please give it a big applause for the speakers and also the moderator for this last session. And now, please be seated. And now we come up to the end of our journey today. As the closing remarks, we kindly invite the Honorable Dr. Ho Lin, the Executive Director of Science and Technology Division, Taipei Economic and Cultural Office in Australia, to come up to the stage. So please welcome Dr. Ho Lin.
Thank you, Vice President Leo, and all the distinguished guests. It's my great honor to join this today's event hosted by NTUST, and I also thank everyone here to keep yourself stayed to the end of this event today. Regarding to the missions of Taiwan National Science Technology Council, we not only funding support the Taiwan Indonesia Science Technology Innovation Center, but also we funding support all the levels of the international cooperations, including joint research program, scholar exchange, including the professors, lecturers, or all level students, postdoc fellows. So I think it's a really good opportunity for everyone here to cooperate with the Taiwanese scholars. And notably, I would like to announce that there is a newly launched internship pilot program since last year, we funding support the overseas students like the O-level students in Indonesia to visit Taiwan for maximum 3 months. So if you are interested, please contact us. We will let you know all the details. Okay, so again, I'd like to thank you for joining today's event. I hope that being through today's events and all the funding support from our National Science Technology Council, we will have a more and closer collaboration in the near future. Thank you.
Thank you, Dr. Ho. What an impressive closing remarks. And ladies and gentlemen, we have come to the end of this conference. And on behalf of the committee, we would like to extend our deepest appreciation to all distinguished guests, ladies and gentlemen, for your attendance and sharing of knowledge. Many insightful thoughts have been gained during this conference. The last but not least, thank you very much for having me and see you in the next opportunity. Have a good day. Wassalamualaikum warahmatullahi wabarakatuh.